Hello, good afternoon everybody. Welcome to the third edition of the Plastic Conference 2024. This conference is organized by the Institute of Environmental Assessment and Water Research. I am Maria Vittoria Barbieri, a researcher from IDAEA-CSIC, and together with Lara Cioni, my colleague, we are going to chair the next session. This third edition had been specifically focused on plastic contamination, in particular in the automobile sector. And this morning we had many speakers from different sectors, including research, communication, industry, and politics, that highlighted some initiatives and improvements that are currently taken in our society to try to minimize the environmental impact of plastic pollution and in the automobile sector. This afternoon, we continue with 7 talks that are dealing more with microplastic contamination and in particular focusing on its transport and fate and the possible implication for human exposure. Tomorrow, the conference continues with the first session starting at 9 in the morning with the keynote of Luis Cabedo, professor from the University Jaume I. And we'll continue with 4 more talks with a specific focus on bioplastics and nanoplastics. After that, there will be a coffee break at 11. And during the coffee break, there is the poster session. There are 25 posters that are here outside exposed. So if you want to display it, and so you are welcome to look at the poster and ask questions as well. After that, there will be at 12, the conference continues with 7 talks that are more focused on human exposure, and the conference will finish at 2:30. Just to say that in the past edition, the Plastic Conference was held during 2 short days, but this year we received lots of abstracts, so we extended the conference for an extra afternoon, and for that we would like to thank everybody for their interest in participating in this conference. So now let's start the afternoon session of today. For all the speakers, please remember that you have 20 minutes, 15 for the talk, and then 5 minutes for the questions. So the audience is invited to ask questions and be participated and active. And now the first speaker, Giuseppina Zuri, couldn't come, unfortunately, so we continue with the second speaker of the day, which is David Mennekes from ETH Zurich, which is going to present his presentation on plastic fate and transport in rivers. Where do we find the plastic? Welcome, David.
Yeah, hello and welcome everyone here. I'm really happy to be here, although I'm not working in Spain yet. Maybe in the future, or hopefully in the future I will do so. So talking about plastics, I think there are 2 big topics in the risk assessment of environmental risk. On the one side, we have the hazard. And with the hazards, I'm pretty sure we're going to hear about this much more in the later talks today or tomorrow as well. I'm going to talk more about like the exposure. So the exposure of plastics in the environment, in the soils, as well as in the water bodies. And I think we need to remember always that it's very important to think that only where we have an overlap of exposure concentrations with the hazard concentration, there's actually an environmental risk. If you don't have enough exposure, let's say, there's no risk, and we might not be worried so much about like the hazard. So the scope of the studies I'm going to present today is about like this exposure, and we use to model the exposure rates based on physical parameters as well as observational data. We did mostly do this. ¿Todo bien? Vale. Gracias. Well, so we're going to talk about this mostly in the system boundary Switzerland, but we have also other colleagues who did the same or similar studies in other countries as well. And the most important one, we're going to talk about like a very high spatial micro and macroplastic distribution, or like exposure modeling in water bodies and soils. And this will also include like transport processes. Today, given the time frame we have, I will mostly focus on results, but I'm also going to have like some slides about the methods. If you have further questions about the methods, I have down here the papers that you can read so well, and you also can just approach me. So starting with something like the emissions. So a few years ago, Delfin Kawicki and Bernd Nowak started to estimate the emissions. Emissions means like how much plastic is emitted into the environment. And here we see a map for the Swiss water bodies with the red color more high values and with the blue colors lower values. But we also see a lot of rivers which actually are not contaminated by rivers, like emissions into the plastic in the rivers. Sorry. The same we can also do for soils. So here we have a map for the plastics emissions into the soils with brighter colors, higher concentrations, and black colors, lower concentrations. We see two different patterns, and I think this is uniform everywhere, also in Spain, that mostly the plastics emissions are related to where we have higher density populations. Here in the yellow circles, you see the big cities of Switzerland, Zurich, Bern, and so on. So if we summarize all these emission sides, we can say that first, we have much more macroplastic than microplastic emissions, and for Switzerland, we talk about like 510 grams per capita per year versus 75, and we have much more emissions into the soils than into the water bodies. However, these are emissions, and these are not the exposure values yet, because we need to consider that plastics, once emitted into the environment, are going to be transported. In order to approach this, we coupled like an emission model with a transport model. And here I'm going to show quickly some slides about like the transport model and how we calculate the transportation. So talking about transportation, this is like rivers or water bodies, generally speaking, and lakes. We have first the input emissions, and we also have input emissions from upstream segments, rivers or lakes. And then we consider something like the sedimentation or like the yield of plastics. As well, we consider like a resuspension phase, and like the transport onwards downstream is something like the input minus whatever is going to be yielded or retained. Well, this is basically our system we have. And for macroplastic, because we did this for micro and macroplastic, we also added some additional processes. Here we have something like removal basically happening in weirs because the hydrowater plants want to protect their turbines, so they catch out like a lot of debris. As well, we have phases of macroplastic getting stuck in the riverbanks, and there it can be removed. So we did all this modeling for two sizes, basically microplastic or small plastic particles and macroplastic or debris. Then we did this individually for all the river segments. In Switzerland, we have around 200,000 kilometers of rivers. And in each river segment or river sections, it's based on the river flow conditions, basically how fast is the river. This depends on how much force you're then going to have to actually settle plastics or sediments. And also based on the land use, how it's like the meandering and all this. Of course, also it was individually done for each lake. So there we have something like a lake surface or like this lake size. If we do so, and we now couple the emission model with the transport model, we get new results. And here we have like an example of macroplastics exposure in the rivers. And I think two things already stick out a bit. First, more rivers are polluted. And this is quite obvious because now if we have an emission, we estimate the emission, we can now also estimate like a transport downstream. So river segments that might have been pristine going to be polluted afterwards. And we have increasing pollutions down the river streams, or concentrations, higher exposures. Well, to show you some more and get you a bit more into the results, I want to present you some results of this publication. So if you look now and we're interested in how is the exposure in these rivers, we also can have a look at the river catchments. And I'm just going to show you one catchment here. This is the most dominant catchment in Switzerland. It's the Rhine catchment. So this is a catchment, and we're going to look at some results of this catchment. If you want to know how much of this microplastic emitted into these big catchments is now transported outside of the catchments, we see that about 45% is retained for microplastic, and about 55% is going to be transported onwards towards the neighboring country, in this case, Germany. Now, the interesting part is, in contrast to macroplastics, here we see the numbers for macroplastics. Here, most of the plastics is going to be retained in the system or in the rivers, and only a small portion is actually in the river itself, in suspension. So we have a very different distribution of exposure for macroplastics and microplastics. Just to give you some numbers, so the outflowing masses per year, per tons, is around in the same order of magnitude, 4 versus 1 tons. But interesting enough, for microplastic, most of the plastics is basically like 6 tons is retained, and even much, much, much more for macroplastics. So summarizing this, we have similarly high micro and macroplastics emissions in the water, actually. Plus, especially for microplastic, the river environment acts as a reservoir of plastics. Microplastic mostly are retained in lakes. This is a result I didn't show here, but that's what we found. And they're very similar to sediment behavior. And there are also many other studies going in this direction. Also here we have a study, or like we're doing currently some experiments to figure out like how this really behaves with the microplastics and the sediments. And here you see some preliminary results of a master thesis I'm supervising. And we did like different experiments in a flume, which kind of represents like a river. And we looked at different sizes of PET fragments in 210 and 720 micrometer size. And we have different velocities on the axis, basically, so different forces. And the interesting part here is if the particles are small enough and the forces are high enough, you basically see no sedimentation. Although you, based on the density, which is like 1.4, you would expect kind of a sedimentation phase, but you don't see it anymore when the particles are small enough. This is also well understood for sediment science, and now also much more and more confirmed for microplastics. In contrast, again, we have the macroplastics, and what we see here is that we have very high concentrations close to the sources of the macroplastics, and we see very fast and high retention as well in the river systems. How you can imagine this is that the plastics get entangled in the meandering rivers and the vegetation that hangs into the rivers and so on. To show you a result here we see like a long river stretch from kilometer 0, so the source, all the way to kilometer 350, which is basically the boundary with Germany. And in white, you see the microplastics exposure or microplastic concentrations in suspension, and it's basically increasing over time or down the river stream. While in contrast, in yellow, you see how the macroplastic concentration goes up and down on a normalized axis, because we have high inputs close to where the people live, and we have high retentions just close to this input sources as well. Finally, I want to talk a little bit about like plastic accumulation in soils and how I see emissions into the soils. Here's an example of the microplastics into the soils. Well, from what we see on the literature out there is that mostly the microplastics is not very transported in high degrees on soils. So we might have some vertical transport, while this is not so far, and we see maybe small horizontal transports, but only in phases when we have very high slopes. On the other hand, very high slopes, at least in Switzerland, we have in the Alps, and in the Alps we have very low contamination because basically no one is living there. So with these maps here, I did just basically an accumulation of the plastic that, based on an MFA, is emitted into the environment. And you see that in some regions we reach about like 2,500 kilograms per hectare in soils now. Well, this number seems to be very high, but the question is, like, what is happening to this? Does it get anywhere? Like, of course not with the soils maybe, but what are other pathways? And we were discussing this, and here we have an example or like a discussion that we are thinking about that also might happen to actually increase the exposure of microplastics in rivers. And so if you look on the urban areas, basically in a river, in the country here on the left side, and you think that maybe in urban areas we have like pollution into the urban areas, but then you have I would say like artificial transport via drainage systems into the rivers. This is one possible option. Or you might think about like how much of the plastics actually close to the rivers might also be somehow in longer time frames maybe transported to the rivers. And on the right side I have two examples. In red you see basically buffers of 100 meters around each river in Switzerland. So maybe we can calculate how much is like in this 100 meters included. In blue, we see like 1,000 meter buffers, but already with 1,000 meters, we have so many rivers in Switzerland, then it's basically all included in these rivers. Well, to give you just some numbers before I finish. So if you add all the plastic that we estimate is emitted into the urban areas, we might add like another 1,500 tons of plastics into the rivers, which is a hell of a lot of plastics. And this excludes tire particles here, which is on top the same again. And if you look about like the distances to the rivers, we might also think about like another 1,000 to 4,500 tons additionally into the rivers. Of course, we're missing some science here to really understand how much this transport is happening. It's just some thoughts. Well, to sum up like my presentation, I think we can say that we can estimate plastics exposure. For the water bodies, it's very important that microplastic transport is very closely related to sediment transport, and we can relate to a lot of studies published there already. For microplastics, we really see this concept of rivers as reservoirs. For soils, as far as you know, we have mostly no transport, but it's very interesting to look into this, I would call this artificial transport via drainage systems. And finally, we could use this kind of data to do a spatial resolved risk assessment, which would be very cool. Finally, I want to thank everyone here for being here, and also the organizing team and the Professor Denise Metrano, where I'm happy to be in the group here. Thank you.
Okay, thank you, David, for the very interesting presentation. Are there any questions for David?
Hello, thank you for your presentation. I was wondering, because I can understand that macroplastics are more easily retained in the sediment than microplastics, but what is the specific size range that when you are considering microplastics, what is your down limit and your upper limit?
So now we were looking into microplastic, basically something like more in the debris size, and we were doing like a first estimation of looking what kind of processes are understood. And actually for microplastic, we don't talk about like transport in the sediments or being captured in the sediments, but mostly being captured in the riverbanks on the sides. And for microplastic, the lower limit we're thinking now, based on the material flow analysis we're looking in and what we're looking at, is more like something like nanoscale, down to the nanoscale.
Nanoscale, okay, really small, okay.
But like, because we talk about masses, it's not really important, the small particles. Would be very important if you talk about the hazard.
Yes, I understand, just to have an idea. Thank you.
I think there was another question here in the front.
Hello, and thank you very much for the presentation. In the case of the soils, for example, did you validate the results? Can you validate that? Because at that scale of the country?
So for the rivers, we have some measurements. There are not so many measurements, obviously, so we can validate it, and we're in the same order of magnitude. Because, of course, if you do measurements on modeling, we're happy in the same order of magnitude, more or less, because everything fluctuates a lot with weather conditions and so on. With the soils, we are not there yet, also because like we are just doing a very roughly first estimation of what are the numbers we might be talking about. So if you go to the soils, and I think everyone who samples soils knows this, you might look here, you find a high number, you might look here, you find nothing, right? So it's harsh to validate it directly.
Any more questions? I think we have time for one last question. Okay, otherwise I think we can move to the next speaker. Thanks, David. So now we will have a presentation from Marta Blanco from ICM-CSIC, and she's gonna talk about linking marine litter land sources and its spatial distribution on fishing grounds in the NW Mediterranean Sea. The floor is yours.
Okay, so yeah, as she presented me, I'm Marta Blanco, and I work in ICAT-MAR, the Institut Català de Governança del Mar, and today I will present you this work entitled Linking Marine Litter, Land Sources, and its Spatial Distribution on Fishing Grounds in the Northwestern Mediterranean Sea. I will talk about marine litter. So, in fact, marine litter is a global problem. It is defined as marine litter is any manufactured or processed persistent solid material that is discarded and disposed in marine and coastal environments. It is estimated that between 19 and 23 million tons plastics ended in aquatic ecosystem. And it causes environmental degradation and also wildlife harm. And also socioeconomic losses related to its negative effects and costs of removal effects. In enclosed seas like the Mediterranean Sea, it may have the highest amount of waste, both floating and also benthic marine litter. The seafloor is, in most cases, the last destination of marine litter, and this waste is commonly captured by the nets of bottom trawlers. So, bottom trawling fleet is an important actor for Fishing for Litter initiative. It is estimated that bottom trawling fleet in the Catalan Sea potentially removed 2,237 tons of marine litter per year. So, marine litter sources can be many, from the sea and also from land source. But in most cases, seafloor marine litter comes from land. The land sources can be many, but the ones that we detect that are more important are the submarine outfalls, also the river mouth, and big cities like Barcelona, which concentrate more inhabitants, and coastal areas which concentrate a lot of tourism during summer months. So the main objectives of this work are to do a characterization of seafloor marine litter in the northwestern Mediterranean fishing grounds, and also do an identification of the factors that contribute to its spatial distribution, and analyze the marine litter spatial distribution in the Catalan Sea. So the sampling consists that after each haul, the fishers sorted the catch into two categories: the commercial catch and discarded catch. Discarded catch is composed by no commercial species and also by natural debris and marine litter. And this fraction is transported to the laboratory, and once there, all marine litter was classified and weighted. The classification of marine litter was done following the European directive into 6 categories. Metal, which includes cans, lids, and other kind of metal waste. Rubber, that includes some pieces made with rubber, like balloons or boots or everything. Textile, also plastic, that which includes wet wipes and other sanitary waste, and also bottle plastics, or plastic bottles, plastic bags, between others, wood, and other waste that cannot be included in the other categories, like batteries or others. So from ICAT-MAR continuous monitoring program in the trawling fleet, we analyze marine litter in 9 ports along the Catalan coast in 420 hulls from 2018 to December 2022 in 3 depth strata: the continental shelf, the upper slope, and the lower slope. So the factors that we analyzed to contribute to the spatial distribution of marine litter, we choose the season, depth strata, and also for land sources as the distances from this source. The distance to the city, we consider only the city of Barcelona because it's the biggest one in the study area, which concentrates more than 1.5 million inhabitants, and the distance to the coast, the distance to the river mouth, and the distance to a submarine outfall. Additionally, we evaluate the effect of fishing effort on the spatial distribution of marine litter. Because if fishing for litter work, we will expect that in areas with higher fishing effort, we will have a less marine litter, less density of marine litter. So this is our results. This table shows the mean density of marine litter by each category, and the P chart shows the percentage of each category. The mean marine litter density in the study area was 8.22 kilos per square kilometer, and the most important one was plastic, which represent more than 64% of the total marine litter. And the most important plastic was wet wipes. As we can see in this map, the spatial distribution of marine litter show higher values of marine litter in front of Barcelona, with some house that concentrates more than 200 kilos per square kilometer. These two box plots show the density of marine litter between seasons and between depth. The highest mean value of marine litter was observed during spring and in the continental shelf too. However, as you can see in these plots by the black dots, a high dispersion is observed on the marine litter density. And this indicates that there are some areas that act as hotspots in some times. So this map shows the fishing effort for the trawling fleet, and the blue lines indicates the hauls. And as we can see in this result, fishing effort don't have a significant effect on the spatial distribution of marine litter. And this indicates that marine litter removal by the trawling fleet will not affect its distribution. So the best model who explains the spatial distribution of marine litter in the Catalan coast considers the factors as sampling area, the distance to the river mouth, and the distance to submarine outfall. And the third column shows the deviance explained by each of the factors. And this map shows the predicted spatial marine litter distribution in the Catalan Sea. And as you can see, high concentration near Barcelona and also near Tarragona, and in the continental shelf between Palamós and Blanes. And lower densities were observed in the northern and southern boundary of the study area. And this plot shows the observed density in each howl versus the predicted density by the model selected. And as to finish, and as a conclusion, we observe a large variability in marine litter density in the study area, with a clear predominance of plastics, with more than 64%. And also we observe hotspots identified near Barcelona and other urban areas. No significant correlation was found between fishing effort and marine litter distribution, indicating that basing seabed cleanup on fishing for litter is not sufficient. So it is important to act at the source. Proximity to land source such river mouth and submarine outfall, plays a key role on the distribution of marine litter. Reducing the arrival of litter through these sources is essential to reduce marine litter at sea. And finally, it is vitally important to address the marine litter problem by considering the spatial and temporal dynamics of its distribution, and to focus on reducing inputs from land-based sources near urban and also industrial areas. So thanks. If you have any question.
Thank you, Marta, for your nice presentation. Any question in the audience? No? Yeah.
Thank you very much for your nice talk. I have a question. Have you looked at the polymers you found? Were they buoyancy? Can you hear me?
Yeah, but I don't understand you. What
have you checked for the polymers you found?
Polymers?
Yes.
No, we also check for big macro marine litter.
I think there was another question here.
Thanks, Marta, for the presentation. How or why do you explain that you find that water density, the higher in spring than in summer? It shouldn't be or expected to be higher in summer because of tourism and related activities?
We expected that, but we didn't find that this factor was explained the spatial variability. So we expect it on summer, but as we read in other works about seafloor marine litter, that marine litter sinks from the surface. So perhaps we will expect in summer at the surface of the sea and also in beaches, but this
like in winter sinks,
yeah, it need to sink, and perhaps the most important events to sink marine litter is during storms that can occur during winter and also spring.
Okay, thank you. Any other question? Yep. Here, Lara.
Thanks for the nice talk. I was wondering if, depending on the distance, the categories of litter were changing, or was it more or less the same?
We didn't find that. We are doing more work about the categorization, or do more categories to define better what marine litter we have. But we didn't find, or with our eyes, didn't know that there are differences in the different depths or distances.
Yeah, thank you.
Okay, thank you very much. No more question? Okay, thank you again, Marta.
Okay.
Now we move to the next speaker, Manuel Serrano from the Doñana Biological Station, which is going to present his work about las gaviotas como biovectores de la dispersión de plásticos desde vertederos a humedales.
Well, hello everyone. As she said, I'm Manuel. I'm a PhD studying from the EBD, and I'll be presenting Gulls as plastic biovectors. First, I want to talk a little bit about our studies, because we are studying how water birds are dispersing plastic from landfills and urban areas to natural spaces. So first, let's talk a bit about plastic and its production. 377 million tons are produced every year, and of those, 8 million are ending in the sea. And this is more or less like dropping a truck full with plastics to the sea every single minute. And we all know how those plastics are getting dispersed by wind, by the water, by the sea flows, the tides and everything, and also human are affecting those plastics dispersed because of moving those from urban areas to the landfills, and also going, for example, for the at beaches at the vacation and letting the plastic over there. But what about animals? What about birds? How are they dispersing those plastics? Well, animals, in this case birds, are also a very important biovector for the plastic dispersal. First, because they are building their nest using those plastics that they found in the urban areas and landfills, and also by the pellet dropping. Pellets are basically the non-digest substance that they eat and they cannot digest, and they drop it in the natural spaces after eating in anthropogenic places. But they are also very important biovectors because first they are migrators, so they connect very far away places from other places. They are generalists, so they might be eating in natural spaces, but also they tend to eat quite easily because it's full with food in landfills and urban areas. They are widely distributed, so those birds, we can easily find them basically worldwide, so they are connecting those places, and they are colonial, so they are not dropping the plastic anywhere. They are creating what we call the hotspot of plastic dropping. Our study place is a marsh in the southern of Spain, in Huelva, that is at the end of an Odiel river, and there is also a very big salt pans where there is production of salt for human consumption, so this might be affecting the salt quality. But also it's a very important place full with biodiversity and different birds that should be pristine. Our study species are these two that make look quite similar, the yellow-legged gull and the laser black-backed gull. The first one is a little bit lighter, just to divide them by just in a sea. But they have different foraging strategies, and they are biologically a little bit different. For example, the yellow-legged gull is a non-migrant bird in our place and is breeding in the area. They are also more related with sea foraging, so they tend to eat a little bit more in a natural way. The laser black-backed gull is a winter migrant, so we don't really have them here, and they are not breeding in our area. And is more an inland gull, and we can easily see them in the landfill and urban areas while it's staying here. But the important thing about these two species is that they are sharing an important point, and is that they are both doing daily trips and travels from the wetlands to those urban areas and those landfills where they eat, and then they go back to the natural areas where they drop all these plastics and debris. So, summing up, they take their rubbish and then they go back to the natural spaces where they put those plastics and debris. So this is the way they are moving the plastics. The methodological approach of our study was basically taking those pellets and analyze them using GPS tracking data from the gulls, census data, and tissue analysis to see how those plastics are not only affecting the environment, but also those gulls directly. So the first thing we need to do is go to fieldwork, grab some pellets, and then go back to the lab. Once in the lab, we take those pellets, we dry them, and we make them pass through a sieve of 0.5 millimeters, and then we analyze them one by one in a stereo microscope to separe all these plastic and anthropogenic items to analyze them. The first analysis we'll be doing will be an FTIR, but that is basically an spectrophotometry that is going to tell us what kind of plastics they are eating. And every plastic has a special profile, so if our plastics are matching one of those, we'll know which kind of plastic they are eating. And the following one will be a physical analysis that starts with a picture of the items, and we'll do a color analysis, a size categorization, if they are under 5 millimeters, we'll be considering them as micro. Mesoplastics, if they are between 5 and 25 millimeters and above 25, they will be considered macroplastics. We also are doing a type categorization that will be separating hard kind of type of plastics, line as ropes and everything, foam and film. Those all pictures were found inside those pellets from the gulls. Our first results shows that both gulls are foraging a little bit different, and being the yellow-leg gull, the one that is showing up with less plastics in the pellets, even though it's more than half of the pellets being found with anthropogenic items. And the laser blackback gull show a little bit more of plastic items, over the 75% of them showing up plastic items. Even though they are foraging a little bit different, once they have been eaten and swallowing those plastics, those both pellets are kind of similar. So from now ahead, I will be analyzing them all together, not differing between species. And as we can see here, most of the plastic were hard type, followed by line, foam, and film, but we also find a lot of glassix, for example, inside those pellets. For the main of plastic item found, most of the, between 5 and 6 items, plastic items per pellet were found inside those pellets. And the one that we found with more plastic items were 39 plastic items per pellet. And the main of the weight of the plastics found was around 0.26, 27 grams per pellet. And now we wanted to analyze how many plastics per size we got in those pellets. Again, differing them in micro, meso, and macroplastics. And we found out that the majority of the items were in the microplastic part, or the latest tiniest mesoplastics, and they were all hard plastics. So this is giving us the information that those hard plastics are the ones that are getting broke and dispersed more easily by those kinds of birds. Jumping now to the GPS and movement data, the first thing we need to do is grab a bird, put a GPS tracking device, and let it free. So now they are helping us to do this kind of science. So every 2-3 minutes, they are giving us a location information. But not only this, they are giving us speed information and the height they are flying or staying. So we got a lot of information about those kind of devices. So the first thing we wanted to know is what are those birds doing during the day. And so here we can see the hours of the day and the percentage of the individuals in every hour. So we can see that at the beginning and at the end, basically at the night, and those gulls are in the Odiel marshes. So they are staying here at safe and they are sleeping over there. But during the day, they are moving, they are traveling to urban areas, to fish auction, to those fields, to the landfills, to forage. So they go to those places, they eat all the rubbish they can consume, and then they go back at night where they drop those pellets. With this GPS data, we also could do what we call, as I said, the hotspot of plastic dropping. The first of it would be just in front of the urban areas that we have. The following one will be in the salt flats that could be affecting the quality of the salt that is being used for human consumption. And the other one, the most important one, in the heart of the Odiel marshes where the colony is located. This hotspot is quite special because it's not only by those pellet dropping, because they are also building their nest over there, and they are also using a lot of plastic in the nest. This is another study we are carrying. But yeah, because they are building the colony over there, most of the plastic are going over there. We also realized that there is a difference between winter and breeding season, and also summer, because during summer, more people are going to the beaches they are going for vacation and everything. So this is ending up in more rubbish that is ending in more gas that are coming to forage in the urban areas, and with the implication that more people are coming while those birds are breeding. So all this rubbish is contributing to grow up those tiny chicks that could be affecting the fitness of the birds. As we can see here, during the summer, more birds are going to the urban areas, and they are not foraging in the landfills because they are farther away, so they prefer staying next to the marshes where they can find food easily. And finalizing, an histological study is also being doing, so we can study how those plastic and sowing all those plastic with all the contaminants that are related with them are affecting directly the individuals, the gulls. This is a tract of a gull that is not affected by plastics, and this one is affected by plastic. All this blue tissue is basically fibrosis. Fibrosis is a kind of disease that is created when there is a scar after scar formation, and this is ending in a gland loss. All the tissue will be with a chronic inflammation. This reduces the amount of nutrients the gull can take from all the food they are taking. So this is a really important disease that the gulls are suffering from taking all this plastic. All these plastics are not only in the tract, they are also jumping, the tiniest part of them, to the blood system, and they are ending in a lot of different spaces. So for studying this, we are taking tissue samples to analyze all the contaminants that they have, and also we are taking the whole tract to analyze what is inside this tract, so we can directly know what are they eating. For finalizing, I will like to give you the last important point is that gulls and these kind of birds are not the responsible for moving all these plastics. They are just another group, they are just animals that are affected. They are just using what they have for foraging and to grow up their colonies, but they are not the responsible for moving. They are just affected for our bad management of the residuals. So thank you all for listening, and thanks also to my group that is helping me for all this process and has given me the opportunity of do a lot of good stuff. Thank you all, and any question?
Thanks a lot for the great talk. Do you have any questions? Maybe I can start with one. So I was wondering, you said that often these birds use plastic to make their nest. So I was wondering if you have any data, if the birds that use more plastic for their nest would then be more exposed. Did you see any difference in the number of plastics in the pellets depending on how their nest will build? I don't know if you have that kind of data.
Yeah, for now we got more observational data. We are not only working with gulls, we are also working with the white stork and the cattle egret for now. So for example, the stork is showing up with a lot of plastic in their nests, and by ringing them, we've seen that, for example, some chicks get a rope in the leg or something, and they lose the leg. So these kind of birds, obviously in nature they are legless, they might be not survive as long as other birds. So yeah, they are basically affecting not only the ecosystem by bringing those plastics, but also the individuals.
Yeah. More questions?
Thank you, Manuel, for your presentation. Just to clarify, so you see that in the urban areas during summer, there is like a higher amount of pellets that are transported. So you suggested, or your main conclusion were that these are higher, like due to the tourism, that due to the normal migratory behavior of the gulls.
Yeah. Most of the birds, I mean, the hotspot of taking those plastics in the urban areas were related with bars, pubs, chiringuitos, and where all these rubbish cans are located. So they are not like distributed in the urban areas wherever. They are looking for certain places that we are matching with those kind of places that are more polluted in summer. So we can relate those two informations.
Okay, thank you.
Okay, any last questions? Okay, otherwise, thanks, Manuel.
Thank you.
And we can move to the next speaker. So the next speaker is Julio López Donal of the Beta Technological Center, which will tell us more about the project Plastic Pirates Go Europe.
Well, thank you. I am Julio López. This presentation should be presented by Meritxell Abril, but she has different problems, and I'm going to do this presentation in behalf. Okay, the aim of this presentation is to show you a program, a citizen science project that has the aim of monitoring plastic litter in European rivers. Well, as you know, the plastic litter is a problem, and a global environmental problem. In the sea, we have more or less 12 million tons of plastic residues that arrive to the different oceans and seas each year. And as you know, the rivers are the main contributors of this pollution. Well, rivers transport this litter that arrives from landfill, for example, seaways, runoff from the lands, and so on, and they make us transport way of this litter to the rivers. However, despite of this importance of the rivers in the contribution of the plastic pollution for the aquatic marine ecosystems, we have several gaps on the knowledge. For example, the different studies that started to study the problem of plastics in the sea, they started in the 18th, more or less, but only until the 2010, we start to have knowledge and to produce results on the effects and presence of this litter in freshwater aquatic ecosystems. So we have a very limited understanding of the pollution source, the effects, and also the storage and other degradation cycles of this plastic litter in the aquatic ecosystems, freshwater aquatic ecosystems. On the other hand, we have a water framework directive that it focuses on water quality, but only focusing in different quality elements. For example, the biological quality elements, like, for example, abundance and presence of diatoms, microinvertebrate communities, plants, and so on. We also has chemical and physical characterization, focusing on nutrients and other chemical substances, and hydromorphological alterations. But we still don't have monitoring protocols for the regulation of these products and these materials, and also to know the quantity and the effects of these substances in the environment. This is a bit contradictory because we have information and we have different evidences on the effects, negative effects, and presence of these substances and materials in the organisms, animals, macroinvertebrates, biofilms, and so on. For this reason, we propose the citizen science as an instrument, as a tool, in order to cover this gap in the knowledge of the presence, quantity, and quality of plastic litter in aquatic ecosystems, freshwater ecosystems. The citizen science has two different or more advantages. One is that we have a big effort, a sampling effort. We have a lot of people working. We have a high temporal scale covered and also geographical scale to be covered. On the other hand, the citizens, the participants, has insight or an awareness on the different environmental problems that they work. In this case, about plastic pollution in freshwater ecosystems. Well, the project that I am going to present here is the Plastic Pilot Projects. This project started in Germany 8 years ago, and it is still working. They have a big amount of points, sampling points, and also a big collection of data, a temporal and geographical data collection, and they have demonstrated the validation and the quality of this data enough to produce scientific results in order to monitor, in order to explain the presence and the typologies and quality of these plastic residues in freshwater ecosystems in Germany. Now this project has been extended to other European countries. Now we are participating in 12 European countries. And this project has been of interest for the European Commission. This is included in the European Union missions Restore the Ocean and Waters. Here in Spain, the Beta Technological Center, together with the University of Burgos and in collaboration with IDAEA, as well as Fundación Oxígeno, we are coordinating this project here. We started in autumn of 2022, and we have performed 3 different sampling campaigns, and we are to develop 2 more in this autumn. We are starting with the sampling campaigns, and we are to finish in the next spring. The geographical context that we are covering is Castilla y León, mainly Burgos province, Catalonia, the 4 provinces, and also several countries, several villages in Galicia and País Valencià. Well, how this project works? Well, we have a big effort in order to recruit schools and other young associations and other groups involving students from 16, 18 years, more or less. This is the range of ages that we work with. We call them, we make mailings and direct contact in order to recruit these participants. And then we perform different training activities and coaching. For example, we perform 7 webinars in order to explain the protocols. We make also demonstration in situ, for example, helping in the sampling campaigns and so on. Then the activity is performed. Here you can see the activity. And finally, they have all the data collection. Once they have developed the activity, they collect all this data and they upload in a platform that we have, an European platform, in order to storage this information and in order to have this data. Then we start, the scientists involved in this project, we start the data verification that we are going to explain now how it works. Well, the sampling, the plastic pilot has a very standardized protocol. Here you can see different materials that we provide to the students and to the teachers. This is the action booklet. This is the hoja de campo, the fieldbook sampling protocol. This is another supporting material for the teachers in order to complement in the classroom, talk about the problematic of plastics and so on, and different activities. And also we have in the web page, the website, this is the one, we have other different materials, videos and so on, in order to teach, in order to have other materials to help the teachers and the students to develop the activity in the field and in the classroom. Well, this project has mainly 5 groups. We are going to focus on the group A and B and the group D. The different groups has different roles in the sampling activity. The group A makes a study of the quantitative aspect of the plastic litter in the riverbank. The group B works on the quality. They focus more in classification and identification of different plastic items. And the group D makes a support in taking this information, taking pictures, and also helping to the other groups in order to cover the information. The group C works with the analysis of microplastics, but we are not to focus now in this point. Microplastic is a point that is analyzed by IDAEA, Marta Llorca, many of you will know, but we are not to show results. And we have another extra group that is not performed here because the substrate is not good enough. It is just to study the presence of microplastics in the sand, but the substrate heat is not so good to work in this way. Well, how it works? Mainly the students select a river section. This river section has 100 meters of length and 20 of width, counting from the river. The participation, more or less, is between 10 and 30 students in order to be operative and to develop the activity correctly. And this is more or less the sampling, an scheme of the sampling area. Here we have the area for the quantitative sampling, the group A, and this is for the qualitative sampling. This is the sampling areas. They are 7 meters squared, but they have 9 circles in order to develop this quantitative sampling. This is more or less an ideal place of working. There is the rubbish, we have bottles, different cans, and so on. And this is, well, more or less is the place where the students work. No? So they have to develop these activities. The group A focus on a quantitative approach. They count the number of items in meters squared. This is the area, the sampling area. And they can work in different transects separated with 10 meters more or less. And then they can upload this information in this grid, in this template. Here you can see the different categories that we have. They are the European categories: paper, plastics, metals, glasses, and so on. This is the different categories, and here they can put the numbers of the different items found in the sampling area. And here, this is the group T. Take pictures of the different circles and the material found in the different circles. Then we have the group B, and the group B works in a qualitative approach. In this way, in this area, they have to count the different items. Here they have a grid with the different categories. Here is more detailed, and then they have to put the number and then count them, and then finally they can count the weight of the total waste. Again, the group D helps the students, help the different students in order to take the pictures, and this we are going to explain then, but these pictures are very important for us in order to validate information. And well, as I told you, the information is uploaded and is worked at the classroom. Then you upload to the platform, and then we receive this information, and then the start our work. That is to validate this information. In order to validate this information, we have a clear protocol in order to select the pictures, in order to select the information, and so on. Here you have a reference in order, if you want to know more about this criteria of validation. And well, as I told you, basically the work consists in compare these pictures with the data that is supplied by the students. For this reason, pictures are very important in order to contrast this information. We count, for example, we confirm the quality, the quantity, and so on. Sometimes we can find differences between the picture and the categories and the number of the different items, and so on. For a good validation, we need good pictures. This is the picture taken, for example. This is a good example of pictures. We can count each element. They have well classified by the different categories and so on, and this is a very bad example. Here we can't do anything, and this is a pity because they do the work, but we can't use this information for any treatment. So we have to discard this group and this classroom, and we lost this information. And now we are going to show you some preliminary results just to demonstrate that this information is very useful for the monitoring and also in order to provide information about hotspots and quality of items finding and the places where we can find more and different plastics in rivers. Well, this is some data about how this project has been increasing in number of participants as well as sampling sites. Now, in the last edition, we have 32 schools, and the main basins were the Duero, l'Ebro, and the internal Catalan basins. Despite the bad results, we have only 6% of rejection, so the students work quite well, and we have a good size of information in order to work. This is information compiled in the group A, the group working in a quantitative point of view. And thanks to this information, we identified some hotspots. These hotspots are related to big cities or industrial poles. For example, this is the city of Burgos, and this is Miranda de Ebro, two cities with high industrial activity, and also the corridor of the Besòs River and Girona with the Ter, for example. This is very interesting, and it's related also with the last presentation on litter in the Mediterranean. So I think it's interesting also to correlate. Going to the group B, this the average contribution of the different categories to the total percentage of waste. And as you can see, more or less 70% of the plastic is a single-use plastic. If we go in detail of this single-use plastic, mainly the four main contributors are plastic packaging, the web sanitary papers and products, plastic bags, and the bottles. This is a constant that we have found in the different sampling campaigns and also in the different sampling points. Here again, hotspots related with this spatial pattern. This is again Miranda de Ebro, and this is the corridor of the Besòs. Santa Coloma de Gramenet and Granollers, they are the main contributors of the pollution are the wet pipes also. So I think it's another interesting point, but because these results has been repeated in the different editions. So yeah, this is a big problem. And now I'm going to the conclusions, maybe a fast presentation. Well, this is the conclusions. We had a high participation in this program, and this means high spatial and temporal coverage. But on the other side, this is also a problem because this means high effort on coordination and also in the analysis of data. On the other hand, the protocol seems to be easy to be applied because the percentage of the rejection is very low. This means that we have a very good database on plastic presence and quality and quantity in different sampling points. So I think it's a good result also. On the other hand, we had a good feedback from the participants that this means a high satisfaction and engagement. Many of the groups repeat in the different years, and we have fidelized schools and people that participate in the different editions. And as well, students and teachers are very happy with this program. And other point is that it is interesting to be complemented with other citizen science projects and even with other scientific projects, I think. For example, now I found very interesting these correlations within the results obtained in the Besòs and the pollution in the Mediterranean and close to the Barcelona city and so on. I think we can make collaboration in this sense. And finally, we think that this information is of interest for different managers at the level of local, by water, environmental, Agència Catalana de l'Aigua, Agència Catalana de Residus, and so on. This kind of stakeholders that could be interested in this information because we are covering the sampling effort that they can't do and they don't do. So, and this is finally, and thank you very much. If you have questions.
Thank you very much, Julio, for this talk and for the initiative, actually. Yes, there is a question.
Thank you, Julio, for this nice presentation. I was wondering if, with these hotspots that you detected with these samplings, there is any relation or there is any role that you can define with wastewater treatment plants? Because can you find more plastics down waters from wastewater treatment plants? Have you checked this?
This is a point that we have to work, because when the students perform the sampling, they don't select the sampling point with these categories. The criteria to select the sampling point is another one. But sorry, pardon. No, the criteria that they use is the proximity to the school and another criteria. So we don't have the information on the wastewater treatment plants is a posteriori. Now we are going to check these sampling points, because we have the coordinates and so on, and to check if they are before or after sampling wastewater treatment plants. In the case of Granollers, we think that it is done because the com es diu això? Els abocadors, les efluentes de Alcantarilla. No, it's not a wastewater treatment plant, but it's urban seawash. But the other points, we have to investigate it.
Thank you. Any other question? Yeah.
Thank you. I really enjoy always like the citizen science. I was wondering, how do you select the locations? Because I think there were other works showing that people like to select locations with a lot of litter because they're more interesting to look at.
Sorry?
How do you select locations? Like, where do you do the measurements? Who is selecting the locations, the sampling sites?
Yeah, the location is selected by the schools. We don't have this control on the places where the school sample. So, as I told before, they used to select the sampling point related to the proximity to the school, or if they are easy to sampling or not. Remember, they are children, and sometimes it is difficult to move 30 or 20 students to a sampling point. So they have to be careful in this point, and sometimes they don't have bus and so on. They have to go walking and so on. So this is a limitation maybe, because we don't have this control. We can't select the point of interest for us. They select or choose point of interest for them. I don't know if this is a question.
No, that's okay. Thank you. No, that's okay. Thank you very much.
There was another question, I think, here in front.
Hi, thank you for your presentation. I was wondering if will you involve any other communities, such as neighborhoods of those places, instead of only schools?
Not at the moment. We are thinking in this because it could increase the range of participants. But now this is thought to schools because for us it's easier to contact with them, because we have a representative that is the teacher, and also the interest for the schools is that they can include this activity in the different school activities and educational activities. But I think the protocol is also useful and could be applied by other interest groups. But now it's like it's a practical or functional question. It's not another one.
Thank you. Any other question in the audience? I think we have time. If there is no other question, I will ask, because at the beginning you said that there were less data for freshwater than in marine environment, and now that you have some data of freshwater, you can correlate somehow the differences in the type of material and garbage you find, like if it's more or less the same in terms of percentage.
In the sea?
Yes.
Well, now we are going to be sincere with you. We have a lot of data, but we don't have time to analyze them. No, it's a joke, but we have a lot of data. We have to work with this, because Yeah, now we have started to compile a significant volume of data in order to obtain significance in this analysis. But well, it's a good idea to check, no, if we have the same pattern between sea and rivers and so on. Yeah.
Okay. Thank you very much, Julio. So the next speaker is Manuel Barbero from the Polytechnical University of Catalunya, and his talk is entitled Liberación de microplásticos en lavandería industrial.
Okay, so thank you very much for the attending. I'm going to present a study called Release of Microplastics in Industrial Laundry Processes. It's part of my PhD thesis, in which the UPC has been involved as the academic part and Girbau is involved as the industrial part of the thesis. So maybe you know UPC, but not Girbau, so I'm going to start presenting or introducing you Girbau as a company. Okay, so Girbau is present in more than 135 countries around the world. It had a turnover of 193 million euros in 2023, and it provides products and services to the industrial laundry business, from machinery to turnkey projects. We are divided in two divisions, commercial division and industrial division, and our purpose is to be a reference for creating a positive impact on people and planet. And as we notice, the 35% of the primary microplastics that arrives to the oceans coming from the laundering of synthetic clothes. So a few years ago, we decided to estimate the microplastics that are coming out from our machine. So we did this exercise and we conclude that annually 500 tons per year are arriving to the oceans directly from our machines. Taking in account that 80% of this water is arriving to wastewater treatment plants, with 90% approximately capturing the sludge, and it is a bit controversial, but 90% of capture, and the remaining 20% arrives to mistreated wastewater networks. At the end, our washing machines are emitting 156 tons per year of microplastics. It's the equivalent of 700 billions of microplastics and the weight of 2 blue whales. Okay, so if we want to be loyal with our purpose, we focus on minimize or trying to start a project to minimize the emission of microplastics from our machines, knowing that it is not our impacts, the impacts are generated by our customers, but it opens a window of opportunity to be honest, to be loyal with our purpose. No? How? So publishing good practices manuals to our customers and to designing microplastic retention systems to be fitted to our machines. And for that, we start this study, and the main objectives are to characterize the life cycle of garments in terms of microplastic release, understand the influence of washing factors on microplastic emission, and to study the morphology of release microplastics. Okay, so to do that, we use a laundry machine, one of our laundry machines with 13 kilograms of nominal capacity, and we filled this machine with 8 kilograms of polyester commercial textiles. This is the program that we implemented to the machine with 3 phases and different temperatures, chemicals, degrees of mechanical action and duration. And we install in the outlet of the washing machine a bypass to capture samples from the different washing stages. Then we take a composed sample from all these different stages, a proportional sample. We analyze all of the 5 samples at the end with a suspended solid based method. It's a gravimetric method. In this method, we use fiberglass 90 millimeters filters that allow us to filtrate big samples and to minimize at the end the total error of the method. Then with the composed sample, we did a characterization that has the objectives to do a counting of or to know the number of microplastics per liter of water released by our machines, and to also analyze the length of microplastics. To do that, we use cellulose nitrate grid filters, and then we perform a microscope analysis and data treatment with a limit of detection of 50 microns. This limit of detection we impose ourselves because we thought that if we try to count or to analyze particles below that limit, we are doing a lot of analytical errors. So this is an example of a microscope photography of the surface of the filter, and these are with all the fibers characterized. With this characterization, we are able to obtain the microplastic release units in microfiber per kilogram of garments, and also the average length of the microfiber or the microplastic detected. So with the average length, we try to impose a cylindrical shape with a regular diameter to these fibers, to calculate the average volume of each microplastic, and then taking in account the density of the material, that it is polyester, to obtain the average mass of each microplastic. And mixing the microplastic unit release with the average mass of each microplastic or the typical microplastic, we are able to obtain the microplastic concentration, and then we can compare it with the microplastic concentration obtained by gravimetry methods. So these are all the tests that we did to obtain the results. As you can see, there are 30 cycles, because it is considered that 30 washes is the life cycle of commercial clothes. And these are all these quantification and characterization that I have told before. The results. Okay, so in this graph, we can see the microplastic release for the whole life of the garments. We did 2 replicates, so this is an average for the 2 replicates we did. In the left axis, you can see the milligrams per wash garment and per kilogram of garment and wash. And in the right part you can see the cumulative microplastic amount release over the whole life cycle of the garments. We can see that in the first washes there is a lot of microplastic release due to we think this is plastic fibers that remains in the textiles after the manufacturing process. Here in this graph, you can see for the 2 replicates that we did, the contribution of each washing stage to the total microplastic release in the whole wash, in the whole washing process. If we mix both graphs and we isolate the first and the second rinse, which has different mechanical action degrees, we can observe the impact of the mechanical action on the total microplastic release, that in this case was 80%. So the 80% of the microplastic release depends on the mechanical action. If we try to also to isolate the first and the third regions, we can observe here the influence of the softener on the microplastic release. That for us it is known. It is, yeah. Here you can see the density distribution of lengths of all the microplastic that we have analyzed in the microscope. With this data, we characterize the average microplastics. The average microplastic for this case that has a length of 421 microns, diameter of 24 microns, and with supposing the density of the material, the average mass, that it is 2.16 per 10 up to -4 milligrams. So here the microplastics, the microfiber release per kilogram and was of the fibers bigger than 50 microns is 100,000 microfibers, but we try to analyze or to know how many fibers are released between the 1.2 micron limit of detection for the quantification and 15 microns that it is the limit of detection for the characterization. So taking into account the mass of the typical microplastic and the average release in units of microplastic per liter, we can obtain this concentration of 2.01 milligrams per liter, that if we compare with the same sample with the result of the quantification, we obtain that there are 0.26 milligrams per liter that are missing there. No? So imposing again a cylindrical shape, density, and an average length, we can estimate the number of microplastics that we are missing in our analysis, that are around 200,000 microfibers, that as they are very small, between 15 and 1.2 microns, they represent a little percentage of mass of the sample, but a lot of microfibers that in microplastic problem is a big issue. This is our results compared to the literature in this topic, and I'm going to go for the conclusions. 2,000 milligrams of microplastic released per kilogram of wash garments along life cycle. 10 up to 7 microplastic fibers released per kilogram of wash garments along life cycle. 89% of the mass of microplastic release is attributable to particles longer than, or to fibers longer than 50 microns, but only 32 of the microfibers emitted are longer than 50 microns. The 80% of the microplastic emission reduction is achievable by minimizing the mechanical action in the washing. 44% of microplastic release throughout the life cycle are released in the first 5 washes, and this is important. And the average length of the released microplastic longer than 50 microns is 421 microns, and this data is very important to design microplastic retention systems or devices. Just to end my presentation, I'm going to put you a realistic example to take these numbers that we have obtained to the real world. So supposing that in a week we are washing 8 kilograms of clothes, and 69% of these clothes are polymeric. In a year, we are washing 400 kilograms of clothes, and we are emitting 21 grams of microplastic per year per person. So, taking this data to the city of Barcelona, we are emitting in a year 36 tons of microplastics that represent 17 billions of individual fibers. If we suppose, and again it's controversial because it is retained in the sludges and so on, but if we suppose that 90% is retained in wastewater treatment plants and only 10% is leaked into the environment, we are releasing directly by only washing machines 1 billion of fibers that put together could cover a surface of 64,000 square meters that could represent to cover all the Plaza Catalunya and Ramblas by microplastics. Okay, so thank you for the attention. And
so thanks, Manuel, for the great presentation. Are there any questions? One over there.
Thank you, Manuel, for this very illustrative presentation with numbers, figures, and so on. So then you are investigating this for an industrial company, no? For Girbau.
Yeah.
But as any of us here, as machine users, because what we can do at home? We can use any kind of filters to adapt in our normal washing machines to avoid these 21 grams per year, or there is any that we can do?
From my opinion, the best way to not emit microplastic is to not wear microplastic or macroplastics. No, is the first thing. But the second thing, I mean, there are some brands, commercial brands. I mean, we are focused on industrial businesses, and we are affected by regulations and so on, but there are a lot of commercial brands that are selling microplastic filters. I mean, for me, it's not the solution. The solution should go through wearing less plastics at the end, but there are some commercial filters for domestic washing machines.
Any more questions? There's another one there at the end of the room.
Well, thank you for your presentation. I was wondering if your company was having an interest in developing filters. That I think so, but it would be better to focus on filters in the individual machine or like in wastewater treatment plants, because in the end, these microplastics are anyway conveyed to the wastewater treatment.
Yeah, very good question. In the case of laundering, we are not talking about regular microplastics. We are talking about fibers, microfibers. And in terms of filters, it takes a different degree of complexity, because we want to deal with the smaller dimension of these fibers. So, yeah, this is a complexity, added complexity to deal with that. And from my point of view, and that's why we are doing that, we think that in industrial laundries, treating with the whole drainage of the facility is better than put some solutions in different in isolated machines. I don't know if, but in the domestic side, maybe the best solution is to install filters in each machine, because I don't know how can we deal with fibers, but also the most of the particles or the microplastic particles that are cylindrical shape with the same technology.
Yeah. So you have to tailor the solution based on the dimensions and the shapes of the fibers, basically.
Yeah, but for example, if we want to create a filter for general microplastics, maybe we are comfortable with 50 microns as mesh size, for example. But for example, the particles in this study has a diameter of 24. So it is not going to catch these particles. So that's why we think it is a big problem, and we should create or generate a technology intended to treat with this particle with this type of particles.
Okay.
And that's what we are doing.
Yes. Okay. Thank you for your presentation. I think it's very honest for your company, the company who makes who gives the subvention to your PhD to investigate that. I have two small questions now. You say at the end of the presentation as an assumption that 90% will remain in the wastewater treatment plant, no? And I'm not sure I can believe it, but I guess you have some data about that. Maybe you can comment. And another thing, I guess also that when you designed the experiment, you said, if I'm not wrong, that everything was done at 40 degrees, no? So my question is that if you wash at, let's say, 60 degrees or higher temperature, the amount of microplastic would be the same. Did you study the influence of temperature washing on the release of microplastic?
No, we did not study the influence of temperature on microplastic release. I suppose that with higher temperatures, the degradation of textiles is bigger, is higher, but I haven't studied that. And the second question,
about the fact that 90% of the will remain in the wastewater plant.
Yeah, there are a lot of studies that said that 90% of the microplastics remains in the sludge of the secondary treatments on the wastewater treatment plants. I know that with this sludge, then they go to crop fields, and they don't disappear, but it is just to give a number that means comfortable to everybody. And there are a lot of studies, I checked again a few days ago, and 90% is an average.
Okay, thank you.
Okay, so thanks again, Manuel, for the presentation. So the next speaker will be Isabel Marín from University of Algarve, that will present on biodegradación de microplásticos en lodos de depuradora sometido a condiciones de compostaje.
Thank you. Hello, good afternoon, everyone. So I'm Isabel Marín, and I work at the Centro de Ciencias de Mar do Algarve in Faro, Portugal. And I'm going to present some results about a study we performed on microplastic degradation under composting conditions. So all of us know that plastics are part of our daily lives, and that plastic production has increased exponentially in the last decades. But something that I always like to start telling in every presentation is that, to me, one of the roots of the problem is that plastics are designed to be durable, to be resistant, and instead, about 50% of plastics that are produced annually are aimed to short-lived products. That means products that are acquired and then they are discarded in less than 1 year. So in these lines, Geiger and collaborators published this study showing that of all plastics ever produced until the year 2015, about 60% of them have ended up in the, can you hear me? Oh, sorry. About 60% of them have ended up in the natural environment. So as long as plastic demand has increased exponentially in the last years, so has plastic waste in the environment. And what happens when plastics enter the environment, this is just an example for the marine or a coastal environment, but it's similar in every environment. They are exposed to, plastics are exposed to abiotic and biotic factors, and we know that they take a lot to degrade, but instead they break down into smaller plastic pieces, and when they reach a size below 5 millimeters, they are normally called microplastics. So continuing a bit to the previous presentation and entering into my research topic. So wastewater treatment plants are known to be a source of microplastics to the freshwater ecosystem, as said by the previous speaker. And I also have this data that about between 70 and up to 99% of all microplastics that enter into the wastewater treatment plants are finally removed across the water line. But what happens is, as the previous speaker said, they are not really removed, they are not eliminated. They normally settle down in the sludge, in the solid phase, that is called the sewage sludge, and very high concentrations of microplastics compared to, for example, soils or sediments are normally found in these type of samples. So according to, in the scope of a circular economy, it has been encouraged that sewage sludge is recycled as fertilizer in agricultural soils. And in this sense, in Europe, around 10 million tons of sewage sludge are produced yearly. And of this amount, about 50% of sewage sludge is applied to agricultural soils. Also, although the amount varies quite highly across countries. For example, in Portugal, the place where this study was performed is around 10%, whereas here in Spain is around 72%. And well, the sludge normally suffers some process before land application, but really there is only the pathogens or metal concentrations are taken into account before the applications to soil. So there is no legislation regarding other emergent pollutants such as microplastics. So the objectives of our study were mostly to assess at which extent are conventional or compostable microplastics degraded under composting conditions that we simulated in the laboratory, and evaluate how these microplastics may affect sludge properties under these conditions that I will explain now. So composting conditions can also vary, but there are mostly two types of composting, the home composting and industrial composting. Industrial composting is, these are the two main requirements, that temperatures should be between 50 and 70 degrees, and that the composting process should last at least 6 weeks. And then there are other, apart from temperature, there is also important the moisture content of the sample, aeration, etc. And normally across the composting process, there are like different stages when there is a maximum temperature that it is reached, and then the temperature decreases, and other conditions also change, such as the bacterial or microbial community that can be present during the process. So now, what we did is we used two types of plastic polymers for this experiment. And according to this classification of plastics by European Bioplastics, we used a PET bottle as a representative of a conventional plastic, petroleum-based, the typical plastic we are used. And then there are plastics that are considered bio-based, and others that are bio-based and biodegradable, or both of them. And for this, we used a compostable plastic bag labeled as compostable, But then when we analyze it chemically, this plastic bag, to be sure about its composition, we found the analysis by Fourier transforming infrared microscopy, or micro-FTIR, as I will refer it from now on. It revealed that the composition was actually polyethylene, low-density polyethylene. So in principle, there should not be labeled as compostable, but still we performed the experiment. I will call it compostable polyethylene from now on for the purpose of this presentation. And then we recover sewage sludge from a wastewater treatment plant located in southern Portugal that counted with an aerobic granular system as a secondary or biological treatment. And then what we did is we mixed some amount of this sludge with dry leaves that were used as bulking agent, basically to provide aeration in the mixture. And then we divided this mixture across 33 flasks, glass flasks, in which one of them were considered as the positive control, where we only had like the bacterial community initially present in the sludge. Then we added, in two of the treatments, we added either 40 microplastic particles of this compostable polyethylene or PET. And then there were two extra treatments in which we added one of those polymers, and also we inoculated those samples with a bacterial inoculum of the genus Bacillus that had been found to show potential to degrade PET in a previous experiment. This is just the general scheme, and samples were performed all the treatments were carried out in triplicates, and we conducted the experiment at 50 degrees during a period of 60 days. And we monitor a series of variables. I'm not going to enter into detail into the methodology because it's quite a standard procedure. So we analyze it like properties more related to the sludge itself, such as organic matter, humidity, the carbon-nitrogen content, the pH, and the bacterial community. And then we also assessed if the properties of the plastics chemically by micro-FTIR or physically by scanning electron microscopy to see if there are any signs of biodegradation of these polymers across the experiment. So responding to the first question, to which extent are conventional and compostable microplastics degraded under composting conditions, we performed these two types of analysis at the beginning of the experiment, after 30 days and 60 days, as I already said. And micro-FTIR, so this is a typical spectrum of low-density polyethylene. In this case, I am comparing the compostable polyethylene in the sludge and the compostable polyethylene in the sludge with the amended with Bacillus, and then with control particles that were not exposed to the sludge. This is really just an example, but we took several measurements across the two sampling times and in different particles. And just summarizing the results, what we found in the particles that had been exposed to microbial activity, let's say, especially so when they had been amended with Bacillus, they showed more these peaks, these absorbent peaks, changed across time, showing higher intensity in some cases that revealed some oxidation, or we could call biofragmentation of the polymers. And then the same was performed comparing the different PET treatments. And in this case, we found changes mostly across this part of the spectrum that is called the fingerprint region. And what we found, especially in the samples amended, we found higher peaks, higher absorbance in the PET treatment amended with the inoculum, as compared to the PET without the inoculum and the negative control particles. Meaning, and these samples, this fingerprint region mostly refer to changes in the benzene group of the PET. Then scanning electron microscopy revealed certain physical features. For example, in the case of the compostable polyethylene plastic bag, we observe the presence of some fractures or holes when they had been exposed to bacteria, whereas the negative control showed a smooth surface instead. And also, we found some scattered bacteria, even though these samples had been quite clean after the experiment and before the analysis. They still showed the presence of bacteria, scattered bacteria, or a proper microbial biofilm that is normally indicative of the first step of biodegradation, let's say. And similar in the case of the PET treatment, like particles not exposed to bacteria showed a smooth surface, whereas those exposed to the sludge, and particularly when amended with bacillus, showed a biofilm formation around them. So to summarize these results, the compostable polyethylene, and especially bio-augmented with bacteria, showed chemical signs that were indicative of some biofragmentation. And biofilm formation was observed in all the particles, and even the presence of holes and fractures in the case of the compostable polyethylene bag, but not in the PET treatment in this case. Regarding to the parameters that affect the composting process, we measured the pH and did not find any significant differences across treatment, but we also measured the content in organic matter, the carbon-nitrogen ratio, and bacterial community. And what we found, in the case of the organic matter content, it somehow even increased in some of the treatments, but we found that in the compostable polyethylene treatment, when amended with bacillus, the organic matter content was reduced. So the process was more effective, we will say. And similar in the case of the carbon-nitrogen ratio, in this case we found differences across the two PET treatments. Once they were the treatment amended with the genus Bacillus, it showed more a lower carbon-nitrogen ratio, and therefore the process of compost was more effective in this case, we will say. Regarding the bacterial community across the samples, the different treatments and sampling times, mostly we found a different community, especially related to the two sampling times. So the community changed mostly because of the time, not because of the treatment. But in any case, we found that the compostable polyethylene samples with or without the Bacillus inoculum and the PET samples without the inoculum clustered together. So the bacterial community was more similar in those samples as compared to the positive control and the PET samples without the inoculum. Just to summarize these results, the organic matter remineralization was favored in the treatment of the compostable polyethylene bag with the inoculum, and a lower carbon-nitrogen ratio was found in the PET treatment when the inoculum was added. And regarding the changes in the bacterial community I just mentioned, there were two types of treatments. And while we expected more abundance of the genus Bacillus in the samples amended with Bacillus, we didn't really find differences for this group, but we found differences in the group Trupera, that is a genus with this only species that, as far as I know, it has not been really studied much, but eventually it could be the one that foster one of the species that foster some of the changes we observed. So the main conclusions of the study is that no complete degradation was observed of any of the polymers, even the compostable, but the labeled compostable plastic bag showed more signs of biodeterioration as assessed by electronic microscopy. Then both the compostable polyethylene and the PET treatment showed changes in the functional groups of the polymers, especially so when inoculated with this genus of bacteria. Microplastics with bacterial inoculum favor organic remineralization or a decrease in the carbon-nitrogen ratio. And the bacterial community was different across treatments, and more particularly, there was a cluster of samples that seems to enhance more the biodeterioration or biofragmentation of the polymers that had more abundance of this genus of bacteria, that is Trupera. I just have to acknowledge the funding sources, and thank you all for listening.
Thank you, Isabel, for your nice presentation. Is there any question? This is the last talk, so.
Hi,
Hi, thanks for the very interesting presentation. I was wondering what are the criteria to lab polymer as compostable, if then it's, as you say, like it was labeled as compostable, but then you find it's polyethylene, so...
Yes, yeah, I think, well, there are some... I think the regulation is not very clear, but indeed there should be a polymer that it's labeled as compostable. It should like degrade completely under some, in natural conditions in a period, I think like about 100 days or so, and in specific treatment like industrial composting in less than 60 days. So, and our experiment was 60 days, so really this label was not really legal, I would even say. But,
yeah. Thank you.
More questions? No? Okay, thank you very much, Isabel.
Thank you.
So we can conclude the day. I don't know if Ethel wants to say something. Otherwise, yeah, we see you tomorrow at 9 in the morning. We will start with the keynote speaker of Luis Cabedo, and then we will continue with the talks and the poster session during the breakfast. Thank you very much.
Hola, buenos días a todos y bueno, bienvenidos a esta segunda parte de las jornadas científicas. Ayer por la tarde tuvimos ya unas primeras presentaciones y hoy completaremos el resto. La jornada de hoy empezaremos con una conferencia plenaria, después tendremos una sesión de 4 presentaciones y a continuación pararemos para tomar café y tendremos 1 hora de tiempo para sesión de pósters y después de la sesión de pósters pues volveremos para otras 7 presentaciones orales, ¿de acuerdo? Bueno, y sin más doy paso a la presentación plenaria de hoy, que nos la va a presentar Luis Cabedo. Tenemos el honor de contar aquí con su presencia. Él es catedrático de Ciencia de los Materiales en la Universitat Jaume I y director de la Cátedra de Plásticos Sostenibles de la misma universidad. Es miembro del Grupo de Investigación en Polímeros y Materiales Avanzados y coordina por la Universitat Jaume I la unidad asociada de investigación con el CSIC en tecnología de polímeros. Su línea de investigación inicial se centra en el diseño y procesado de materiales poliméricos, en la que lleva casi 20 años dedicado al estudio de materiales de alta barrera, nanocompuestos y polímeros biodegradables para aplicaciones de envasado alimentario sostenible. Asimismo, de manera más reciente está liderando una segunda línea de investigación dirigida al estudio de la biodegradación de los materiales plásticos. Ha participado y coordinado en más de 30 proyectos, tanto a nivel europeo como nacionales, y luego también es cofundador de 3 spin-off. Él nos va a hablar sobre los bioplásticos y bueno, nos va a explicar mejor qué son los bioplásticos, cuáles son sus ventajas y sus inconvenientes, ya que bueno, se habla mucho de estos materiales como alternativas y un poco que sepamos, digamos realmente, bueno, como él comenta en el título de su ponencia, si son aliados o enemigos. Así que Luis, cuando quieras.
Perfecto. Pues buenos días. En primer lugar, quisiera dar las gracias a ETH y a la organización de este congreso por darme la oportunidad de venir aquí a contaros un tema que a mí me resulta apasionante y que espero que sea también de vuestro interés y que responda a las dudas que podáis tener en cuanto a todo este totum revolutum que ha salido o que está hoy en día con el tema de los bioplásticos, para ver si somos capaces de aterrizar un poco qué es un bioplástico, cuáles son sus ventajas, cuándo es útil, cuándo no lo es y si realmente tiene interés o no para el medio ambiente. Lo primero que tendríamos que preguntarnos es si si para empezar los plásticos son buenos o malos. Luego ya entramos en detalles si los bioplásticos son buenos o malos, ¿no? Entonces, bueno, los plásticos son materiales que presentan muchísimas ventajas desde un punto de vista tecnológico, muchísimas. O sea, no es casualidad que los plásticos hayan ido y estén sustituyendo paulatinamente a otros materiales que estaban antes prestando estos servicios y cubriendo de manera mucho más eficiente que los anteriores las expectativas que esperaba de ellos, ¿no? Entonces, ¿por qué? En primer lugar, son materiales de baja densidad, lo cual los hace ligeros, fáciles de transportar y es eficientes en el punto de la parte logística. En segundo lugar, nos da transparencia. Transparencia es una propiedad que no es muy común en la naturaleza. Solo hay que ir por el campo para ver que no hay muchas cosas transparentes. Y dentro de los materiales transparentes, pues la mayoría son frágiles y nos quedan los plásticos y que es algo que sea tenaz, flexible y transparente, ¿no? También tienen una versatilidad en cuanto a propiedades mecánicas y a comportamiento mecánico que es único. No hay otros materiales que tengan la capacidad de darnos esa versatilidad mecánica. También en cuanto a la capacidad de producir diferentes formatos. Aquí, por ejemplo, pongo 5 imágenes de un mismo polímero. Es un PVC, un cloruro de polivinilo. Puede ser un elastomérico para hacer un patito de goma, puede ser una tubería rígido, puede ser, por ejemplo, en el flan de huevo, lógicamente el envase de abajo es metálico, de aluminio, pero la capa que sella es de PVC. Las cortinas de ducha, las mangueras, hay infinidad, una miríada de productos y de requerimientos técnicos que se pueden cubrir con un mismo material. Aparte es un material inerte e higiénico. Los procesos de fabricación de los plásticos dan como resultado un material que ya es inerte e higiénico desde el principio, lo cual lo hace fabuloso para sectores como la sanidad o el envasado alimentario. Y por otro lado también para tener una durabilidad extraordinaria en el medio ambiente, que en algunas aplicaciones es una propiedad muy buscada. También es muy sencillo de procesar. Desde un punto de vista técnico es fácil, es muy sencillo, permite que lo hagan empresas muy pequeñas. Una empresa pequeña, un taller, se compra una inyectora de plástico y inyecta plástico, ya puede fabricar pieza. Es muy sencillo. Y aparte es muy barato y aparte es muy sostenible desde un punto de vista de energía invertida. Es decir, no tiene nada que ver la energía que se requiere para fabricar una botella de plástico con una botella de vidrio. Hablamos de órdenes de magnitud de diferencia, de la fabricación de la botella en sí mismo. Y también es un material muy barato. Esto tiene una parte buena, que es que hace accesible productos a mucha más gente, para que todo el mundo podamos disfrutar de las mismas calidad de vida, por así decirlo, pero también tiene una parte negativa que hace que entremos en un paradigma lineal de economía de usar y tirar. Como no tiene valor, como el plástico es muy barato, como vale €1 el kilo, pues claro, ¿qué sentido tiene recuperar sus residuos? Si valen menos de €1 el kilo, compro uno nuevo y a funcionar. Por tanto, no cabe duda que hay muchísimo bueno, ¿no?, en cuanto a los plásticos a la hora de fabricar cosas. También en la cadena de valor de la alimentación, que es una cadena en la cual se invierte aproximadamente el 45% o el 50% de los plásticos, desde la agricultura hasta el envasado alimentario. Los plásticos han sido una revolución dentro de la cadena de valor del alimento, porque permite un montón de cosas interesantes. Primero, desde la parte de cultivar de manera más eficiente, con lo cual hay menos pérdidas, con lo cual se aprovecha más el terreno, hasta después, sobre todo, en la parte del envasado alimentario. El envasado alimentario ha sido una revolución en cuanto a la seguridad alimentaria. Solo hay que viajar a países donde la comida no se encuentra envasada en sus cadenas de logísticas y de alimentación para ver qué pasa con la seguridad alimentaria en esos sitios, ¿no? Entonces, sin lugar a dudas, es un elemento positivo para la seguridad alimentaria, para personas que tengan problemas, para contaminaciones cruzadas, para manipulación, para conservación, para todo. También, desde un punto de vista medioambiental, para disminuir la huella medioambiental asociada a la cadena alimentaria. Y diréis, ¿cómo es posible si el plástico contamina? Bueno, el plástico contamina. Aquí hay un ejemplo, que pongo siempre este ejemplo porque me parece paradigmático, ¿no? El plástico que envuelve el pepino. Todo el mundo, ¿es que el pepino ya tiene su piel? Sí, el pepino tiene su piel. Una piel que le aguanta 5 días hasta que empieza a ponerse pocho. Si le pones el plástico, te aguanta 15. Con lo cual reduces el desperdicio alimentario. El desperdicio alimentario, en una cadena logística, esos 10 días de incremento, lo que hace es disminuirte casi en 15 o 20%, ¿vale?, la cantidad de rechazo de fruta que tiras sin consumir, que estamos hablando de más de un tercio de lo que tiramos sin consumir. El impacto medioambiental asociado a fabricar un pepino respecto al de fabricar su piel de plástico no es comparable, es mucho menor. Y luego también están los envases en los plásticos en la cadena alimentaria nueva en todo lo que llamaríamos la cuarta gama, ¿no? Los envases, aquí he puesto algunos ejemplos, ¿no? Ensaladas y frutas. Claro, está levantando mucha polémica en cuanto a la cantidad de plástico para comerte una ensalada. No, es que no es necesario. Bueno, es cierto que no es necesario. Ahora, los modelos actuales de consumo están haciendo que, gracias a esto, se esté disparando el consumo de ensaladas, ¿vale? En sustitución del fast food, de la comida rápida. Entonces, desde un punto de vista epidemiológico, desde un punto de vista de la sociedad, a lo mejor paga la pena, ¿no? Lo que pueda tener de malo ese plástico en cambiar los hábitos de consumo. Nosotros tenemos delante mismo de la universidad, en la que llevo pues prácticamente 30 años allí en esa universidad, delante hay un Mercadona, ¿vale? Y yo he visto cómo ha ido cambiando a lo largo de 20 años los hábitos de consumo de los que íbamos a comprar al Mercadona para comer y los estudiantes. No tiene nada que ver. Ahora, 1 de cada 2 estudiantes come una ensalada. Antes comía una hamburguesa. ¿Vale? Luego, ahí tiene esa parte positiva. Y es el plástico quien lo hace posible. Porque con otro tipo de envases esto no es viable. Por tanto, ¿es una opción medioambiental? Pues habría que verlo. Como todo en esta vida hay que echar números. ¿Dónde está realmente el problema de los plásticos? Si alguien le pregunta, ¿dónde está el problema? Pues el problema todo el mundo lo identificaríamos no en su uso, sino en 2 apartados. En primero, su origen petroquímico y segundo, sus residuos. Vamos a hablar primero del origen. Si analizamos la cantidad de petróleo que se emplea para fabricar plásticos, estaremos en una horquilla entre el 4 y el 6%. ¿Vale? El otro 94-96% no se emplea para fabricar plásticos. Por tanto, el motor de la industria petroquímica no es el plástico. La mayor parte del petróleo no se gasta para plástico, se gasta para otras cosas. Es un share muy pequeño que se dedica a este sector. Por tanto, no está ahí el problema del petróleo, está en otro sitio. Además, si esos plásticos finalmente los recogemos y los incineramos de manera correcta para obtención de energía en sustitución, por ejemplo, de combustibles fósiles, que es como se gasta actualmente en gran parte de la generación de electricidad y mucho calor industrial, pues entonces lo que estamos haciendo es simplemente el combustible que nosotros quemaríamos antes gastarlo como plástico. Luego, no es una mala opción. Habla de que hay estudios que dicen que disminuiremos hasta un 80% la cantidad de plásticos que va al vertedero, y en España, por ejemplo, ya se practica con la industria cementera y prácticamente el 40% del combustible que gasta la industria cementera viene de plástico, ¿vale? En lugar de gastar gas. Luego, a lo mejor no está mala opción esta. Bueno, pero aún así vamos a intentar hacerlos de origen renovable. Prácticamente cualquier polímero que podamos pensar en la actualidad, prácticamente cualquier polímero, actualmente, de los decenas de miles que hay diferentes, se pueden obtener por rutas sintéticas a partir de precursores orgánicos o renovables, o de las plantas, animales, de precursores no petroquímicos. Ahora bien, ¿sale a cuenta? ¿Sale a cuenta económicamente? Económicamente no. La petroquímica lleva 100 años optimizando todos los procesos catalíticos. Es una máquina perfecta. Si me permitís la analogía, el petróleo es a la química lo que el cerdo es a la carnicería, hasta los andares. No hay un gramo de petróleo que no se aproveche. Está optimizadísimo hace 100 años y tiene muchísimo dinero y han invertido mucho. Esto no pasa con lo que viene de plantas o vegetales. Todavía no. Ya vendrá. Pero además hacemos un ensayo, si hacemos una medida de impacto medioambiental y calculamos, uno de los principales medidores que se gastan, que luego a lo mejor vemos que no es el más adecuado, pero es la huella de CO2. Entonces, la huella de CO2 de un plástico renovable, a día de hoy, incluso proveniendo de residuos, ¿vale? A día de hoy, dudablemente, es muy dudable que llegue a mejorar la de un plástico normal. En manera general, si vamos a un plástico como el polietileno, no tiene nada que ver. Es mucho, contamina muchísimo menos, emite mucho menos CO2 a la atmósfera fabricar 1 kilo de polietileno normal que 1 kilo de polietileno biobasado. ¿Esto qué estoy diciendo con ello? ¿Dejemos de estudiar biobasados? En absoluto. No es en absoluto, y no es mi idea tampoco transmitir aquí que sacar petróleo debajo del suelo sea una buena idea. Sacar más carbono a la superficie de la Tierra es una mala idea. Lo mires como lo mires. ¿Vale? Por tanto, vayamos a intentar, aunque consumamos más energía, vayamos a intentar buscar rutas sintéticas adecuadas e investigar para conseguir que las fuentes renovables sean competitivas. Por tanto, yo creo que el problema del plástico no está en su uso, hemos dicho que es fabuloso, no está en su origen, claramente están sus residuos. ¿Vale? A mi juicio, el problema principal de los plásticos está hoy en día, medioambientalmente hablando, en sus residuos. Claro, todo el mundo somos conscientes, y en este foro además más todavía, de la problemática medioambiental asociada a los materiales plásticos en la actualidad. Son por sus características, interactúan a nivel íntimo con la naturaleza, tienen capacidad de viajar por sus densidades y sus formas de baja espesor y alta relación de aspecto, viajan de manera muy sencilla, tienen densidades cercanas a la del agua, lo que permite flotar, cosa que no le pasa ni a las cerámicas ni a los plásticos ni a los metales. Claro, todo esto además tiene colorcitos, es brillante, es una cosa nueva, con lo cual no hay... Claro, llevan escasamente 50 años de manera masiva entre nosotros. El resto de especies que no somos nosotros no han evolucionado aún para reconocerlos. Entonces la mayor parte de ellos no lo conocen. Piensa que es alimento. Ante ese paradigma, claro, si los residuos de los plásticos es un problema, hagamos bioplásticos, ¿no? Entonces, ahí aparece la palabra bioplástico. ¿Y qué es esto de bioplástico? Pues claramente todo el mundo cuando habla de bioplástico habla de un plástico menos contaminante, más verde, ¿sí? Pero esto no está aterrizado. Le preguntas a uno qué es un bioplástico y normalmente no está aterrizado. Algo que contamina menos, sí, pero ¿qué es? Pues alguien piensa que es orgánico, otros piensan que es renovable, otro piensa que si es muy reciclable también tiene que ser un bioplástico, porque gasta mucho reciclable, otro que si se desintegra, pero otro que se mineraliza, otro que si se puede asimilar a materia orgánica, otro que... Quiero decir, hay todo un revolutum aquí de conceptos que orbitan en torno al concepto o a la palabra bioplástico que hace que hoy en día esté prácticamente carente de sentido y se esté gastando de manera torticera y malintencionada por parte de la comunicación e incluso del ámbito científico. En algunas ocasiones hasta yo el primero, ¿no? Un bioplástico en lugar de decir un plástico cuando es un plástico. Entonces, aparecen situaciones como estas. Pues una conocida empresa de leche que ahora ha cambiado y ha puesto en sus envases: yo soy un tapón de caña de azúcar. No, señor, no eres un tapón de caña de azúcar, eres un tapón de polietileno de alta densidad, ¿vale? Otra cosa es que tu carbono venga de la caña de azúcar. Bueno, ni siquiera, quiero decir, tus moléculas no vienen. Los promotores con los cuales químicamente se han obtenido tus moléculas vienen de la caña de azúcar y no del petróleo. De ahí a que tú seas una caña de azúcar, creo que dista muchísimo. O no soy un vaso de plástico, claro que eres un vaso de plástico, de un PLA, ¿vale? 100% compostable y 100% biodegradable. ¿Biodegradable cómo? ¿Vale? ¿Compostable cómo? Vengo de plantas. Bueno, vengo de plantas, yo qué sé, todo viene, el petróleo también viene de plantas, es cuestión de darle tiempo y al final, ¿no? También son plantas. Entonces, vamos a ver exactamente de qué manera gestionamos esto de una manera que sea útil y que no sirva para hacer un greenwashing, ¿vale? Que no sirvan para que la industria del plástico continúe haciendo lo mismo que venía haciendo, pero con mínimos cambios que afectan, además, están consiguiendo que afecte poco desde un punto de vista económico, porque el polietileno biobasado está ya siendo casi competitivo con el polietileno normal en términos de precio, con lo cual, nada, ya está, estupendo. Lo solucionan fácilmente y gastan la palabra bioplástico para una comunicación que resta a su favor y que realmente no avanza o no permite avanzar, a mi juicio, en el camino adecuado. ¿Qué son bioplásticos? Ayer la última charla de la tarde ya introdujo este concepto. Entonces, bioplásticos, al final, realmente hay dos cosas que son bioplásticos. Son plásticos que vienen de origen renovable y dos, plásticos cuyo final de vida permite la biodegradación, permite que los bichos se lo coman como materia orgánica, ¿vale? Como fuente alimentaria. Esto es lo que es un bioplástico. Esto establece un eje de coordenadas cartesiano en el cual tenemos que 3 sectores de los 4 son bioplásticos. Tenemos que solo no son bioplásticos aquellos plásticos que vienen del petróleo y no son biodegradables. Son el 90%, pero aún así estamos hablando de que bioplástico se puede encontrar aquí, aquí y aquí, con lo cual dice poco esa palabra en estos momentos en cuanto a su gestión, porque podemos estar hablando de un plástico que venga del petróleo pero que sea biodegradable, o podemos hablar de un plástico que sea no sea biodegradable pero que venga del petróleo. Total, el tema de los residuos, en este sentido, yo creo que es donde hay que poner el foco. No tanto en los bioplásticos por origen renovable, que es importante marcar esa diferencia, porque hemos de conseguir que la gente lo vea de manera positiva, que las industrias lo vean de manera positiva, quieran invertir en esa ruta, si quieran consumir de manera preferente eso para dejar de sacar petróleo, aunque sea solo un 4%, dejar de sacar petróleo debajo de tierra, pero en realidad donde tenemos que enfocarnos es en los residuos, ¿vale? El problema no lo está generando el petróleo. El petróleo saldría por otro lado, o es mínimo lo que se saca. El problema son sus residuos, que hasta ahora se han considerado por la legislación y por el común de los mortales como inertes, y la gente que llevamos tiempo trabajando en esto sabemos que no son inertes, y aquí en el IDAEA tenéis mucha idea de esto, más que yo. Entonces habría que centrar el problema de los plásticos realmente en el problema de los residuos de los plásticos. Entonces, si los problemas son los residuos, pues hay una fácil solución. Hagamos que los plásticos sean biodegradables y por lo tanto se acabaría el residuo, ¿no? Si al final el plástico desaparece de manera natural, es como si lo hacemos de madera, como si lo hacemos de cartón, como si lo hacemos de piel, de cuero, ¿no? De algodón. En principio eso no sería un problema. Si al final acaba biodegradándose, acabaría integrándose dentro del ciclo de la materia orgánica y no habría problema. Por desgracia esto no es tan sencillo. Primero vamos a ver qué es esto de la biodegradación. Entonces, la biodegradación es un concepto que la definición te dice únicamente que es un polímero, es decir, una macromolécula, que es susceptible de degradarse por acción biológica disminuyendo su masa molecular. Esa es la degradación. Claro, con esa definición entra todo. Todo acaba degradándose. Es cuestión de tiempo. No es lo mismo que se degrade en una semana que en un mes que en 150.000 años. ¿Vale? Entonces hay que empezar a afinar cuando hablamos de plásticos de esto, metiendo una parte de un marco de tiempo razonable. ¿Cuál es la buena noticia? Pues como decía, todo es biodegradable y la naturaleza es experta, porque precisamente es lo que hace que haya naturaleza, que es que se adapta a las condiciones cambiantes, ¿no? Del entorno del planeta, va cambiándose. Entonces, claro, la naturaleza está reaccionando y reacciona de manera bastante rápida. Ya se encuentran y ya existen bacterias que han mutado para desarrollar procesos enzimáticos capaces de hidrolizar, por ejemplo, el PET. La más famosa es la Idonella sakayensis, que es una bacteria que se ha aislado de un vertedero en Japón donde se tiraba botellas de PET, y claro, es que no hay en la naturaleza fuentes orgánicas tan puras. O sea, en la naturaleza evoluciona para que no se te coman. Entonces, los materiales vegetales, por ejemplo, ha evolucionado con la lignina para que no se la coman los microorganismos. Los plásticos no han evolucionado. Lo que pasa es que lleva muy poco tiempo. Cuando los microorganismos encuentren las rutas adecuadas, cuando se den cuenta que eso es comida, en primer lugar, y a partir de ahí empiezan, que es comida abundante, y empiecen además que interactúen de manera sencilla con ello, que no les mata al tocarlos, y comiencen a notarlo, van a empezar a evolucionar y van a empezar a cambiar. De manera que de aquí 1 millón de años, el problema de los plásticos en la superficie de la Tierra va a estar solucionado. No os preocupéis que no va a haber plástico suelto por ahí, se lo van a comer. ¿Qué pasa entonces? Bueno, pues que no llegamos, ¿vale? Que al ritmo que vamos no llegamos. Hay un estudio por ahí que saca un número muy, muy bonito, no sé cuánto habrá de cierto, pero muy bonito, que dice que para 2050 habrá más masa de plástico en el mar que de peces. O sea, a ese nivel estamos llegando. Entonces es una auténtica salvajada, es una barbaridad. No hay ningún escenario en el cual se prevea una bajada en el consumo y fabricación de plástico, ni uno, ¿vale? No hay tampoco muchos escenarios plausibles que vean que vaya a disminuir la liberación o la gestión, porque al final los residuos es complicado de gestionar, ¿no? Entonces todo eso es complicado. Entonces, ¿qué pasaría si solucionamos todo de material biodegradable? Bueno, por ejemplo, de madera. Pues la madera todo el mundo sabemos que se biodegrada, pero hay madera que tiene 9.000 años, ¿vale? O 500, o 600, o 200, las vigas, los travesaños. ¿Qué quiere decir? Que no todo se biodegrada en todo momento. Papel, lo mismo, el papel es biodegradable, todo el mundo lo sabe, es celulosa. Sin embargo, hay papeles que tienen 2.000 años. ¿Vale? Es decir, la biodegradación no es una cosa ubicua, no es una cosa general, no es una cosa transversal. La biodegradación sucede en determinadas condiciones y tienen que alinearse unas propiedades de los materiales y unas propiedades del entorno. Y si esto no se alinea, no hay biodegradación, hay acumulación. ¿Vale? Entonces, ¿qué pasa con la biodegradación? Vamos a ver de manera muy sencilla. Ayer ya se habló de esto, con lo cual no voy a incidir. La biodegradación consta de 4 etapas. La primera es, los microorganismos colonizan la superficie, generan un biofilm y empiezan a liberar ahí un montón de productos químicos que ellos generan para empezar a comerse lo de abajo. ¿Por qué? Pues porque los microorganismos no tienen boca. Entonces no pueden comer cosas grandes. Necesitan romper lo que haya en cosas pequeñitas para que les pueda permear por su barrera celular. Y estos son enzimas. Entonces hay que degradar. La segunda etapa es la fragmentación y la desintegración. Esta etapa se puede hacer también de manera física. Ayer contaba la compañera de Algarve que había visto un film de polietileno que sufría meteorización, que sufría cambio, desintegración con el tiempo. Claro, esto se conoce de mucho tiempo. Los aditivos OXO llevan ahí un montón de años. O sea, se puede romper un plástico en trozos pequeñitos. Eso no hay ninguna dificultad. No hay nada difícil ahí, es sencillo. El problema está en lo siguiente. El problema está que los trocitos que rompamos lo asimilan las bacterias. Y eso sí que es más complicado, porque la bacteria tiene una membrana que es selectiva. Entonces solo deja pasar lo que es comida. O por lo menos lo que es pequeñito y puede asimilar. Y luego, finalmente, que lo que asimile, porque también puede asimilar productos químicos que son tóxicos o productos químicos que no son comida y acumularlos, sino que además ese carbono tiene que estar en la forma en la cual sus procesos enzimáticos posteriores permitan obtener energía y biodegradarlo, ¿vale? Todo esto ha de pasar para que la biodegradación tenga lugar. Con la materia orgánica natural, esto pasa de manera espontánea, no hace falta planteárnoslo, porque sucede de manera espontánea. Con los plásticos no. Entonces hay que pensar de qué manera analizamos los plásticos para ver en qué escenarios son biodegradables y cómo podemos cuantificar y medir. Y como la naturaleza es sumamente heterogénea, los entornos son sumamente heterogéneos, al final hay que definir una serie de normas y una serie de ensayos que permitan medir y llegar a poder afirmar que tal plástico es biodegradable en tales condiciones, ¿vale? Para saber de qué estamos hablando. Entonces hay una serie de normas, tanto de la STM como de la ISO, como europeas, de todo tipo, todo un plectro de normas que permiten medir la biodegradación a partir de ver cómo se desintegra, de ver cómo cambia el peso, de ver cómo se libera el CO2, hay diferentes herramientas, ¿vale? De todas ellas, en función de todo esto y de esas normas podemos clasificar los polímeros entre biodegradables y no biodegradables. Y ahí me gusta mucho esta imagen, que es un trabajo que hace el Instituto Nova de Alemania sobre bioplásticos, en el cual te muestra las principales familias de polímeros que se consideran biodegradables. Tenemos la celulosa, con menos de un 5% de lignina, porque sabéis que la lignina no pasa, la lignina, que no es ningún problema en la naturaleza, no pasaría los ensayos de biodegradación, según norma, sería no biodegradable, ¿vale? Porque tarda más tiempo de lo que debe, porque precisamente está diseñada por la naturaleza para que no se lo coman los bichos. Las celulosas modificadas, el PBAT, el PBS, el PBSA, la policaprolactona, los polihidroxialcanoatos, el PLA y el almidón. Yo creo que la mayor parte de nosotros conoceremos todos estos materiales. Fijaros, estos son los polímeros biodegradables. Fijaros que cada uno se biodegrada en unas condiciones y en otras no, y que solo tienen un máximo común divisor, o un mínimo común múltiplo, ¿vale? Solo tiene una cosa en común, esta, compostaje industrial. Por tanto, la comunidad científica asume que un polímero es biodegradable y por tanto un bioplástico si lo es en condiciones de compostaje industrial. Repito, industrial, no es natural, es industrial. Entonces, ¿biodegradable es compostable? Bueno, vamos a ver. ¿Qué quiere decir compostaje industrial? Compostaje industrial tiene lugar a 58 grados, cosa que el peor escenario meteorológico no espera que suceda ni en Córdoba en el año 2050, ¿vale? Con lo cual no hablemos de Suecia. No se va a dar esa temperatura en la superficie de la Tierra. Si se da, pues nos extinguiremos. Y aparte, ha de ser compatible con los... Bueno, establece que tiene que desaparecer todo su carbono en 6 meses, transformarse a CO2, en 6 meses, ¿vale? 180 días, expuesto a 58 grados con un inóculo de compost. Claro, si conocéis cuáles son los tratamientos de compostaje actual de la materia orgánica, sabréis que no son 6 meses, que son 28 días. Algunos un poco más, ¿vale? Pero el estándar en España son 28 días. Claro, los primeros 14 a más de 58 llegan a 70 perfectamente, los segundos 14 no te garantiza que puede estar por encima de 45. ¿Vale? De manera que medía 180 días a 58 se parece como un huevo a una castaña a lo que sucede en un proceso de compostaje industrial. ¿Cuál es el resultado de esto? Pues que estas medidas no garantizan siempre, o no garantizan de manera segura, que el plástico que pasa un proceso de compostaje industrial se biodegrade. Por suerte, para no generar aquí más polémica de la necesaria y no causar el pánico, ¿no? La mayor parte de ensayos en plantas reales funcionan mejor de lo que funciona la norma. En primer lugar, porque en la norma es un laboratorio, está controlado a 58 grados, en un compost industrial aquello es la guerra. Es decir, allí hay todos los bichos, las condiciones son de la guerra. O sea, allí está preparado para degradar todo. Entonces va todo mucho más rápido. Las temperaturas son muy superiores, hay calentamientos locales muy fuertes, hay bacterias extremófilas que no priman en un laboratorio en condiciones controladas. Es decir, que pasan un montón de cosas. Hay condiciones anaerobias que también suceden, bueno, hay un montón de cosas. Pero ¿qué pasa cuando acaba un proceso de compostaje y el compost que tiene microplásticos o que tiene plásticos va al campo o se libera en el medio ambiente? Pues en función del plástico que hayamos metido, esos microplásticos se comportarán igual que el plástico inicial. Si es un PLA que no se biodegrada por debajo de su temperatura de transición vítrea de sus 58 grados, pues no se biodegradará y tenemos microplásticos de bioplásticos biodegradables, de PLA, recalcitrantes a temperatura ambiente en entorno marino, por ejemplo. Tan recalcitrantes como un polipropileno. Exactamente igual. ¿Vale? Hay un estudio que salió hace poco en el cual habían visto algunos indicios de que podía haber pues no lo sé, a lo mejor algún indicio alguien ha visto que... Pero yo he medido un montón de veces el PLA en medio marino y esto no se biodegrada. Está publicadísimo, todo el mundo lo sabe. Lo mismo pasa con el PBS, lo mismo pasa con otros polímeros. Entonces, hay que ir con mucho cuidado. Un polímero compostable que no se gestiona de manera adecuada en un compost, estamos haciendo un pan con unas tortas. Estamos generando, en lugar de plásticos, macroplásticos, que podían ser gestionables, por ejemplo, por incineración, o a una mala, en vertedero. En vertedero, por lo menos, ahí, mira, sumar no suman, pero restar tampoco restan. Los acumulamos ahí y ya los que vengan nuestros hijos, nuestros nietos, ya verán qué hacen con eso. ¿De acuerdo? Pero generar microplásticos dentro del suelo, en un producto circular como es el compost, bueno, positivo para el medio ambiente como es el compost, es una cosa realmente complicada. Complicada. Entonces, ¿cuáles son los principales challenges, ¿no? que tienen los bioplásticos? ¿Cuáles son los principales retos a los que se enfrentan? ¿Por qué no podemos directamente sustituir los plásticos por bioplásticos por biodegradables inmediatamente y ya está? Bueno, el primero de ellos es porque no se comportan igual. ¿Vale? Los polímeros biodegradables hay, ya habéis visto, 6 familias. Los polímeros no biodegradables hay 25.000 familias. ¿Vale? Y aparte de eso, si empiezas a modificar la estructura química de los polímeros biodegradables, llegará un momento en el cual dejarán de ser compatibles con las enzimas. Si las vas haciendo tan diferentes a las que las enzimas pueden hacer, dejarán de funcionar. Con lo cual, si tú empiezas a modificar la arquitectura molecular de un polímero biodegradable, acabará no siendo biodegradable. Es decir, las herramientas que hay son limitadas. Se está trabajando, hay mucha gente que estamos trabajando en eso, yo me dedico a esto, en ver de qué manera se puede conseguir, pero la cosa es que no tiene una performance adecuada porque no tiene las estructuras moleculares adecuadas. Lo que quiere decir que si tú quieres hacer un material que sea, por ejemplo, para bolsas de vacío, que es una utilidad que se gasta muchísimo, que tenga barrera, que tenga resistente a la punción, que tenga resistencia al rasgado, que se pueda termosellar, pues eso no existe en polímero. No hay nada en la naturaleza que sea biodegradable que pueda o que darte esas propiedades per se. ¿Vale? No se puede, no existe. Puedes modificarlo a partir de la tecnología de plásticos, generar diferentes grados comerciales e ir mejorando el comportamiento a partir sobre todo de aditivos y de cambios y de mezclas. Claro, el problema es que la industria potente no está centrada en esto porque no lo fabrican ellos. Los procesos, la mayor parte de los bioplásticos no son rutas petroquímicas, sino que vienen de fermentación, procesos fermentativos, aunque hay una parte de síntesis química, no hay un control claro sobre la materia prima, pierden un bocado del pastel muy grande. Entonces no hay interés poco. Entonces no hay mucho grado, no hay mucha empresa plástica potente ofreciendo grados, porque tú quieres un polietileno, hacer algo de polietileno, cualquier aplicación, la que quieras, una cosa rarísima que se te ocurra. Tú llamas a SABIC o a Repsol y dices, mira, quiero hacer esto, y además que me aguante ultravioleta, y además que tenga color verde, y además que tenga no sé cuántos, y que tenga antiestática y que tenga touch. No te preocupes, hay un grado. Tienes un grado que te va a hacer eso. No te preocupes, ahí lo tienes. ¿Pides eso a un PLA? No, hay 10 PLAs y como mucho, comerciales, 5 PHAs comerciales, 2 PBSAs, y es lo que hay. No hay grado de inyección y extrusión, el PLA algo hay, pero no hay. Entonces, claro, no hay grados. Esto hace que tengamos que desarrollar y meter una cantidad ingente de aditivos para que esto funcione. Y de esto sí que sabéis mucho. Por ejemplo, el grupo que lo conozco un poco, trabaja, hay que meter una cantidad ingente de aditivos, muchos más de los que tendríamos que meter a lo mejor a un plástico normal, porque su estructura molecular no te permite las propiedades, no te permite el entanglement, el enmarañamiento de las cadenas poliméricas, no te lo permite, no te permite un entrecruzamiento parcial, no te lo permite, porque deja de ser biodegradable. Entonces, a base de aditivos lo conseguimos. Y esto, claro, tiene su problema. Coste. Uno de los beneficios del plástico es que es muy barato. Uno de los problemas del plástico es que es muy barato. Entonces es muy difícil venderle a nadie que está pagando €1 el kilo, €1 el kilo por un material que tiene una densidad de 1, es decir, €1 el litro de material, es muy difícil. No, ahora págame 8. Te mira, no. Oblígame a pagártelo, si no, no te lo voy a pagar. Entonces, también hay una parte de comunicación y aceptación. Hay que deshacer esta maraña de desinformación. Desinformación que nace de las bien intencionadas, en muchas ocasiones, bien intencionadas, pero que disparan con los que promueven un mensaje del plástico mate y demás, lo hacen con muy buenas intenciones, pero disparan con cartucho de perdigones, ¿vale? Disparan a todo, no son quirúrgicos. Que el plástico no mata. Mata algunos residuos, algunos plásticos, algunas especies, pero el plástico por sí, o sea, la solución al plástico no es quitar el plástico y hacerlo de aluminio, porque vas a hacer un pan con unas tortas, porque para hacer 1 kilo de aluminio, la energía y lo que contaminas no tiene nada que ver con lo que cuesta hacer 1 kilo de plástico, nada que ver. Y tiene mucho más efecto en aguas, tiene mucho más efecto en un montón de cosas, entonces no es tan sencillo. Hay que desleír la paja del grano y el sector académico tenemos que trabajar en ello. Las etiquetas tampoco ayudan. Ayer veíamos uno de compostable, biodegradable, eco. Esto hay que regularlo. La regulación, los estándares van como van y la transposición de estos estándares a la legislación europea tiene una serie de tramoyas detrás que son muy complicadas de entender y que a veces te sorprenden y cuando entiendes lo que pasa es muy complicado. Y luego a nivel nacional cada uno hace lo que quiere. Esto hay que armonizarlo. ¿Lo armonizamos o esto no hay forma de poder avanzar? Y luego hay que aceptarlo. Hay que hacer que la gente pague más dinero por el plástico que tiene un menor impacto medioambiental. Y si la gente no está dispuesta a pagar, lo que espero que sí, porque yo lo estoy, yo creo que la mayoría de gente lo estaríamos, porque la diferencia de precios sería mínima, ¿vale? Hay que bonificarlo económicamente de otras maneras, incentivos fiscales, lo que sea, pero hay que ganar la aceptación del público y de los gobiernos. También hay que mejorar algo que tiene que ver con la gestión de residuos. Primero, la selección actual de residuos no permite canalizar bien los biodegradables, no lo permite. Las tecnologías actuales de sorting no lo permite. Segundo, el tratamiento de la gestión de residuos orgánicos actuales no es compatible con los ciclos de los plásticos. Habrá que hacer algo. Claro, digamos, no pasa nada, que en lugar de 28 días, que estén 56. Bueno, pues en Barcelona, en lugar de 400 metros lineales de túnel, necesitaríamos 800 metros lineales de túneles para compostar. Y eso tiene un coste que hay que repercutir, hay que subir las tasas, es más caro, todo es más complicado. Entonces, los ciclos de digestión aeróbica no son compatibles y los de compostaje tampoco lo son. Con lo cual, ¿qué pasa? Que esto pasó, por ejemplo, en Italia, que es donde primero triunfó el PLA, hace casi 15 años, pues hace 10 años ya saltó un problemón allí que las plantas de compostaje dijeron, oye, no nos mandes más PLA. Y aquí en España me consta que la mayor parte de las que yo conozco unas cuantas, cuando llegan las bolsas de compostables que llegan a la basura, las cogen y a vertedero. Porque lo último que quieren es encontrarse esas bolsas de plástico o trozos de ellas en su compost final. Entonces, en estos momentos está sacándose y va igualmente a vertedero. Entonces, sin embargo, por no ser tan negativo, ¿cuáles son las oportunidades delante? Pues mira, sin lugar a dudas, va a permitir, o sea, bien gestionado, los polímeros biodegradables generan una cosa que es clara, que es la biocircularidad. Tú coges carbono, que si viene de origen renovable, y lo metes en un proceso de compostaje, de gestión de la materia orgánica, y estás haciendo lo mismo que todo el resto de cadenas de valor de materia orgánica, que la alimentación, que lo que sea. También gastan compost, fabrican manzanas, las manzanas se usan y lo que no se usa las manzanas se composta y va otra vez a hacer al campo, a hacer más compost. ¿Vale? O sea, si somos capaces de integrar ahí el plástico, miel sobre hojuelas. Tenemos el problema solucionado, por lo menos, para algunas aplicaciones. Segundo, también reducir la acumulación en el medio ambiente. Plásticos que se biodegradan en el medio ambiente es una buena herramienta. Tercero, permite herramientas muy potentes, como por ejemplo una liberación controlada de agentes en el campo, predecir el final de vida, programar la biodegradación, controlarla. Hay mucha tecnología por desarrollar en este campo. Y es muy útil en determinadas aplicaciones. La primera de ellas es cuando hay aplicaciones que no son reciclables. Hay algunas que por su naturaleza no son reciclables. Un envase multicapa, a lo mejor tiene 7 capas, 3 de las cuales son termostables, una es hidrófoba, otra es hidrófila, tiene una capa de EVO, una de polipropileno, 2 de... Claro, todo esto no hay manera de reciclarlo, no hay forma, no se puede físicamente. También cuando hay cosas pequeñitas y muy sucias. Si conocéis los procesos de reciclaje de plásticos, a la entrada de reciclaje del amarillo, a la entrada del proceso de sorting, lo que hay es un trimmer por lo cual nada que sea más pequeño que esto se recicla. Porque no hay manera de separarlo luego aguas abajo. Tú no puedes separar trocitos pequeñitos. Las herramientas que hay para separar no te lo permiten. Entonces, para que no haya impurezas en todos los ciclos posteriores, lo que es pequeño ha de salir. Por tanto, los papeles de caramelitos, los trocitos de plástico, todo eso no se recicla, todo eso va a vertedero en España. ¿Vale? No se recicla. Escapa completamente a circularidad, porque técnicamente no es posible. Con lo cual, hacer algo que fuera biodegradable, esas cosas pequeñas, que generalmente tienen pocas exigencias mecánicas, ni barrera, ni nada, a lo mejor es una buena opción. Tema higiénico, también. Un problemón espectacular, el tema higiénico. También, allí donde no hay una gestión adecuada de residuos, es interesante. ¿Vale? Aplicarlo donde no haya una gestión adecuada de residuos. Y también, y esto es muy importante, para usos agrícolas, donde no está prevista la recuperación del plástico posterior. Un porcentaje grandísimo de los residuos plásticos en el mar viene de la industria pesquera. Grandísimo. No recuerdo ahora la tarta, pero de macroplásticos era muy importante. No sé, era más del 30%. Una cosa bárbara. Es muy grande. Chicos, hay un problema. Yo creo que tenemos margen de mejora con esto. Y en el plástico agrícola, todos los plásticos pequeñitos, las etiquetitas, las gomitas para tutorar, todos los plásticos agrícolas, ahí tienen mucho margen de mejora. Cuando no tiene sentido esto es importante, cuando no tiene sentido hacer un bio en plástico, cuando hacer un biodegradable es hacer un pan con unas tortas. Primero, cuando el reciclaje es posible. Si se puede reciclar, se debe reciclar. No tiene sentido biodegradable cuando se puede reciclar. El impacto medioambiental es mucho menor. Que no sea un reciclaje que sea un downcycle, que no sea un reciclaje en el mismo sector de aplicación, sino que se gaste en otro segundo sector. Bien. Pero tú, si lo puedes reaprovechar luego como plástico, gástalo como plástico. Eso no hay ninguna duda. Es mucho mejor. Pero el reciclaje ya sabemos que tiene unos límites que hemos alcanzado, hemos alcanzado ya el límite que es la capacidad máxima de reciclaje mecánico. Primero porque empezamos a perder muchas propiedades. Segundo, porque por un tema de aditivos la cosa se pone mucho más complicada en tema de seguridad alimentaria y seguridad para los humanos incluso se pone complicada, porque hay sectores como el envase alimentario en el cual no se permite más que el PET en reciclaje de material metálico. Hay una normativa que sí que lo permite, pero nadie lo aplica, y la comunidad que nos dedicamos a esto, cuando salió, yo aún estoy patidifuso, ¿no? Es decir, ¿esto cómo se les ocurre? Con lo cual, hay limitaciones en el reciclaje, pero si se puede reciclar es la mejor opción, no hay duda. ¿Cuándo no tiene sentido? Cuando lo vamos a enterrar en un vertedero. Si lo vamos a enterrar en un vertedero, da igual que sea un polietileno que un PLA, es que da igual. ¿Qué más da? Si lo vas a enterrar, ¿qué te aporta que se vaya a biodegradar? Va a estar encapsulado ahí junto con una cafetera hasta que alguien venga y lo saque. Es decir, no te aporta nada nuevo. Y permitiría, ya no es lo que te aporte, es que permitiría entonces, si consigue, por ejemplo, la Unión Europea no permite certificación de biodegradación en compostaje. En vertedero. La americana sí. ¿Por qué? Pues imaginaros si les diéramos el certificado de que es biodegradable en vertedero, ahora cómo quitamos los vertederos. ¿Vale? Entonces no está sobre la mesa. Tercera parte, para partes permanentes y componentes permanentes. Aquí, ¿en qué momento se nos ocurre que puede ser una buena idea hacer un avión o hacer un coche de un polímero que es comida para las bacterias? Esto no es una buena idea. No lo es. Primero porque es peor desde un punto de vista de performance, habría que aditivarlo muchísimo más para que se comportara y pudiera cumplir con lo que te pide el sector de automoción. Y segundo, vas a tener problemas de biofouling. Y si no quieres tener biofouling, vas a tener de crecimiento bacteriano en superficie. Y si no quieres tener problemas, vas a tener que aditivar con antimicrobianos eso a saco, porque eso te tiene que aguantar 20 años o 15 años. Es decir, y quien tiene un coche en el Sahara no le pasa, pero quien tiene un coche en Cuba, ¿vale? Tiene un problema con ese tema. Quiero decir, hay que poner sentido común a esto. No tiene sentido hacer biodegradable para cualquier cosa. Y luego, sobre todo y fundamentalmente, si el uso de la palabra biodegradable, si el uso del concepto biodegradable acaba siendo una manera de mal emplearlo y de favorecer la no gestión de los residuos de estos plásticos. O sea, esto para mí es clave. ¿vale? Esto es un tema que se ha de trabajar muchísimo. Ahí ha salido ahora un marco europeo para el tema de greenwashing y demás. Yo espero que sigan trabajando en esta línea, porque esto sí que realmente no solo tiene la parte negativa del producto que se genera con eso, sino también la parte negativa de que empezaremos a asociar una cosa que es potencialmente muy buena a cosas muy malas. Y cuando esto suceda, no os preocupéis que estarán los stakeholders actuales para aprovecharlo, ¿vale? Y que nada cambie. Entonces, todo lo que pueda ser, todo lo que sea greenwashing, todo lo que sea mala comunicación, para mí esto es un tema muy serio, ¿eh? Tan serio como la parte real de contaminación de más de los plásticos, porque va a ser lo que va a garantizar el camino para que esto sea una realidad en 10, 15 años, para que de aquí 10, 15 años estemos igual, solo que produciendo un 20, un 30, un 40% más de plástico del de ahora. Y bueno, con esto concluyo mi presentación. Muchas gracias.
Bueno, Luis, muchas gracias por esta magnífica presentación, por aclararnos los conceptos y, bueno, quizás dejarnos un poco un mal sabor si pensábamos que por esta vía podíamos encontrar una fácil solución al problema, pero bueno, es bueno conocer cuál es la situación real de las cosas. Tenemos tiempo para un par de preguntas, si hay alguna pregunta. ¿No? Sí.
Hola, Luis, muchas gracias por la presentación. Me ha gustado mucho. Una pregunta sobre la huella de carbono que has hablado antes del plástico biodegradable en comparación con el plástico habitual. ¿Es la huella de carbono que se mira en la fabricación o de todo el plástico desde que se fabrica hasta su cuna, que se llama?
Yo no soy experto en LCA, esto me lo pasó una compañera que se dedica a esto y recuerdo que fue en todo, porque el problema que tienen los bioplásticos es el uso de disolventes y de la parte catalítica y demás, y ahí es una barbaridad comparado con el plástico normal.
Vale, es que yo pensaba que quizá teniendo en cuenta todo el ciclo desde de cuna a tumba, es decir, desde que se fabrica hasta que se va, que quizá con el biodegradable, bueno, ahora contando todo lo que has contado que no es biodegradable, pues se reducía, pero viendo eso, pues...
Probablemente el que mejor salga sea el polietileno biobasado ahí. Ahí sí saldrá mejor. Vale, pero no lo declaré. Una cosa que a lo mejor me he quedado con... Claro, normalmente yo estoy acostumbrado a dar estas presentaciones en foros de polímeros biodegradables o de bioplásticos, gente que trabaja en bioplásticos. Entonces, a lo mejor he transmitido negatividad. No quiero transmitir negatividad, quiero simplemente poner en relevancia que la cosa es compleja y que no podemos decir esto es un bioplástico y ya está. Quiero decir, esto es un bioplástico, vale, esto es una solución. Yo llevo 20 años trabajando en esto, me lo creo. No estoy haciendo una cosa que no me crea. Ahora, lo que sí es que hay que, o sea, para que esto sea funcional, hay que hacer las cosas bien. Hacerlas bien es legislación, tratamiento de residuos, industria del plástico. No podemos permitir, por ejemplo, una cosa que está sucediendo muchísimo, que es en polímeros biodegradables, que además, precisamente, hay artículos que han salido al respecto de esto recientemente, incluso del IDAEA, cargar un polímero biodegradable que tú sabes que se va a biodegradar, que tú sabes que va a desaparecer, con todo tipo de aditivos horrorosos. Quiero decir, esto no puede ser. Tienes que ser responsable, que esto te lo va a liberar. Si un plástico normal ya te da problemas por migración, imagínate uno que está destinado a desaparecer. O sea, es que no hay ni un solo nanogramo de aditivo que no vaya a estar liberado en ese plástico. Por tanto, hay que ser muy responsables con lo que se pone ahí. ¿Vale? Entonces, a eso me refiero, que hay que ser conscientes que no se puede continuar igual.
Muchas gracias por la presentación. Y en esa relación siempre difícil que hay entre industria, gobierno y científicos, ¿no? Con los conocimientos científicos necesitas que la industria se implique y necesitas que te legislen. En el caso de los bioplásticos, tú que estás como más interaccionando con ellos, ¿cómo ves presente-futuro en el sentido de los bioplásticos? Gracias.
Pues hay una lucha fuerte, ¿vale? Hay una lucha fuerte. Hay una lucha fuerte por varios motivos. Primero, porque tienen argumentos para ir en contra. Uno de los principales es la huella de CO2. Entonces, al final, todo el mundo vamos a medir en huella de CO2 el impacto medioambiental de lo que hacemos, pues los bioplásticos van a salir mal parados. Por lo menos a día de hoy, ¿vale? Van a salir mal parados. Respecto al plástico, pasa automoción, por ejemplo, y es que no hay ningún motivo para, incluso en envase alimentario, en cadenas logísticas y demás, es complicado. Entonces, tienen argumentos para ir en contra, ¿vale? Tienen argumentos para ir en contra. También el tema de la seguridad con los aditivos, también tienen una batería de argumentos para ir en contra. Sin embargo, la comunidad científica estamos remando mucho a favor, muchísimo. Y los legisladores, pues, como siempre, navegan entre dos aguas. ¿Por qué? Porque escuchan mucho a la Comisión Europea, por ejemplo, escucha muchísimo a los investigadores de la comunidad científica y de hecho solo hay que ver, por ejemplo, toda la cantidad de proyectos, de convocatorias de proyectos europeos que van dedicados precisamente a los bioplásticos. Un montón de ellos. Hay muchísimos. Es una cosa clave, ¿vale? Y aparece en la misión suelo y aparece en la misión... Es clave. Luego la comunidad científica y la Comisión Europea se lo cree. Ahora bien, tienen también toda una herramienta de lobby o de industria muy potente, que en realidad son los que fabrican las cosas, que les dicen, mira, así no podemos, con esto no se puede, fíjate que esto es mejor, date cuenta este artículo que ha salido que dice que no sé cuántos, oye, fíjate que no sé qué, oye, que es que ni siquiera ellos lo tienen claro, pues vamos a dejarlo conforme está la cosa, porque es que te voy a echar 15.000 personas a la calle, porque es que... Entonces hay toda una pugna actual entre la parte científica y la parte... Entonces nos encontramos, por ejemplo, os daré un caso claro, no sé si conoceréis todos vosotros los polihidroxialcanoatos. Son unos plásticos que se producen las bacterias de manera natural, por tanto, desde un punto de vista medioambiental sería similar a la celulosa, la molécula. Está presente en la naturaleza, se biodegrada en todas partes, hay miles de cepas bacterianas en todas partes que son capaces de quemarlo. Esto, por azar de la naturaleza, da unas propiedades termoplásticas, es decir, la fundes y es un plástico. Esto no pasa. Tú vas por el campo de la naturaleza y las cosas no son termoplásticas. La materia viva se quema, no se funde. Entonces, ese plástico, tenemos una molécula tan espectacular como un poliéster, que es esto, los PHAs, que es biodegradable y que además es termoplástico, ¿vale? Y en la directiva SUP de plásticos de un solo uso no la han salvado de la quema. ¿Qué ha pasado aquí? Ay, es que resulta que se fabrica de manera... Dice que la excusa es que se fabrica de manera industrial, sí, y el queso también, y la cerveza también, y nadie duda que sea orgánica, que se hace por fermentación. Pues pasan cosas como estas. Entonces, un camino que la comunidad científica tiene clara, en ocasiones la empresa y la política te lo dificultan, sí. Es complejo.
Yo tengo una cuestión que lo que has estado explicando del compostaje, que claro, requeriría mucho más tiempo el poder estar a temperatura de 50 y tantos grados para poder conseguir la degradación en 6 meses que comentabas. ¿No sería una opción viable, igual que hacemos recogida selectiva de todo, hacer recogida selectiva de estos bioplásticos y entonces no tenerlos que juntar con las plantas de compostaje generales, sino hacer plantas de compostaje específicas para estos bioplásticos? ¿No podría ser eso una solución más viable, quizá?
Sí, yo creo que es una o la solución, de momento, en el primer plano. Es hacer flujos de materia orgánica sin plásticos y flujos con gran contenido de plásticos. Y la que va sin plásticos, como la actual, en 28 días está estupendo. Y la que no está de esto sí que habría que tenerla más. Y luego también hay otra cosa que es muy importante, que es diferenciar los bioplásticos que después del proceso de compostaje van a continuar con su biodegradación normal de aquellos que no. ¿Por qué? Porque al final el compost como resultado, el compost es materia orgánica. Es decir, solo el 40% de la materia orgánica se pasa a CO2, el 60% está ahí. Cuando uno tiene un compost y ve un hueso de aceituna, no se preocupa porque sabe que lo echa en el campo y va a desaparecer. O un trozo de hueso, no se preocupa porque se va a desaparecer. Bueno, pues puede pasar lo mismo con plásticos que luego vayan a biodegradarse en el campo. Si ves un trozo de plástico, pero tú sabes que ese plástico en el campo en 6 meses va a desaparecer porque es, por ejemplo, de PHA, como de polihidroxialcanoato, pues no había mayor problema. ¿Vale? Entonces yo creo que están esas dos líneas. Y hay una tercera que está trabajando también, que es en... Claro, no hay en estos momentos los consorcios microbianos del compostaje industrial, como de la naturaleza en general, han evolucionado para comerse la materia orgánica, no los plásticos. Entonces hay todo un trabajo que está haciendo ahora en microbiología de identificar cepas que son selectivas con la degradación del plástico e introducirlas en procesos de compostaje de manera que había aumento de ese proceso, que desbalancees para que si tiene que quedar agua al final del compost, que no sea el plástico, que quede la fruta o la madera.
Bueno, Luis, pues muchísimas gracias por tus explicaciones y por aclararnos un poco todo este tema y por acompañarnos en estas jornadas. Bueno, nada. Y ahora, bueno, vamos con un pelín de retraso, pero empezamos ya la primera sesión y llamo a las chairmans, a María Vila y Lara Cioni, que se encargarán de llevar la sesión.
Okay. So maybe next speaker, which is Clara. Oh, a ver. No, Mapis. Sorry, Mapis. Are you ready to give the talk now? We can do we can switch both speakers and now start with Mapis Carrillo. She's working on the interaction between plastics and macroinvertebrates. Maybe, yeah, this one, right? So the title of her talk is Bioplastics, Effects on Microbiome and Brain, Crosstalk and Cognition in Daphnia magna.
Okay, so I am Maria Paula Carrillo, but everybody calls me Mapis. So I am quite a morning person, so I come with a lot of energy, and I hope I can transmit some of that to you, so you can end up loving as much as I do the study of the microbiome and brain crosstalk and cognition to evaluate the effects of bioplastics. Before I start, I want to say that you have to be very focused to understand the things because it might be a little complex, so direct all your senses here and let's be present and do some mindfulness. So, okay. The study of pollutants is a bit difficult, and if you don't agree with that, it's because you have not studied the pollutants in aquatic ecosystems. So, in the environment, the pollutants are present in mixes, they are difficult to identify, they also can be accumulated and be toxic to the marine species or aquatic species. And so there is this new need of new technologies to integrate the whole study. So I want to say, well, a bit of bioplastics, although I think the previous speaker explained it quite better. But they have come up as a more sustainable alternative to plastics, but there is this questionable biodegradability in aquatic ecosystems. So some studies also indicate that they can be as toxic or even more to the petroleum-derived plastics, and also their toxicity has been studied for the particle itself, not only for the additives. And about multiomics, this is like new technologies that we can use to study pollutants. And I want to talk about the gut microbiome. I mentioned it before in the title, and it's important that you understand what it is. So gut microbiome is the microorganisms associated to some higher organism. They communicate, these are bacteria mostly, communicate with other organs and affect or are implied in the effects that pollutants or other modulators can have in the organism. Maybe you have heard about microbiome because now it's a little bit fashionable. Everybody has gut dysbiosis that is called SIBO. And in that case, it's related with diet, stress, but recent research has shown that also the environmental exposure to different pollutants can affect gut microbiome. And this imbalance can be involved with the whole toxicity in the organism. So we thought maybe bioplastic particles can have this effect, provoke this imbalance in the gut microbiome, for instance, by potentially growth harmful bacteria and introducing them by ingestion. Or at least we hope something happens so that we can see something, right? We aim to assess the effect of bioplastic particles in the feeding and behavioral responses, gut microbiome and cephalic transcription in Daphnia magna, and we think that probably these microparticles will have an effect in gut-brain axis because it is a very sensitive endpoint we can measure, and that this can be reflected also in their food intake or altered locomotion. This is the experimental design. So briefly, we exposed Daphnia in different tanks to these different groups. There are several controls. For instance, negative control, it means we did not add anything. Then, obviously, we exposed them to bioplastics, specifically polylactic acid and polyhydroxybutyrate, which are more or less the most common ones. And we used two concentrations, a more environmentally relevant one that it's called low from now on, the presentation, and a high concentration to check for toxic effects. We also exposed Daphnia to kaolin in another group to check for the particle effect of natural particles. So this should not be harmful. And lastly, we left some Daphnia in starvation, so we didn't add food, to check if some of the effects of the microparticles are related with the Daphnia not eating, but you can ask me in the questions why we did that. Then, after the exposure of 3 days, we measured the feeding inhibition, and also we did several behavior tests, so we can see how the Daphnia are behaving. And then we also took samples from the brain to evaluate the transcriptomic response, which I didn't explain before because I forgot. But transcriptomics are other omics, and when we mix transcriptomics and metagenomics, so gut and brain, we can do a multi-omics assay and check if there is something connected in this pathway. And then, of course, we also evaluated the gut microbiome by sequencing the 16S, and also we characterized the bacteria present in the water, both attached to particles, I mean the microplastics or the kaolin particles, and also the ones that bacteria that are free living in the water. Okay, so the results we obtained showed that these bioplastic microparticles at high concentration did inhibit feeding and also had effects on the behavioral responses to light stimuli. It's a measurement we use to check how the Daphnia behaves. So these results are similar to previously reported ones, and these effects show a maladaptive anti-predator response. So this is quite bad for the Daphnia because it means she cannot respond well to predators in their environment. However, at low concentrations, we didn't see any effects. So, the gut microbiome. So, we saw that when we exposed Daphnia to microplastics of PLA and PHP, there was an increasing in the relative abundance of Enterobacterales and Pseudomonadales. These are taxa of bacteria that are normally pathogenic in Daphnia or other aquatic organisms, even in humans. And also we saw a decrease in a key good bacterial taxa of the Daphnia gut microbiome that is implied in their health. Okay, so I don't know if you understand well when I say bacterial communities, but they are like societies. So when you evaluate a society, you take into account all the individuals that integrate them. And when there is a neighborhood, for instance, that changes, you can see changes in the whole society, right? So with bacteria, it's more or less the same. If we see a change in specific taxa or bacterial groups, then the whole community is changing. And this is what we can see in this graph here, that bioplastics and starving conditions shape the bacterial community. Also, this analysis, which is called partial least square analysis, allow us to identify which specific genera of bacteria, so it allows us to go more specific, on the bacteria that provoke the changes in the bacterial community. And they are highlighted here, but probably it's slow and you cannot see it, but the bacteria are taxa from Enterobacterales and Pseudomonadales, so same as before. And this change is seen in bioplastics and starving conditions at high concentrations mostly. Vale. So, when you characterize a bacterial community, you can also characterize their functions, because each bacteria or groups of bacteria have a role in this community. And we saw that at high concentrations, the effects were more discernible. And what we saw was that short-chain fatty acids via synthesis pathways had lower abundances after the microplastics exposures. So what is short-chain fatty acids? These are like biomolecules produced by the bacteria that communicate with the brain. So this gives us a lot of information of what is happening in this connection. And also we saw differences in the precursors of different neurotransmitters. So in this case, the effects were opposite to the ones observed in starvation conditions. And that was also the case for the transcriptomics analysis. It means the genes that are dysregulated in the brain of the Daphnia are dysregulated differently depending on if they are exposed to microplastics or to starvation conditions. In cluster A, we are seeing the genes that are upregulated in PLA mostly, and downregulated or less expressed after starving conditions. PHB didn't show many changes in this endpoint measure. I don't know if you remember, but I said that physiological responses were similar in starvation conditions and in bioplastic exposures. And this means that if then the transcriptomic and functional microbiome responses are different, probably the mechanism to reach these effects that we can see is different. And to end, I put the most fancy graph, but it is just showing the differences, responses in the functional analysis of the transcription in the brain. Okay, so what this means? This means that when genes are deregulated, this is expressed in different functions altered in the organism. So we saw that functions such as cell turnover, growth, and differentiation were upregulated after bioplastic exposure, PLA, but downregulated after starvations. And this can be related by the effect of the gut dysbiosis involved in plastics exposure, but the need to preserve energy for maintenance in starvation conditions. Also, dopaminergic pathway was deregulated, by microplastics, both of them, and this means there is a potential neurotoxicity associated with microplastics as well, and this can be further explored. And also we observed some differences between the use of fatty acids and carbohydrate pathways. So we can see all that I explained here. This is just a cluster analysis of the different pathways that are altered in these exposures. And here you can see the relative abundance of the genes in each of these pathways here for each cluster. So you can see the pattern is quite different between starvation and bioplastics. So to conclude, both microparticles altered behavior and feeding responses in Daphnia, also altered the gut microbiome, enriching pathogenic taxa, mimicking starvation effects. But this only happened at high concentrations. And you can ask, well, why just in high concentration? I mean, what I want to know is what happens at environmental relevant ones. Well, we need to check what are the effects of these microparticles to compare them with microplastics. And for that, in toxicology, we use sublethal concentrations. So it's because of that. But it's actually a nice conclusion as well. Also, these microparticles showed opposite transcriptomic patterns to starvation ones. And as I said before, this means there is different mechanisms involved in how the Daphnia responds to the microplastics or starvation conditions. And well, last but not least, this is the first evidence in invertebrates linking this gut microbiome. So this is quite new because, as I said before, in humans it's quite known that gut microbiome has an impact in the brain and in mental health and everything. But in Daphnia or other aquatic animals, this is not so known. And gut microbiome is quite sensitive to pollution. So I think it's very nice that we can study this now. And just to finish, I wanted to highlight and give you a little spoiler about my thesis. And this increase in enterobacterales and pseudomonadales that I told you that are pathogenic bacteria is a trend that we are observing as well after exposing to other pollutants, such as organophosphate esters that are plasticizers, as Ethel commented yesterday. So maybe we have here a potential tool to examine pollution in an integrated way. So what I mean with this, when you have a mix of pollutants, maybe you cannot measure targeted pollutants because some of them will be at low detection limits or other techniques that might difficult you to identify them. But if you see a change in microbiomes that indicates this trend, you can more or less see that there is some pollution happening there and you can explore more. So, as always in life, teamwork is quite important, and I think integrating all disciplines might give more information. And to end with teamwork, I want to give thanks to my two teams, because I have two teams, I am so lucky, and well, to all of you for listening to me.
So thanks a lot for the great presentation. We have time for one question. Any question?
Thank you very much for the talk, so interesting. You were mentioning that you are using these high concentrations because it's a way to explore the toxicology. I'm wondering if it would be also interesting to make some more chronic exposure at lower concentrations to see whether or not is it also relevant in terms of environmental impacts.
Yes, that's very interesting that you mentioned, because on the one hand, 3 days might seem low, but for Daphnia it's quite some time. So this is not an acute exposure. Acute exposure in Daphnia is hours. So this is between acute and chronic. But I agree with you that it's important to evaluate more chronic exposure, but in this case was because of the experimental design. We wanted to leave the microparticles untouched, to say it some way. And for Daphnia, these are like sensitive organisms. If you don't change the food, they die, just because of the change of the medium. You need to change it every 2 days, or at most every 3 days. So it is because of this that gets more difficult to do the experimental design, but we will for sure consider it.
We have time for one quick question.
Thank you for the presentation. I have a curiosity about the exposure to these particles. Were they like constantly agitated? How did you ensure that the particles were always in contact with the organism?
Yes, we have a system of agitation, so they were like moving all the time and floating.
And while changing the alimentation, you would renew particles, or you would just renew with fresh media?
No, they were left there. It's like a machine that you use closed bottles, and it goes like this, like
So
cycling.
it's constant concentration of the particles.
Yes, exactly.
Okay, thank you.
Yeah, you are welcome.
Okay, so thanks again for your presentation, and we have to move to the next speaker. So I think now the first presentation should be uploaded. So I would like to introduce Berta Bonet from EBD-CSIC, who's gonna present about bioplastics, trick or treat for freshwater ecosystems in the context of global change. Thank you.
Thank you, and sorry. So now we have the presentation here. And as the title is saying, is bioplastic, it can be a trick or treat. No? It's something that Luis was discussing before, if it can be something that it can be not harmful for the environment, but also maybe can produce some kind of unexpected effects. So let's see. And also let's see in freshwater ecosystems and in the context of global change. So we here already know that in the sea, in the oceans, there are plastics because the rivers are the main transporters of this kind of materials. And here we can see in the Global Mundi several spots that are important for this introduction of materials in the sea. So what we can do is just cut and reduce this transport, or may focus in these streams. Because plastics, we know that they can arrive from several sources, agricultural, industrial, even at home when we are doing our laundry, right? So it's important to see what happens when they arrive in the environment, in freshwater ecosystems. Because sometimes plastics can produce effects at different levels, biological levels, organizations, so it's cellular, cells, organs, that these can be different kind of ecological relevance. Depends if they are affecting just individuals, or maybe these effects can upscale to the population, or even to the ecosystem function. So problems or effects can be beyond what we can see, right? And when we can see them, maybe it can be late. So, okay, so plastics are harmful, are a problem for the environment, so let's produce bioplastics, right? That maybe looks like that it's the solution, but now maybe you are not completely convinced of that because for the previous talk, right? So plastics, looks like that the resident time in natural environments are less than plastics, so fine. Then also the likelihood of bioplastic causing harmful effects on living organisms is less than can be in plastics, right? And also because in the rivers, we have these microbial communities, biofilms, that can potentially decompose these materials due to their high potential recycling and decomposition capacity of nutrients such as carbon and nitrogen or phosphorus. Okay, but if this kind of microorganisms can decompose or decompose this kind of plastics, can be a source of nutrients for freshwater ecosystems? And if so, then can originate or start or trigger some kind of eutrophication problems? Or bioplastics, for example, have a lot of special additives, as this had been commented before, to perform those plasticity, colors, or any kind of other characteristics and properties. Antifungals, anti-agents, for example, for food packaging, they need to have this kind of additives, no, to avoid this kind of proliferation. So what happens when these materials arrive to freshwater ecosystems? What happens with our natural environment and natural microbial communities? Here, you already are familiar with this kind of graph. So we have this kind, three kind of bioplastics, but not all that shine is gold, because bio is used not very in an appropriate way. But here, so we have the conventional ones, the bioplastics, biodegradable ones, that, as we have seen here, right, can be fossil fuel bio-based and can be not biodegradable, and the other ones that can be fossil-based but degradable, and the other ones that should be the best ones, right, the best option, that are bio-based and biodegradable. But which are the difference between plastics and bioplastics once they are used? Once they are, so when we are talking about the end of their lives. Okay, in one hand, can be just recycling or composting, and also incinerating. But incinerating also is not a good solution because it's just increasing the gases and global warming, right? The other hand also it's the improper disposal that sometimes can happen, and sometimes it's just do it in purpose, and also the landfills. So then, when we have this in the system due to, for example, improper disposal and arrive to ecosystem, to freshwater ecosystems, what start is this kind of degradation, biotic, abiotic degradation, mineralization, and these materials are just broken in tiny materials like microplastics, and also release, or can release, or potentially can release their additives, right? And what happens then? Because microplastics can cause several problems, and we don't know in the environment if they can be synergistic, antagonistic. So bioplastics are the solution? It can be discussed, right? So what impacts we can expect on the environment, particularly in aquatic ecosystems, due to the increase of such materials, and especially with their additives? Or, for example, what impact will the degradation of bioplastics can have on carbon and nutrient cycles, and then consequently on the essential ecological service provided by these microbial communities, like can be the purification of water, right? And furthermore, and we're adding another thing, what happens if we increase temperature? For example, with global change, temperatures are changing, also the hydrological events are changing. So, in particular, with rising temperatures and increasingly frequent extreme meteorological events, such floods and prolonged droughts, results of the mobilization of plastics in freshwater ecosystems, so also can degrade more of them in microplastics. So there is an urgent need to investigate and gain a deeper understanding of the impact of bioplastics on freshwater ecosystems in the context of current, but also in the future global changes. And this is exactly the topic of my project, bioplastic effect, that aims to investigate and expand the knowledge based on the effects and discomposition of bioplastics in freshwater ecosystems in the context of current and future global changes. And to get this aim, we performed several experiments, and one of them is, for example, to assess the temperature effect on discomposition of bioplastics and their effects on fluvial biofilms. For that, we use three kinds of treatments. So one with one bioplastic, another with just biofilm, and another one with biofilm and this kind of bioplastic. In that case, we use Matter B. I don't know if you are familiar with this material. I will explain a bit more later. And we use per triplicate. We use these treatments and place it at 20 degrees and 30 degrees under laboratory conditions, right? And we expose them to and sampling them over these times, after the start exposition of plastics, after 1, 2, 6, 12, and 20 days. And we use the biofilm. We just scrape some samples from the streams and create our own biofilm in the lab. And yes, this is the experimental setup that we used. The plastic that we use is the Matter B, is a bioplastic that one company provides us. You maybe know, Implast. And the Matter B is a commercial and biodegradable thermoplastic based on all this long word, and a starch. Okay. And we are looking at that this polymer is a synthetic and 100% biodegradable polymer based on fossil resources. But this is not what in the website of the commercial company is saying. According to Novamont, that is the commercial one, it is saying that it's biodegradable, compostable, bioplastic, according to the standards, but industrial compostability, that is different process that can happen in environments. And also it's obtained by starches, cellulose, vegetable oils, and their combinations. And properties are similar to the low-density polyethylenes, so it's fantastic in terms of use and can change these plastics. But then also there are publications that talk a bit more about the composition of this plastic, because it's like a secret formula and you don't know what exactly is behind this name of Matter B. So in this publication, they say that the biodegradable polyester is about 65%, starch just 28%, and then there are natural plasticizers, about 6%. They then calculate the carbon content and determine that it was 26%. So also this material complies with this other normative about biodegradability in soils. Okay, soils, good. So with this knowledge, we prepare all our things, all our materials. We take not pellets, we use Matter B in format of film, and we cut this film in small squares, the 1x1. So we use these small squares in our Erlenmeyers. And we analyze different physiochemical measurements. We did this, and also different biological endpoints, right? And also we just take some extra samples just in case that so later on we can perform molecular analysis and taxonomy. So just moving to the results, here what we can see is that physiochemical parameters were constant throughout the experiments in all treatments and all the temperatures, so it's great. So we have this in a constant. But even though we saw at the end of the experiment visual differences between the treatments. Here, for example, we have after 21 days, the one that was just having biofilms and the one that having the Matter B and the biofilms, and the other one's the same, but with but at 20 degrees of temperature. So we can see that with temperature, the biofilm was having some kind of aggregations between them, and the other ones no. Wait. Oh, shh. Sorry. So what we have in 20 days with this material, it was a reduction between 4 and 8% of the initial bioplastic weight, because the plastic that we use, we dry and then weight, and then we place in each Erlenmeyer. So after 20 days, there was a loss of this weight that in both cases. So, and temperature was not affecting this kind of degradation of Matter B. Here, we analyze the nutrients of the water of each microcosm, of each Erlenmeyer, and we see that, for example, in this case, nitrogen was very basal, because the concentration, as you can see here, is very, very, very low. And also for phosphate, there was not difference between the temperatures, and also it was some kind of difference, but the scale of this graphic is very, very, very small. So this matter B did not release any nitrogen or phosphate in water. But yes, in the case of carbon, bioplastics cause an increase of DOC, of the dissolved organic carbon, from 1 wave onwards, and it was almost 8 times when we was just seeing the matter B treatment. As you can see here with the biofilm, there was not this release of, or not at least in comparison with the matter B. And with the combination with matter B and biofilm, there was also a release of DOC, but lower. That maybe indicate that that could be some kind of use of this DOC by the biofilm, right? Some kind of consume. Here, the chromophoric organic carbon organic dissolve. Here, a colleague just test different kind of ratios, different kind of indices, and here just to show you one. In this case, what we can see here is this SS to 275 to 195 absorbance slope between these lengths. And what we can see here is in matter B, there is a release of organic matter from the biofilm, indicating some kind of simplification of the organic. So here, in this case here, there are more aromatic molecules that over time was decreasing and converted more in aliphatic ones. In the biofilm treatment, we did not observe this. And here, with the combination of matter B and biofilm, the thing is that we cannot observe the same pattern like here, and it could seem that the biofilm can transform or assimilate these simple compounds, so that ones, right? And then and use them for more converted in more aromatic ones. Algal biomass. What happens with the algal biomass through the experiment? Here, as we expect, no biofilm, but there are some kind of this maybe contamination. No, let's see. In biofilm, there was a growing of the autotrophic compartment, and then yes, a decrease of them, and also happens with the matter B and biofilm. With matter B, this behavior, it's not the same here because maybe the biofilm is the autotrophic biomass is affected by the matter B. So, and here, sorry, I not mentioned before, but in the early layers, we didn't add any kind of nutrients, and we did not perform any change of water over the 20 days because we wanted to explore if, in fact, this kind of material, this matter B, can be or not a source of nutrients. So that's we didn't add anything. Also, we performed some extracellular enzyme activities to see what happens with nutrients and so on. And we use beta-glucosidase. In this case, beta-glucosidase presents degrade the cellulose to a more simple sugars and glucose. And here what we can see is, since there was nothing biologically in this treatment, so no activity, here there was some kind of activity, but when we add matter B and biofilm, we see an increase of this activity at both temperatures and then just at the cliff that can be related or not with the decrease of the community itself. So we have to also check again this. And with the phosphatase, it's another extracellular enzyme activity. Phosphatase, well, we have some kind of activity in somewhere that there are no microbial organisms, right? So this can be that in some way there are some material from this matter B that we have been using that maybe release something that can interact with the protocol or with the process that we analyze when we are analyzing the phosphatase. But here, for example, biofilm had this normal activity, some kinds higher with high in temperature, but was not more significant between these 10 degrees. And when we combine it, we see a different pattern that it's also we need to study deeper, because when there was an increase of this activity with an increase of temperature, but a decrease with lower temperature. So we have to look in detail more about what is going on here. And also what is going on in relation with the nutrients and the phosphate that we have present in our systems. So we still have a lot of things to do, a lot of things to analyze and to combine between them. For example, we need to we have to do bacterial biomass. That tomorrow we are going to start with this. Sorry. Also, we need to check all the photosynthetic activity, also the community respiration. We need to perform another extracellular activity related with nitrogen. Also, we have samples to analyze with a scanning electron microscope to see the change of the matter B surface from the beginning and after 20 days. Also, what is what's commenting now, that this kind of relationship between phosphatase and the matter B, why there is this kind of activity in somewhere that there are not biofilm. And also, apart from this test with matter B, we have other materials waiting in the lab just to start other tests, like can be PLS or PBS and other ones, under different conditions, with temperature, with nutrients, without. So yeah. So what I would like to take home message from this presentation is that bioplastics are a potential source of nutrients in fluvial ecosystems, can alter the biochemical cycles and the recycle of nutrients of ecosystems, altering the maintenance of biological production and altering the water quality. And this should be taken into account when we are assessing the impacts on freshwater ecosystems. And also, there is the need, not because it's bio, have to be treated different, because it's a plastic itself, it can be a microplastic itself, and the fate it will be the same in the fresh waters. So need to be treated as conventional plastics in terms of reuse, recyclability, composting. They have to be included in the circular economy as well. And of course, what we really need is to insist in environmental education, communication, schools everywhere, because bio does not mean that it will be 100% environmental friendly. So this we have to insist in this. And yes, of course, the things we cannot do it alone. So I was super happy to have this super team, and I really thanked all of them, and to you to be here and listen to this presentation. Thank you.
Thank you. Thank you. Thank you, Berta, for this presentation. We have time for a super, super quick question.
Yeah, thank you so much for your presentation. One slide that was about mass change. Thank you for your presentation. I learned a lot. I was wondering about the mass change or rate change in the slide that you were presenting. Is there any difference? I got it. There is difference in between the different temperature effects and yeah. I think this is the weight graphs. So there are differences in between different temperature condition. It means, okay, I don't know. Do you confirm it or no?
But no, I cannot confirm, because here there is no difference between the temperature, you mean?
In the end, the weight, the axis, the vertical axis, So it shows in a different temperature. In the end, you had different weight for the same sample after the process. Yes. So there is some gas releasing, no?
Yes.
Yeah, it can be detected, or if the system, the reactor or the media that you were applying was closed or an open system, or can be a concern of air pollution in a larger scale, or no, there is not any carbon monoxide or dioxide mitigation.
it depends. I mean, we use a closed system. It was a small one, a microcosm, and of course there was a release because also we observed a release of DOC, so carbon or dissolved in water. So of course there was some kind of release from matter D, from this material. What can happen in big systems? Let's see, because there are next steps that we have to do with flumes, recirculating flumes, or also in big tanks, and then we'll see. And also we can maybe using with big tanks or big mesocosms, for example.
Yes.
We can use some kind of proof to test if there are a release of CO2 or something like that. But what we can extract from this experiment.
Yeah, sure, for the future. Yeah, it was my concern. Just thank you so much. I enjoyed a lot. Thank you.
Thank you very much. Let's move to the next speaker, who is Clara Serrano from IDAEA in Barcelona. And today she's going to talk about the comparison of the effects of bioplastic products on marine bacterial communities in a microcosmos experiment. Thank you, Clara.
Thank you, Maria. Okay, so good morning, everyone. Yes, I'm presenting you another study about bioplastics, but this time about their effects on marine bacterial communities. Because bioplastics arrive in the marine environment mostly by terrestrial inputs, so these freshwater ecosystems that Berta was talking about. And once in seawater, photodegradation and physical fragmentation modify their physical properties. So on one hand, smaller fragments and particles like micro and nano bioplastics are produced, and they can be transported by oceanic currents or sink to the deep ocean. And on the other hand, plastic additives and monomers that compose these bioplastics are released into seawater. These are like abiotic processes that affect bioplastic ones in seawater. But also, microorganisms living in seawater colonize the surfaces of bioplastics in a specific structures called biofilms that are responsible for the biodegradation of the bioplastic. The bioplastics studied here were specifically produced from bio-based and biodegradable biopolymers. So in this graph that Luis and Berta were showing, they are like the good ones. And specifically, we studied bioplastics produced from polylactic acid, PLA, and polydroxybutyrate, PHB. Yes, because they've been proposed as a truly sustainable alternative for conventional plastics. And why? Well, due to mainly their independence from fossil resources, due to their properties that are similar or can be similar to other conventional plastics, and what is of interest for us, due to their biodegradability by microorganisms, which interestingly in seawater is where bioplastics are degraded to a lower extent. So, and the main responsible of this biodegradation, the first microorganisms that initiate this, are marine bacteria. They are the ones colonizing the bioplastic in the first place, initiating the biofilm, and depolymerizing the biopolymer. And we know that marine bacteria living with bioplastics in seawater can be either freely in seawater, can be living particle attached to some particulate organic matter present in seawater, or directly attached to the bioplastics, creating the biofilm and potentially biodegrading it. So we considered these three fractions of bacteria in the community to answer which are the effects of selected bioplastics and the leachates they produce on the composition of marine bacterial communities of these diffractions. Also to know which bacterial responses to bioplastics and leachates we can detect. And we, at last, aim to identify bacterial taxa with potential for bioplastic degradation. To do so, we set up a microcosm experiment simulating Mediterranean coastal environment. So seawater was collected from a low pollution input area and amended with different bioplastic types produced from these different biopolymers. So we had pristine PLA and PHP pellets that are expected to have less additives content, and also ready-to-use knife and bag bio-based that are commercial products with more additives content expected. And we also had a control treatment with only bacteria, and also all these treatments but without any bacteria, so as abiotic treatments. And the microcosms were in constant UV and aeration conditions with pH and temperature controlled during the 2 months of incubation, so 16 days. Every 2 weeks, we sampled the chemical part to see the leachates that were being produced and potentially affecting the community. And at the end of the experiment, a full chemical and microbiological characterization was performed. So on the chemical part, water aliquots were extracted by solid phase extraction and then analyzed by liquid chromatography coupled to high-resolution mass spectrometry to tentatively detect these leachates. And the biological samples consisted on the analysis of the bacterial production only of the free-living bacteria, and then of the analysis of this community structure of the 3 fractions that I mentioned by rRNA 16S gene amplification and sequencing. So first, in total, talking about the compounds, the leachates that were produced, we detected that during the whole experiment, 160 compounds were detected where bacteria were living. And at the end of the experiment, that is when we sampled also the biological measurements, so we can compare the effects of the compounds on the community, we see that 132 compounds were detected. From these, 60 were detected only when bacteria were present in seawater. So they are most probably produced as a result of bacterial activity. And then 72 were produced when bacteria were there, but also when any bacteria was there. So they are most probably produced by abiotic processes. And both biotic and abiotic produced compounds can modulate these bacterial communities. So we look at the biological measurements to test what the effects were. And the measurements were the bacterial production in this graph and the bacterial abundance on the other one. First, the bacterial production was measured by the incorporation of radiolabeled leucine in each cell per milliliter, in each cell, sorry. And we measured it, remember, only in the free living fraction. So what we could observe is that bacteria living with PLA in seawater freely were the most productive ones. Then looking at the bacterial abundance that was measured by the rRNA 16S gene copies per milliliter and represented per fraction of bacteria, we see that in the free living fraction, the most abundant ones were those living with PHB pellets. And in this fraction, so the most productive bacteria were not the most abundant. Then looking at the particle-attached bacteria, there are these ones that live attached to organic matter present in seawater. Any bioplastic type was resulting in a differences in the abundances, and bioplastic bacteria living attached to the bag were the most abundant in this fraction and among all. So in general, what we can say is that the different fractions of the community were affected differently by bioplastic types. And then looking at the community structure, we also saw differences by fractions of the community. In this graph, what we see is that the unique number of the number of unique bacteria, so the number of unique species, that is the richness present in each fraction of each microcosm, is always higher, so there are always more unique bacteria living attached to the bioplastic, creating this biofilm. And in this other graph that represents the relative abundances of the top 15 taxa, so the most representative ones for all the samples, we see that these bacteria are specific of this fraction. So not only they have most unique taxa that are specific of this, but they are only living bioplastic attached. And interestingly, some taxa are enriched in this fraction, and specifically Phytis varales is described by literature to be ubiquitous in biofilms of bioplastics, and it has a potential for bioplastic biodegradation. And finally, this graph represents the dissimilarities, so the differences between the bacterial communities of the different bioplastic types, and also identifies some compounds that can be covariants or like modulators of these differences by the arrows. And these compounds modulating the differences between communities were only detected in the bioplastic attached fraction and in the free living fraction. First, for the bioplastic attached, we observed that 2 plastic additives were not present in the PLA microcosms, so they were driving the differentiation of these communities compared to the others. And in the free living communities, knife and bag communities, so the commercial products, were more similar or were differentiated from the pellet communities. According to the additive contents of commercial products or pellets, the compound driving the differentiation of the knife and the bag that are commercial products with more additives is a plastic additive, but in pellets that are expected to present less additive content or any, the compound driving the differentiation was a copolymer that is also used to change some properties in the final product, but it's not directly catalogized as a plastic additive. So this study allowed us to conclude that leachates are produced in similar proportions by abiotic and biotic processes, that fractions of the community are affected differently by bioplastics, that bioplastic attached fraction had higher bacterial richness compared to free living and part attached. Also in the bioplastic attached community that was specific, some taxa were enriched and could have biodegradation potential for bioplastics. And last, that specific leachates presence could be significantly related to the differences in the community composition, only for those bacteria living bioplastic attached and free living. And last but not least, I would like to thank my wonderful team and collaborators, and thank you for your attention.
Thanks, Clara, for the great presentation. We have time for one question. I have one, actually. So for the experiments with the pellets, what was the size of the pellets? Would be the size a factor that could influence the growth of the bacteria?
Would be a size, sorry?
The size of the pellets.
They were like micro pellets. We bought them to a manufacturer, so I think the sizes were not considered for us, just pellet of pure pristine PLA and PHP.
Okay, thank you.
Thanks, Steve.
So we can move on to the last speaker of this session. Yeah, thanks again to Clara. I would like to introduce Marlid García from Universitat Complutense de Madrid. who's going to speak about interaction of nanoplastics and phenanthrene, evaluation of ecotoxic effects on in vivo and in vitro fish models.
Okay, so thank you everybody for attending this conference. I'm from Autonomous University of Barcelona. And today it's a pleasure to me present part of our research work. It is a collaboration with the Universidad Complutense de Madrid. The presence of nanoplastics in the environment is recognized as a problem of a global concern. The previous results from our groups and others have shown the nanoplastics can accumulate in fish cells and tissues, and due to their hydrophobic natures and large specific surface area, they could absorb other pollutants like polycyclic aromatic hydrocarbons like phenanthrene, a type of persistent organic pollutants, and they could accumulate easily in aquatic organisms, modulating bioavailability and hazardousness. And the bioaccumulation of nanoplastics brings adverse effects in the food chain. Being the relevant knowledge gap, can nanoplastics modulate the effect of persistent organic pollutants? In this context, the liver is the main detoxification organ in vertebrates. Piece and piece accumulation has been in zebrafish liver cells has been previously reported. On the other hand, the main tissues exposed to nanoplastics in aquatic organisms are the gills and gut, with the gastrointestinal epithelium having the largest surface area, therefore being one of the main portals of entry for both nanoplastics and persistent organic pollutants. Accordingly, to assess the ecotoxic effects of the interaction between nanoplastics and phenanthrene on uptake and metabolism, we use zebrafish liver cells and intestinal epithelial cells from rainbow trout as in vitro model and zebrafish larvae as in vivo model. We work with polyestyrene nanoplastics piece and piece of 50 nanometers and plus phenanthrene and pre-incubation 24 hours. First, to evaluate the uptake, we perform by flow cytometry piece and piece uptake in zebrafish liver cells. As you can see in the graph marked in orange, we can observe that the piece and piece uptake increase in presence of phenanthrene. On the other hand, we can observe that the percentage fluorescent zebrafish liver cells and mean fluorescence intensity is lower when the cells were not co-exposed to piece and piece plus phenanthrene. And by BD view cells technology, in the image on the right side, we can observe that we can confirm the uptake of piece and piece increase in the presence of phenanthrene. To obtain more information and confirm the internalization of piece and piece in presence of phenanthrene, we perform confocal macroscopy assays. We show the membrane in red, the nucleus in blue, and nanoplastics piece and piece in green. And we can confirm in the image on the right side that the piece and piece uptake internalization increase in the presence of phenanthrene. Another of the parameters commonly measured relation to a spore of polycyclic aromatic hydrocarbons is the bioaccumulation and quantification of metabolites. Here we can observe that in presence of phenanthrene, so we can observe that the concentration of phenanthrene tends to be accumulated in all the treatments. When we co-expose to cells to phenanthrene, and when we co-expose to cells with phenanthrene plus nanoplastics in different concentrations, 10 milligrams liter and 50 milligrams liter. And when we evaluate the metabolites of phenanthrene, we can observe that we detect more metabolites in presence of piece and piece, marked in green to 50 milligrams liter and in orange, 10 milligrams liter. And we did the same approach in intestinal epithelial cells. And here we can observe that here we can observe that in presence of phenanthren, decrease the Pis and Pis uptake. On the other hand, we can observe that the mean fluorescence intensity is higher when the cells were not co-exposed to Pis and Pis plus phenanthren. And the same by VDUV cell technology, we can confirm that the uptake of Pis and Pis decrease in the presence of phenanthren. In this case, with the intestinal epithelial cells, we can observe that the concentration of phenanthren tends to be accumulated also, but here we did not detect metabolites. Polycyclic aromatic hydrocarbons are ubiquitous pollutants present in the water, air, and even in foods. To obtain more information that fits into our growing understanding on the phase of copulant interaction and ecotoxic effects, we employ zebrafish larvae. We obtain embryons, zebrafish embryons, and once hatched, we co-expose in a 96 plate to different concentrations of phenanthren plus nanoplastics. And 24 hours, we evaluate the survival percentage and lethal concentration 50. And we observe that the mortality rate decreased in presence of phenanthren. In presence of nanoplastics. When we co-expose the cells to phenanthren plus nanoplastics, we observe that the mortality rate decreased. And the lethal concentration is higher when we co-expose the cells to phenanthren plus nanoplastics. And we also evaluate the uptake in zebrafish larvae, and we can observe that the Pis and Pis uptake decrease in presence of phenanthren, the same that intestinal epithelial cells. And remembering our main hypothesis about the interaction between nanoplastics and phenanthren and how they could modulate the ecotoxic effects in aquatic organisms, in a summary, we conclude that Pis and Pis plus phenanthren decrease in intestinal cells and zebrafish larvae, while increasing in liver cells. And additionally, the presence of Pis and Pis led to lower levels of phenanthren toxicity in zebrafish larvae. Pis and Pis influence the xenobiotics metabolism. High amounts of phenanthren metabolites were detected in liver cells. And as a general conclusion, we can say that the ecotoxic effects of copulant interaction are cell type specific and tissue dependent. Of course, long-term studies are needed for a comprehensive risk assessment. This is my team, and thank you very much for your attention.
Thank you very much. We have time for one, maximum 2 questions.
Hi, thank you for your talk. I was wondering, in your cell studies, when you see that this phenanthren enters into the cell, do you have any viability studies about these cells?
Yes, of course.
So they die? Or?
Yes, of course. We use non-lethal concentrations for the cells, and the concentration that we use is not generate mortality in cells. We don't show the results, but we did the toxicology.
So at any concentrations they die?
Not that we use. After 50 is when the cells start to die.
Okay.
Yeah, not to this concentration of 50 to zebrafish liver cells, and 25 to intestinal 50, and 25 to intestinal epithelial cells.
Okay. Yes. Okay. Thank you.
You're welcome.
Thank you very much.
Hola. ¿Se oye? Hola. Sí. Bueno, vamos a dar comienzo a la segunda parte de la sesión de hoy. Esta está más centrada en el occurrence de la presencia de microplastics y nuestra primera speaker es Lara Cioni con la presentación de Human Exposure to Plastic Additives through Menstrual Products Use. A los speakers de esta parte, por favor, intentar centraros bien en el tiempo, porque si no, a las 2:30 nos echan de la sala.
Thank you. Okay, hi everyone. So until now we heard a lot about the environmental impacts of plastic pollution. In this presentation I will focus more on the human exposure side, and I will present part of the group of the work that we are doing in our group about human exposure through the use of menstrual products. So why menstrual products? Menstruation is a process experienced by half of the world population, and these products are very important to maintain hygiene, prevent infections, and also allow participation in occupational and educational activities. However, some of these products have been shown to contain chemicals of concern for human health. And from a human exposure perspective, this is of interest because the vulvar and vaginal tissues in contact with these products have a high capacity for chemical absorption. And also these products are used during the fertile stages of life, which might be a time frame that is sensitive for human exposure. Among the chemicals that we can find in menstrual products, there are phthalates, which are a class of plastic additives which have been gaining attention because of their endocrine disrupting properties. But as we heard during these days, there are a wide variety of plastic additives. We count as many substances as in the range of thousands. But the majority of these is still not studied in menstrual products. So we decided to focus on two additional classes of plastic additives, which are the organophosphate esters, which have also been gaining attention because their endocrine disrupting effects, and then the alternative plastic additives, which have been increasingly used as substitutes to phthalates and organophosphate esters, but which toxicological properties are still not known so good. And among these additives, we have different types of structures. We have citrates, adipates, and trimethylates. So the goal of our study was to improve our understanding of human exposure to plastic additives through the use of menstrual products. And to do this, the first thing that we wanted to do was to evaluate the occurrence of three classes of plastic additives, the phthalates, the organophosphate esters, and the alternative plastic additives in different types of menstrual products. After this, we wanted to estimate the contribution of dermal contact with menstrual products to human exposure to plastic additives. And lastly, we wanted to evaluate the potential health risks that could be associated with the use of these products. To do this, we collected menstrual products to cover different classes of products, and we decided to cover both single-use and reusable products. So among the single-use, we had sanitary pads, panty liners, and tampons. Among the reusable ones, we had reusable sanitary pads, menstrual panties, and menstrual cups. And to analyze these products, we had to select a portion of each of these products. So to obtain a representative samples for the sanitary pads, the panty liners, and the menstrual panties, we cut 4 square pieces of 1 square centimeters from different parts of the product. While for tampons and menstrual cup, we cut the products in small pieces and randomly selected the pieces and weighed them in an extraction tube to reach a weight of 0.1 gram. The extraction was performed by ultrasonication with hexane acetone 1:1, and the extracts were filtered with glass wool to remove large fibers. After this, the extracts were evaporated and reconstituted in methanol. We analyzed the samples with LC triple quad for 8 phthalates, 17 organophosphate esters, and 10 alternative plastic additives. After this, we wanted to calculate the contribution of thermal contact to human exposure. So to do this, we calculated the estimated daily intakes. And to do this, we take into account different parameters. So the first parameter that we take into account is the concentration of plastic additives expressed in nanogram per product. Then we have two parameters that are describing our habits of use of these products, so the number of products that we use in a day and the number of hours for which we wear each of these products. And then we have two factors describing how thermal exposure is happening. So the first one is the ERF, which is the easily releasable fraction, meaning the fraction of plastic additive that from the menstrual product can reach our skin. And the second one is the absorption factor, which is the fraction of plastic additives that from our skin can enter our body. And for these two factors, there is no data available in the literature, so we assume the worst case scenario, so 100% release and 100% absorption. Then the other factor that we are taking into account is the body weight, that in this case was the average body weight of women in Spain, and we averaged this over 24 hours. This factor, the EDI, was also used to estimate potential risk for human health in terms of non-carcinogenic and carcinogenic effects. And to do this, we compared the EDIs to reference values established by the US EPA. So what did we find in these products? So here in this slide, I'm showing you the detection frequencies for phthalates, organophosphate esters, and alternative plastic additives in the different categories of products that we analyze. So if we start by looking at the phthalates, we can see that high detection frequencies between 90 to 100% were observed in most of the products, except tampons and menstrual panties, where the detection frequencies were a bit lower. For the organophosphate esters, here the detection frequencies are higher in most of the products, but in the menstrual cups, we detect these compounds only in one of the 6 products that we analyzed. And lastly, if we look at the alternative plastic additives, we see that these compounds were detected in 100% of the products that we analyzed. And this is probably reflecting a more widespread use of these chemicals. What happens when we look at concentrations? So for phthalates and organophosphate esters, the highest concentrations are found in the reusable sanitary pads, with concentrations up to 40 microgram per gram for phthalates and up to 4 microgram per gram for organophosphate esters. For the other products, the concentrations are much lower, at least 1 order or 2 order of magnitude lower. And at first, we were a bit surprised about these results because we were expecting the highest concentrations of these compounds to show up in the single-use sanitary pads and the panty liners, since these contain in their design 1 or more layer of plastics. But some of these chemicals are also used to make textiles waterproof, and reusable sanitary pads often contain in their design a waterproof layer. So this might be an explanation for these differences. If we look at the alternative plastic additives, here the situation is a bit different, and the highest concentrations are found in the single-use sanitary pads and in the panty liners, with concentrations reaching up to 10 microgram per gram. In the other products, the concentrations were at least 2 or 3 order of magnitude lower. When we put all this together, we can see there are clear differences in the total of plastic additives among different products. And if we look at the contribution of each class of plastic additive to the total, we can see that the alternative plastic additives are dominating in the majority of products that we analyzed, probably reflecting their more widespread use. And we also observed that phthalates are often found in higher concentrations than the organophosphate esters, and this is all consistent with what is observed for other types of consumer products. Here in this slide, I'm showing you the profiles of the different classes of plastic additives. I will not discuss this in details, but what you can see is that different profiles are observed for different types of products, and we think that this might be related to differences in product design. So as I was mentioning earlier, the single-use sanitary pads and panty liners contain 1 or more layer of plastics. Then we have the tampons that are only made of an absorbent material. We have then the reusable sanitary pads and the menstrual panties that are made of textiles, and the menstrual cups that are made of plastic or silicone. So these differences in design might reflect the differences that we observe in the profiles. After this, we wanted to estimate the contribution of dermal contact with menstrual products to human exposure. So here in this slide, I'm reporting for each class of plastic additive, the average estimated daily intake for each class of product, and comparing it to EDIs reported in the literature for other routes of exposure to plastic additives. So if we start by looking at the phthalates, the highest studies were observed for the reusable sanitary pads. And we can see that these estimates are lower than estimates for the major route of exposure, which is considered the diet, but higher than other important exposure sources for phthalates, such as the intake through beverages, inhalation of air, dust ingestion, and dermal contact with dust. If we then move to look into the organophosphate esters, here the highest estimates are found for the reusable sanitary pad and the menstrual panties. And in this case, we can see that these estimates are actually higher than the intake through the diet, which is considered the main route of exposure. For the other products, the estimates are much lower, but in some cases comparable to other important route of exposure. Looking at the alternative plastic additives, here it's a bit harder to make a comparison because exposure to these additives is less studied, so we have less data available in the literature. And we can see that at least comparing through the diet, the estimates for dermal contact with menstrual products are much lower. But what I want to stress here is that these are all worst case scenario estimates, so real life situation will probably be much lower than this, but we need more data to probably describe the dermal exposure. If we then put this into the context of risk assessment, for non-carcinogenic risk, we observe that the concentrations of plastic additives in these products were well below the threshold for this kind of effects for all classes of products. But if we look at this in terms of carcinogenic risk, here we have that all the reusable sanitary pads, all the menstrual panties, and one menstrual cup and two of the single-use sanitary pads were above the threshold for carcinogenic risk. But again, here I want to remind you these are worst-case scenario estimates, but I think these results are showing us that we need more efforts to better understand the safety of these products. So to conclude, phthalates, organophosphate esters, and alternative plastic additives were detected in all types of menstrual products. The alternatives were found in the highest concentrations in most of the products, probably reflecting their more widespread use. And phthalates were in general found in higher concentrations than organophosphate esters. For all the classes of plastic additives, the concentrations and profiles differed significantly between different menstrual products, probably reflecting their differences in design. And if we put all this together, we can see that plastic additives exposure through dermal contact with menstrual products might be a significant route of exposure and might actually pose risks for human health. But we need better estimates to assess the real-life situation. And to do this, we need more data, especially understanding how dermal exposure is working. So with this, I would like to thank my co-authors, the institutions that you can see in this slide for the funding, and I'm happy to take any questions. Thank you.
Thank you, Lara, for your very nice presentation. So there is a question right here.
Hi, very interesting presentation. I would like to know if you try different brands. And also, another question is if the reusable pads are made also with some plastic, or the additives are coming from the tissue. I didn't get this.
Yes, so I didn't mention it, but during the sampling we try to collect more products for each type, and we paid particular attention like to cover different types of brand, because the idea was to see more if this was a generalized problem for each product rather than looking at individual ones. And the second question,
if the reusable pads are made of plastic as well, or the additives are coming from the tissue?
I would need to check that, but I think most of them are actually made of cotton, or at least it says that in the description. So I'm hypothesizing that the additives are rather like added to the textile to give them technical properties, such the waterproof properties. Yeah.
Okay, thank you.
Any other question?
Yes. I'm wondering if the reusable pads, if they are reused, do they lose the additives over time?
Yeah, I think that's a very good question. Would be very good to know this, but I'm expecting as well. I mean, we saw it with yesterday's presentation during laundry. It is possible that microplastics are released, but we know also plastic additives can be released. So I'm expecting that some of the content that we see will be released during washing. The thing that I'm also wondering if, like, the more you wash, is it then that is released more once we use it? So I think there's still a lot to figure out here. Yeah.
Any other question? No?
Yeah, nice presentation. As you said, this is the worst case scenario, so you extracted all the additives present there. Are you planning to test in a, let's say, real case scenario? Because some of the items could affect differently, no? So some of them will be in contact with the mucosa, and other ones outside. So this will be really interesting also, because at the end is the how it can be affected, no?
Yeah, I agree, and that's actually something that we are working on. We are working on developing a model that simulates the skin, so to see if conditions such as the presence of sweat, sebum, and other vaginal fluids could influence the release of these chemicals. So yeah, I think that's what is really missing to assess the contribution of this pathway, and if the content of plastic additive could pose a risk. Yeah.
Thank you very much. If there is no other question, we move. Yeah?
So thank you for your presentation. I have a question. If we do a press release of these results, because they are very interesting, and people ask us, what do we have as an alternative of these products if there are plastic in these products and metals? Mm-hmm. What do you say?
I mean, I would say that with these results, I mean, this is just another pathway that is contributing to human exposure. But we need these products. It's a bit like saying, like, do we stop eating because we know there is plastic additives in our food? We cannot really stop using these products. I think people need to have this information, because then maybe they can decide using a product rather than another one. But as well, there are other factors that play when you decide which menstrual product you want to use. So I think like if we communicate to this to the public, it's important that we show that this is not something that we need to be scared of. It's just another pathway, and we need to be aware of it. But I would say there's nothing we can do to avoid it completely. Yeah.
Okay, thank you.
Okay, thank you very much, Lara, again. So, the next speaker is Nicola Montemurro from IDAEA-CSIC, which is going to present his work about tracking tire-related chemicals in the Llobregat Delta area, Barcelona, Spain.
Hello, everyone. Thank you for your kind introduction, and thank you for allowing me to present these preliminary data about our project. Well, I just want to spend a couple of words regarding plastic. For me, plastic is amazing. Okay, we are talking about bad plastic, but I cannot imagine my daily life without plastic. So, What is the main problem of the plastic, of course, is the not correct use and production of waste. Maybe you have to be more conscientious on these 2 points. Yesterday we talked about synthetic fibers, synthetic textile, that they are the main sources of microplastic. By the way, at the second place we can find tire wear particles. Yesterday we talked about that 1.5 billion to 2 billion of vehicles are running our roads every day, every year. Well, about 2/3 of these vehicles are common utility cars. The 25% are motorcycle, just the 3% is heavy trucks. As the consequence, there is a lot of production of tire wear particles. Well, if you consider that most of these tire wear particles are produced in North America and Europe, and the percentage is about the 20% of all the total microplastics produced every year, and that can reach the ocean. Compared with India or South Asia or China, that the main problem is synthetic fibers. Well, the problem of tire wear particles that are generated during the abrasion on the road. Just yesterday we also learned that one of the most important factors for a very good tire is the adherence with the asphalt. But of course, during this event, the number of particles, well, there is a production of these particles. But once produced, these particles can reach the wastewater treatment plant or are dispersed by the wind very far from the highway and reach the environment. Well, but what is the main problem? The main problem is related to the tear-related additives. One of the most famous additives is the 6-ppd quinone that is produced by oxidation of 6-ppd, that is an antioxidant that is added to the tire wear particle to the tire to prevent oxidation of the tire. Of course, yesterday Continental don't talk about this additive because maybe Continental is one of the producers that less use this additive compared with the Pirelli, that is the most consumer of this additive. Well, of course, what is the problem? That we need to add this additive because this is the tire with the 6-ppd, and this is a tire without the 6-ppd. This is very important to prevent and to save our lives when we are in our cars. But the main problem is that 6-ppd is very toxic for fish, but just to be honest, the main problem is just the coho salmon in Canada. Of course, the tire wear particles and additives are also toxic for human health. Most classic contaminants could be polycyclic polyaromatic hydrocarbons or benzothiazoles, isoprene, of course, heavy metals. All these contaminants, including tire wear particles, can accumulate in the environment and manifest during the food chain, or we can also breathe these tire wear particles, And just a recent study confirmed the presence of 6-PPD and 6-PPD quinone in pregnant women, child, and adult urine. Okay, the objective of our project, the Transit project, was to identify and prioritize these styrelated additives in the area of Barcelona, very close to the airport in the Llobregat Delta, and assess the potential impact of and toxicity of this contaminant in environment, such as water, fish, and macroinvertebrates from the natural area, and also in workers and people from this area. And well, the area of the study is the Delta of Llobregat. That is a huge area of almost 100 square kilometers. Inside this area, there is the airport of Barcelona El Prat. This is a very important connection of different habitats, because we have natural areas such as the Filipinas remolar or the Ricarda Pond. We have also the Roberta Pond. We have the Parc Agrari of Barcelona, but we have also the influence of the logistic activities zone, the wastewater treatment plant. There is a huge net of highways and connected with irrigation channels, so it's a very complicated area. We selected 25 locations, and the first sampling was conducted at the beginning of this year in January, February, and March. In January during the dry period, in February with not so heavy rain, and in March with a very heavy rain event. And okay, just some photos of the different points that we sampled, because each point is totally different from the other one. Also during the time, because of course in this case we have we sampled the river, the Llobregat River, very close to the bridges of the main highways. And for example, this is an irrigation channel that just passed through below the bridge, and here, for example, is a point that we collected directly from the leakage of the bridge inside. So this, for in this case, it was impossible to collect this sample during the dry period. And this point is very connected to the river, as you can see. Also, in this case, we are in the natural area. This is from the Roberta natural area, La Ricarda natural area, and the Filipinas remolar. As you can see in this point, we also find that the presence of tire in natural area is constant. And another problem that we found at the difference between the seasons. For example, this photo is from March, and this is from September, end of August, September. So this scenario was totally different. And these are my favorite points. As you can see, this is another bridge where we were sampled water during the rain event. Or in this case, we also again collected the water just directly from the asphalt. And this is another channel that across all the Parc Agrari. And of course, also in this case, the scenario was different from for example, February and September, that we performed a new sampling campaign. As you can see, again, the presence of tire in general is very common. Well, this is the methodology. We took water samples, just in this case. This is the workflow, the extraction for water. We just use a solid phase extraction. If you want more details, there is the poster of Francesca De Angelis in the hall. And regarding the analysis, well, I performed the analysis during my stay in Athens this spring, funded by Jose Castillejo fellowship, and I had the opportunity to use team stuff with ion mobility. I performed a wide scope target analysis for about 3,000 compounds. So the idea was to perform a screening not only on tire additives, but just to understand the healthy state of all the area. The samples were injected into acquisition mode different in data independent acquisition to perform target analysis, and data dependent acquisition for a following non-target analysis. The data were processed with target screened 4D, and more details are in the poster. For the preliminary screens, we detected almost 300 compounds, so not only the additives. Most of these compounds are from the river, and they are pesticide, pharmaceutical and personal care products. But we also find a lot of pesticides. And of course, we found more or less 82 industrial compounds. 24 of them are tire additives that we quantified with a genuine analytical standard. This is just an example of extracted ion chromatogram and mobilogram from a real sample of diphenyl guanidine. For this presentation, I just present not all the 50 compounds, just 10 compounds. They are vulcanization agents, antioxidants, or anti-corrosive or UV inhibitors, or well, this is the main problem that we have. It was to compare all these results, because, of course, as you can see, the sampling points are very different from between them. So for this just exercise, I presented just 10 compounds. As you can see, the first three, this is the summary of all compounds and all points separated for the 3 periods of sampling. As you can see, the first 3 are La Ricarda, La Roberta, and El Remolar, that are the natural area. In the case of La Roberta, well, there is a trend with during the rain events, so the concentrations tends to increase during the rain, just because La Ricarda is isolated from the Llobregat River, but is very, very close, very connected with the tracks of the airport. We have to consider that not just the impact of the tires from the flights, but of course we have to consider that the airport of Barcelona is like a small city with a lot of cars inside. And in the case of La Roberta, we can see a different trend because also La Roberta is totally isolated from the river and from the highways, but in this case the dilution effect is due to the rain event. In the case of Remolar, there is a first increase of the compounds during the first rain event, but of course the Remolar is very connected to the river with the streams, the channels. So what happened in this case that during the heavy rain event there is a sort of dilution of these compounds. And of course, the most interesting point is the leaky from the bridge where we found a very high concentration of these compounds. Well, the compounds with high accumulation or high presence are diphenyl guanidine, of course, the vulcanization agent. Followed by 5-methylbenzotriazoles and HMMM. And on the right, you can see the frequency of detection. So the frequency, we can find this compound in almost in all points during the 3 events. And just to conclude that, what I already said, that in this area we can find, of course, tire additives, but there are a lot of other contaminants. And diphenyl guanidine, 5-methylbenzotriazole, and HMMM are the compounds with the highest concentration and detection frequency. 6-ppd quinone was found so only at very low concentration. And of course, ion mobility increased a lot the confidence in compound annotation compared with the LC-MSS method. And well, I will work on target analysis and try to conclude all the work. And nothing. Thank you.
Thanks, Nicola, for this nice presentation. There is time for one quick question. There is someone here.
There's a question.
Hi, thanks for the presentation. I have a curiosity about the future non-target work. How are you going to approach this problem? Because I feel that sometimes it's very difficult to know which chemicals are used for which application. So is there any database that contains chemicals that are used as additive for tires, or how are you going to build the list of chemicals that you're going to look for?
I not really start with the untarget in this moment. The idea was to continue with the collaboration with the University of Athens, that they have several algorithms and software to do the untarget analysis. And of course, they collaborate with the Norman network. So I think that the idea was to process all this data with the Norman databases.
Thank you.
Thanks, Nicola.
Thank you.
We will pass to the next speaker because... Thanks. Well, our next speaker is Daniel Rozuo from IDAEA-CSIC, and he will present the analysis of plasticizers in potential inhalable particles from recycled rubber flooring in playgrounds and sport facilities.
Thank you. Well, as she said, I'm Daniel Rozuo. I come from the Institute of Environmental Assessment and Water Research. And this presentation is about the analysis of plasticizers in potential inhalable particles from recycled rubber flooring in playgrounds and sports facilities. The production of chrome rubber is one of the most common and profitable ways of recycling rubber. This process uses old tires to produce a material called styrene butadiene elastomer made by the grinding of end-of-life tires and their devulcanization. It is important to note that this material contains all the additives that tires have, some of which are known to be carcinogenic in nature. These are the compounds that we studied, grouped in 7 different families in 3 different categories. So, plasticizers are compounds used to give rubber more elasticity and durability. And the families that we studied are the organophosphate esters, or OPEs, phthalate plasticizers, and non-phthalate alternative plasticizers. Flame retardants are used to reduce rubber's flammability, and the families that we studied are the polybrominated diphenyl ethers, or PBDs, and emergent brominated flame retardants as well, and the chlorines. Chloroparaffins give both plasticizing and flame retarding properties to rubber and are a wide family of compounds consisting of alkylic chains with varying length and degree of chlorination. So, recycled rubber, or SBE, is typically used as a base layer when making artificial rubber flooring for playgrounds and running tracks. This base is then covered by a layer of a synthetic rubber, not recycled, which is EPDM. So, yeah. However, this recycled rubber-only flooring can also be found commercially. These materials, especially when outdoors, are subjected to erosion and degradation by the action of the sun, the rain, the wind, and human activity. This degradation can form small rubber particles, some of which are small enough to be absorbed by the human body. PM2.5, that is, particles with a diameter of 2.5 microns or less, are small enough to be inhaled. However, the particles that we are studying are particles deposited on the surface of this rubber flooring. That means that they are not airborne, and therefore they are what we call potentially inhalable particles. Bigger size particles like PM10 also contribute to human exposure by way of ingestion and thermal contact. So, we sampled these potentially inhalable particles, PM2.5, which is the aim of this study, with this instrument that you can see here that was patented by our institute. This is a resuspension chamber that is connected to a vacuum pump that produces a negative pressure that makes air go inside the chamber through the sampling tube. This air then carries with it all the particles that could be deposited in this surface. And inside the resuspension chamber, if a flow of 7 liters per minute is used, we make this chamber separate PM2.5 from the rest particles of all different sizes. PM2.5 then deposits in a quartz fiber filter found in the filter chamber that can be then digested or extracted to see the contaminants found in these particles. Here is the sampling campaign that we did. We sampled a total of 8 different locations in Barcelona, 5 of which were playgrounds with synthetic rubber flooring, and 3 running tracks. We used 2 different methods of analysis and extraction. Plasticizers were extracted with an ultrasound extraction followed by an evaporation under nitrogen current and a reconstitution with methanol, then analyzed by liquid chromatography coupled to mass spectrometry. Flame retardants and chloroparaffins were extracted in more or less the same way, but adding an extra step of a solid phase extraction cleanup. These were evaporated and reconstituted. Here's an error, it's not methanol, it's toluene. PBDs and emergents were analyzed with gas chromatography with electronic ionization coupled to mass spectrometry, the chlorines with chemical ionization, and chloroparafins with negative ion chemical ionization. Here is a summary of the results that we obtained. The units that you can see here are in nanograms per square meter of floor sampled. And, for example, flame retardants, well, most compounds analyzed were not detected, and in the particular case of emergent brominated flame retardants and the chlorines, they were not detected in any samples. Here you can see this data in a logarithmic scale. And as you can see, the families that were detected at the highest concentrations are phthalate plasticizers and non-phthalate plasticizers. The case of phthalate plasticizers, particularly the case of a compound called diisononyl phthalate, was found at almost 3,000 nanograms per square meter. Other alternatives were also found at high concentrations, as well as chloroparafins that were found at around 200 nanograms per square meter, and OPs and PBDs were found at around 20 nanograms per square meter. Here you can see the same, but comparing playgrounds with running tracks. Now, we don't have enough data to make a statistical treatment of this, but more or less we can see that running tracks kind of have a higher concentration of the aforementioned families with respect to playgrounds. Now, with this data, we can make an estimate daily intake, assuming that for each square meter analyzed, all potentially inhalable particles were to resuspend in a cubic meter of air. Using this formula that you can see here, the estimate daily intake, we can calculate the risk associated with these particles. We used both the child and adult average breathing ratio as well as the average body weight, and we assumed a daily exposure to these parks of an hour daily. These preliminary estimate daily intake studies would give us information about the worst case scenario regarding the exposition to these particles. Here you can see all the compounds that were analyzed. Those marked in red are the ones that have a maximum recommended intake value given by the American Environmental Protection Agency. And here you can see the ways to calculate both the non-carcinogenic and carcinogenic risk associated with these compounds. Luckily, risks are orders of magnitude below the maximum recommended value, and taking into account this is a worst case scenario, we can see that the risk associated by inhaling these particles is, well, it is concerning, but is not an immediate threat. So, to sum up, the use of this resuspension chamber allowed for the detection and quantitation of these different families of plasticizers, flame retardants, and chloroparafins. All three plasticizer families were detected at, phthalates and non-phthalate plasticizers were detected at high concentrations, at 3,000 and 1,000 nanograms per square meter respectively on average, whereas OPEs were detected at about 20 nanograms per square meter. Other families were detected as well, for example, PBDs at about 20 nanograms per square meter and chloroparafins at 200. And emergent brominated flame retardants and the chlorines were not found in any samples. These preliminary estimate daily intake studies that we did seem to indicate that there is neither carcinogenic nor non-carcinogenic risk associated with the theoretical resuspension of these potential inhalable particles. However, it's important to note that this is only one of the many different exposition routes that we find throughout the day. Also, we have to take into account that these parks are also related to exposition by ingestion and dermal contact. Here you can see three different ways in which we want to expand this research. First of all, we want to find an association between the concentration of potentially inhalable particles deposited in rubber surfaces and the respective airborne particles found in the nearby air, and whether there's a mathematical model that can associate them both. As I said, ingestion and thermal contact studies are important regarding this subject, and we want to further expand this research in this way because the instrument that we use to sample PM 2.5 particles also allows us to sample PM 10 particles. And finally, we want to do studies over time to see whether the degradation of these materials actually makes these contaminants appear in higher or lower concentrations with time. And that's it. Thank you.
Thank you very much, Daniel, for your presentation. Is there any question? I want to ask a question because I saw that in the sampling points there were some that were parks that were installed like in 2006, others in 2023. Yeah. You see any differences in terms of concentrations in parks that were installed before?
We couldn't find a relationship between the age of these materials, but we also have to take into account that we are working with a small number of samples. And these studies over time, we would like to make several repetitions on the same parks to check exactly this effect, because these materials are found in different places of Barcelona and could be subjected to many different forms of nearby contamination or different activities that could erode them in different ways.
Thank you. No question? Okay. Thank you very much, Daniel. So now is the turn of Nora Expósito from the Universitat Rovira Virgili, which is going to talk about the effect of depuration time on microplastic level in edible mollusks.
Okay, good afternoon. Thank you for being here still. Okay. Our study, the principal objective was to estimate the microplastic removal rate for improvement of depurations process by modifying the depuration time station in real commercial facility for depuration with edible mollusk. At the same time, to measure the effect of depuration time in morphology, size, and composition. This is a useful information for policymakers. Okay. Why we started edible mollusk? Well, we all us know that mollusks are filter feeding behavior, have filter feeding behavior in seawater. Concentrate a big volume of seawater may be contaminated with microplastic, concentrate them a lot. All of mollusks are consumed as a whole, and the mollusks are a route of human exposure to microplastic with human health issues concern. Okay. Our methodology. All of the edible mollusks coming from Catalonia southern zone, from Delta del Ebro, and the depuration facilities were there. And the edible mollusk study were mussels, the typical mussel from the Delta, oyster, the big oyster, and tellerina or wedge clam. Okay. 3 types of assays were established: no depurate, standard depuration, and extended depuration. For no depuration, we have 3 replicates or samples. For mussel, 20 individuals and 56 grams. Standard depuration for mussel, 24 hours, the same as the no depuration. And extended depuration, 48 hours. In case of oyster, we put in 3 replicates also and 7 individual replicates and 144 grams per sample. 72 hours for standard depuration and 96 hours for standard depuration. Similar to the others, the wedget clan, we put 100, because they are very, very small, 148 grams, 3 replicates per depuration size, standard depuration for 2 hours, and standard depuration 5 hours. It's important to highlight that the wedget clan is not mandatory by legislation to depurate. We established this time in order for comparison purpose with an older mollusk, okay? The total, we analyzed 1,100 organisms. You look at very simple design, but it's very, very hard work, okay? And very useful information. Okay, for a microplastic extraction, we use this methodology. We make alkaline digestion with with enzymatic digestion with agitation and temperature, peroxide oxidation, phantom sonication, and extra enzymatic digestion with density separation. Okay, we made control, of course, procedure control with less 10 microplastic between fibers and particles, and we calculate the recovery rate with pattern of polyethylene spheres of polyethylene, very, very smooth. We obtain recovery rates from 60% for 53 micrometers to 99% for 500 micrometers. Okay, for microplastic composition and measure for each mollusk type, we take all of the microplastic that we found for 3 replicate and put on calcium fluoride slice in a 1 centimeter square for analyzed composition in micro-EFT air. Okay, for spectral analysis. Okay, for each mollusk, okay, we made the same. Our results, according to microplastic level, we observe a reduction of 50% in standard depuration for mussels, referenced by individual, okay? But in standard depuration 48 hours, we observe an increase with significant difference between standard depuration and no depuration, okay? Similar to microplastic by individual, we observe that by fresh way, we observe an increase, okay? The total reduction was 46% in case of mussels. According to microplastic composition, we observe that the fiber in each depuration size had similar composition with things only in the proportion in cellulose, synthetic cellulose, polyamide, and polyester, okay? Instead, or by contrast, in mussel particle composition, the polyethylene decreased across the depuration size, and the diversity of the and the polymeric diversity increased, okay? In that case. In case of oyster microplastic level, the reduction was 26% from standard depuration, 72 hours, and 23% in 96 hours, okay? In that case, we don't observe a significant difference between them because we had a high variability in the organism's microplastic. The total reduction was 43%. As other mollusks, we observed that the fibers were the morphology predominant, okay, the mussels and oyster. In that case, referenced by individual, we don't observe significant difference. By reference by fresh way, we observe a reduction of 37% for standard depuration plus a 28% for extended depuration, with a total of 55%, with these different were significant, okay? According to microplastic composition, again, in case of oyster, we observe that the fibers change the proportion, but not change so much in composition, okay? And meanwhile, that the oyster particles, we observe that the polyethylene disappear in depuration size and appear new polymer, polystyrene, and polymer with fluor with high proportion. The polypropylene in that case increased in extended depuration. Microplastic level in Tellerinas or wetland, we observe a reduction again in standard depuration, 26%. For extended depuration, a little extra reduction of 8%, and the total 32%. We observe that the depuration processes were designed for microplastic removal, but even we have a sort of removal when you apply depuration, okay? Again, as a mussel, we observe that by fresh way, standard depuration and extended depuration don't have so much difference. Even we observe that they increase, okay? Again, the fibers were on the most predominant morphology. Microplastic composition, again for fibers, polyester, cellulose, synthetic cellulose, and polyamide were again the predominant, with change some proportion. And the polymeric diversity decreased for extended depuration with increase again of polypropylene. Okay. According to microplastic size, we observe that the longest fibers were found in oyster. Look, okay, and the average microplastic size seems don't change between depuration and size. Okay. The average of microplastic size was around 1 millimeters, including the definition of microplastic. But in the standard depuration, oyster increased the size with include in the large microplastic concept, okay, or definition. All of the size were around 1 millimeters, okay? This is average. This is because mainly the morphology predominant was fiber. Here are the summary, the results. The significant difference were obtained in mussels by individual and by fresh way. In oyster, only fresh way. We observed reduction, but it was not significant. According to the microplastic ingestion by population, we calculate with EFSA data for mollusk intake by Spanish adult, the microplastic ingestion and the yearly ingestion for non-depurate organisms. We obtain a 4,600 microplastic per year, corresponding at a fiber length of 4.5 meter per year, okay? If we observe the standard depuration values, the values decrease by half in 2,500 and correspond to a fiber length of 2 meters, 0.4, okay? This is almost the half. the contribution of each mollusk of this value, it was obvious that mussels have the higher contribution of these values. Okay. Conclusion: the levels of microplastic decrease between nodapurate mollusks and subject to a standard depuration. Even these processes were designed for microplastic removal. Okay, only mussels show significant difference. In terms of fresh weight, oysters show a significant difference by fresh weight, but I think that we need more research, further research in oysters to conclude if standard depuration and the standard depuration is necessary, equilibrating the cost of benefits. It means that equilibrating the quality of product and microplastic removal for human health protection. Okay. The standard depuration does not significantly reduce the microplastic level in mussel and wedged clam. The average size of microplastic in depuration size does not appear to change significantly. We have a less microplastic quantity, but it seems that the size remains at the same average. Okay. We are consuming the length of the fiber with no depurate organisms, about 45 meters of fiber. This is very, very long. With standard depurate organisms, if we consume a standard depurate mollusk, only consume the half. Okay. This is my kit, that big, very, very good equipment, and thank you for your attention.
Thanks, Nora, for this interesting presentation. There is any question here? No? I have one, because maybe I didn't catch it when you explained it, but these mollusks were exposed to different types of microplastics, or these are real?
No, it's real. The mollusks coming from the facility commercial and the fishing company, okay? The mollusks, when arrived to the laboratory, we wash with ultra pure water in order to eliminate any other microplastic attached external from the mollusk, and the vessels treated were removed only for external. Okay, there was the same string of mussel were put in different time of depuration, but the person who made this were the same person that operate the facility of depuration. In this case, it's real microplastic from the environment. We don't have any experiment with microplastic put in the depuration facilities.
Okay, and the analysis of the mollusk is just the edible part, or also the water which is inside of the shells? Did you?
I know the shell were removed also.
But the water inside was also discarded?
Yes, discarded, yes. Only attached in the stomach.
In the gastrointestinal,
yes,
or wherever?
intern, yes.
Okay, well, thanks. I don't know if there is any question. Well, if not, thank you, Nora. And now it's time for our next speaker, which is Andrea Barrientos, also from Universitat Rovira y Virgili, who's going to present presencia de microplásticos en agua, refrescos y otras bebidas.
Bueno, hola. Uy, ¿qué es esto? Bueno, mi nombre es Andrea Barrientos y soy estudiante predoctoral de primer año del grupo Tecnatox, y os quería presentar el proyecto que estamos llevando a cabo ahora muy recientemente, que es presencia de microplásticos en agua y diferentes refrescos. En primer lugar, los plásticos, bueno, como ya sabemos, tienen una unas altas capacidades metálicas, bajo peso, mucha durabilidad, por eso nos hacen utilizarlos muchísimo en la industria. Entonces, la demanda prima de materias plásticas ha aumentado mucho a lo largo de los años, llegando a cantidades extremadamente elevadas, como son esos 400,3 toneladas. Además, muchos estudios establecen una estimación que, si seguimos así, estas materias plásticas se van a seguir utilizando hasta cantidades que no son sostenibles. Es por eso que, gracias a nuestro uso, el plástico se está convirtiendo en uno de los problemas medioambientales más grandes de nuestro siglo, por lo que necesitamos acciones para regularlo. Hemos visto que los microplásticos en nuestro planeta, los plásticos en nuestro planeta se pueden dividir por tamaño en macroplásticos, microplásticos y nanoplásticos. Los microplásticos no hay una definición establecida, pero la más aceptada es que son cualquier partícula sintética o semisintética de un tamaño entre 1 micrómetro y 5 milímetros, de origen primario o secundario de fabricación e insoluble en agua. Según su morfología, se clasifican principalmente en las fibras, fragmentos, films y pellets. Los microplásticos, la vía de exposición principal que tenemos a ellos es mediante la ingestión. Lo que vemos es que nos estamos ingiriendo más o menos unas 883 partículas por persona al día, y lo bueno es que un 90% de estos microplásticos son excretados, pero el problema está en las partículas más pequeñas. Partículas menores de 150 micrómetros pueden atravesar el epitelio intestinal, menores de 2,5 pueden entrar en nuestra circulación sistémica por endocitosis, y de 0,1 a 10 micrómetros pueden incluso atravesar tanto la barrera hematoencefálica como la placenta. Por lo que estamos expuestos a ellos, no solo por la ingestión, sino por la inhalación y por contacto dérmico, y estos, aparte de sus propiedades físicas como su tamaño, su superficie, su composición, lo que van a hacer es darnos una toxicidad celular, sobre todo por estrés oxidativo y por reacciones inmunes. Esto va a generarnos muchos problemas, sobre todo a nivel digestivo, porque, como ya he dicho, la vía principal de exposición humana es la ingestión, a nivel sobre todo de intestino y hígado. Por lo que en este año 2023 nos han concedido un proyecto financiado por el Ministerio que durará entre 2024 y 2028, en los que vamos a tener estos 4 objetivos, que es determinar los niveles de microplásticos en los alimentos y bebidas, teniendo en cuenta también la influencia que tienen los envases, calcular la dieta total de estos microplásticos y la contribución que tienen cada grupo de alimentos, monitorizar la ingesta de microplásticos en humanos y evaluar el posible daño hepático que pueden promover, y evaluar el impacto de los microplásticos en la función intestinal y la posible relación con el daño hepático. ¿Cómo vamos a conseguirlo? Hemos establecido una metodología que se basa en 4 pasos. Ahora nos encontramos en el paso 1, que es analizar y caracterizar los microplásticos más consumidos, sobre todo en la población catalana, y estimar una dieta diaria de estos microplásticos, también teniendo en cuenta el envase que los contienen. Luego pasaremos a hacer una biomonitorización humana, en el que extraeremos muestras de sangre, de biopsia hepática, de yeyuno y de heces para hacer esta biomonitorización. Con las heces y el yeyuno lo que haremos es determinar los microplásticos directamente, y con los parámetros sanguíneos y la biopsia hepática nos podrá dar una información de cómo está el paciente a nivel metabólico y cómo se encuentra el hígado. Por último, ya realizaremos estudios ex vivo en este yeyuno para ver cómo afecta a los microplásticos de manera directa, tanto a la señalización intestinal como a la señalización celular, y estudios in vitro, que lo que haremos es ver la conexión entre intestino y hígado cuando le sometemos a una cantidad de microplásticos determinada. Por lo que, ahora nos encontramos en una fase muy preliminar de este proyecto, en el que lo que hemos hecho hasta ahora es analizar y caracterizar los microplásticos en agua de grifo, agua embotellada y refrescos de cola. Lo que hemos hecho es filtrar estas bebidas al vacío y hemos puesto un filtro de 10 micrómetros de tamaño de poro, donde recogemos todos los microplásticos, los analizamos en un estereoscopio óptico para contarlos, para ver su forma y para ver su color, y por último los analizamos mediante Raman o un FETIR para ver su composición polimérica. Nuestros principales resultados, si analizamos la cantidad de microplásticos en función a los dos tipos de productos obtenidos, vemos que la concentración de microplásticos es mucho más alta en refrescos de cola que en agua. Y además, si analizamos las morfologías más predominantes, lo que vemos es que este aumento se da sobre todo en los fragmentos y en los films. Pero si consideramos que el agua de embotellada y el agua del grifo no son el mismo producto, lo que vemos es que el agua del grifo tiene una concentración muy baja de microplásticos respecto al agua de botella, pero sigue siendo el refresco de cola el que más concentración de microplásticos observamos. También vemos diferencias significativas en cuanto a la morfología de cada uno de los plásticos encontrados. En cuanto a si solo analizamos la Coca-Cola dependiendo del tipo de envase en el que la contenía, o sea, si lata, vidrio o plástico, nos encontramos con que curiosamente los envases de plástico son los que menos microplásticos contenían, aunque estas diferencias no eran significativas. Pero si la analizamos en conjunto de todos, así aquí este gráfico tiene también el agua de grifo y el agua de botella, vemos que esta vez sí que es significativo que los microplásticos encontrados en los envases de plástico son los que tienen menor concentración, frente a que los refrescos de lata y de botella, si no tenemos en cuenta, claro, el agua de grifo que no está envasada en nada. Entonces, lo que nos lleva a pensar es que en los refrescos de cola la contaminación por microplásticos sí que proviene como de procesos de fabricación, pero en el agua sí que los microplásticos parecen provenir del proceso de envasado. Visualmente, un poco para que veáis lo que nos hemos encontrado, hemos visto que en los refrescos de cola encontramos films azules, fibras azules y fibras transparentes. En la Coca-Cola de vidrio lo que encontramos también son esas fibras transparentes y azules y algún fragmento azul. Y en los refrescos de cola volvemos a encontrar esas fibras azules y esas fibras transparentes, por lo que nos hacen pensar que sí que estamos en lo cierto, que pueden provenir directamente de la fabricación de esa bebida. Pero en el agua del grifo lo que nos encontramos es totalmente diferente, que solo había una concentración muy baja y era predominantemente por fibras, pero en el agua embotellada lo que encontramos son microplásticos muy diferentes, como por ejemplo el fragmento verde de allí, la fibra morada, una fibra azul y sobre todo ese film transparente que nos hace pensar que proviene del envase, pero debido a su similitud. Y lo más relevante que encontramos son estos fragmentos rojos, que fueron una de las marcas de agua embotellada, que por su estructura y color nos hacían pensar que podían venir del tapón de la botella. Y efectivamente, cuando analizamos ese tapón en el estereoscopio, vimos esas marcas que podrían ser de abrir y cerrar. Por lo tanto, sí que hay muchos microplásticos que provienen directamente del envase y de su uso o de su uso reutilizadamente, ¿no? Por lo que nuestras conclusiones preliminares es que las bebidas efectivamente están contaminadas con microplásticos y que las concentraciones más altas se encuentran en los refrescos, y estas contaminaciones parecen provenir no solo del embalaje, sino también del proceso de fabricación. Y además que el agua del grifo es donde menos microplásticos hemos encontrado. La diversidad de color y morfología de estas partículas nos indica que hay diferentes fuentes de contaminación que tienen que ser más estudiadas, y los resultados preliminares subrayan la necesidad de continuar este estudio para comprender mejor la magnitud y las fuentes de contaminación de los microplásticos en nuestra dieta diaria. Por lo que ese es nuestro estudio. Muchas gracias.
Muchas gracias, Andrea, por tu presentación. ¿Hay alguna pregunta en la sala? Sí.
Hola, muy interesante, muchas gracias. Quería saber si habíais hecho blanco, no sé si lo han mencionado.
Sí, normalmente cada vez que analizamos una bebida hacemos un filtro en blanco en la cabina de flujo laminar donde trabajamos, y luego también lo paso todo por el filtro al vacío, un blanco con agua ultra pura, que la hacemos agua destilada, la filtramos y con esa agua ultra pura hacemos los blancos.
Vale, que se los resta ya estos datos, ¿no?
A las bebidas, el de Coca-Cola a la Coca-Cola, el del agua al agua.
Vale, gracias.
Bueno, muchas gracias. Quería preguntarte si sabes por qué o por qué crees que la mayor parte de las fibras que encuentras son azules.
La verdad es que no. Supongo que también, o sea, a lo mejor en procesos de fabricación las gomas que utilizan los grifos son así azules, pero no sabemos todavía por qué se debe que son azules.
Gracias.
¿Habéis confirmado qué tipo de plástico es la fibra azul?
No, en estos estudios estamos ahora analizando con Raman y con Fetir, pero todavía no hemos confirmado cuál es la azul y cuál es la transparente.
Una pregunta. Y, o sea, ahora estoy pensando que, claro, ir mirando filtro por filtro y ir caracterizando, esto tarda un montón, ¿no? ¿Habría alternativas con imaging o con alguna alternativa que estuviese más automatizada que te permitiese hacerlo?
Creo que sí que han implementado un nuevo microscopio que ya directamente te hace como un barrido del propio filtro y te saca los microplásticos y que la composición que tienen. Lo que pasa es que ahora en nuestro laboratorio con nuestras capacidades tenemos que mirarlo nosotros y luego ya ir a Raman con los que hemos seleccionado. Pero sí que ahora hay tecnologías que cada vez están más a la orden del día y que nos facilitarían el trabajo. Sí.
Gracias por la presentación. Volviendo al tema este de los microplásticos azules, no sé, supongo que en las muestras de agua habréis analizado diferentes marcas y diferentes tipos de botella. No se lo digo porque, por ejemplo, hay la típica botella de agua azul. No sé si esta la habéis analizado para ver si...
Sí, o sea, hemos analizado la que es azul, pero también hemos analizado una transparente y una que el tapón sea rojo, verde, y en todas nos hemos encontrado esas fibras azules, con lo cual no creo que sea del propio envase azul, será de otro que tengan en común todas.
¿Otra pregunta?
Hola. ¿Habéis hecho un análisis de la distribución de las tallas de las partículas?
¿De la medida de cada una?
Ya.
En este estudio no, porque directamente filtramos con un filtro de tamaño de poro de 10, entonces es de 10 micrómetros para arriba. Entonces en el estudio preliminar lo que hacemos es fotografiar y luego ya a mano iremos viendo los tamaños más que se presentan más, nos iremos midiendo con el microscopio.
Vale.
Vale, ya está. Muchas gracias, Andrea. So now the next speaker is Judith Desmet from IDAEA-CSIC. She's going to present her work about flame retardants and plasticizers in Portuguese homes and schools.
Okay, so hello everybody. As Mavi said, I'm going to present the preliminary results from the flame retardants and plasticizers that we encountered in air samples in Portuguese homes and schools. So this project is being conducted within the in-child health project, and in general they want to detect the determinants for indoor air quality. So we have a lot of partners who each do their own part, and then also see what are the health implications for children. Our part is to analyze the plasticizers and the flame retardants, and because they are present in plastics, textiles, and a lot of other materials, because they are also legally required to be added for fire resistance and protection, and then also for the added physical characteristics that they provide these materials. They are added as functional additives, so this means that they are not covalently bound and they are easily released in their environments. And previous studies already found that they are present in higher concentrations in indoor environments. Then also there are signs that the health impacts that the health is affected by the exposure to these contaminants, and so that's why some of them are being restricted. Then we, as my colleagues also have said, we are detecting three main groups. The first are the organophosphate esters. They are the most common flame retardants and plasticizers, and so they have also been studied the most on their health impact, and there's more legislations on them. For example, these compounds have been these are examples from OPs, which have been assigned cancerogenic and hazardous limits by the Environmental Protection Agency from the US. Then the second group are the phthalate esters. They have been used for food packaging and in toys. and some of the toxic ones have been prohibited, especially the ones that were present in toys. And also for these, there have been limits assigned by the US EPA for their health hazards. Then the last group are the alternative plasticizer, which is basically a variety of base structures because they have been used as alternatives. And the problem with them is also that there's the least amount of information on toxicity available. And the main groups that we are looking at were the citrates and the adipates. And even though there's not that much information for some of these, there have also been risk assigned. So the objectives of the study were to determine the concentrations of the compounds to which the children are exposed through inhalation in homes and schools. We are comparing different environments, and then also the indoor versus the outdoor concentrations, and then also the summer versus the winter concentrations. The sampling locations were in Lisbon, and as you can see, we had 3 schools, but in this school we both looked at a gym and at a classroom, and then 5 homes as well. We collected the air samples using these SPE cartridges. They have a specific matrix that, due to its characteristics, binds our compounds using different bonding principles. And we connected the cartridges to a Leyland pump, which was sampling at 4 liters per minute. So as I mentioned before, in summer and winter, in the outdoor, and we use them during the occupational times of the children. So like in schools, we use them during the day for 5 days of the week, so from Monday till Friday. And in homes, we started the measurement Friday evening and started it with like a 30-hour measurement, so we didn't have to come back during the weekend, and then 15 hours per day during the weekdays. For the extraction, we extracted it with hexane acetone, then evaporated the extracts and reconstituted in methanol, and the analysis was performed in a liquid chromatograph. For the results, 28 out of the 42 compounds that we were looking at were detected, and I'm showing the ones that were detected with concentrations higher than 5 nanograms per cubic meter. So as you can see, like all 3 groups were detected, and of these, some of them were compounds that were like assigned maximum values for exposure. And just as an illustration, like the ranges in which the compounds were detected. And as you can see, it varies a lot, like depending on the compound, and especially the diethyl phthalate and the 3-ethyl citrate were detected in quite high concentrations in some of the samples. Then for the comparison between indoor and outdoor in schools, the PE group, the phthalate esters, they were found in quite higher concentrations than the OPs and the alternative plasticizers. And for all 3 of the groups, the indoor environments were found, the compounds were found in higher concentrations than the outdoor, but the smallest difference was with the OPs. But even though it was smaller, it was still significantly higher. So this is like showing that the previous studies, it's showing that in the previous studies where it also was found higher in indoor concentrations, it's just a confirmation of it. Then for summer versus winter in schools inside of the classrooms. So also here you can see that the PEs were the main group, and this was more obvious in the summer than in the winter. And then also the APs were found in higher concentration in summer, while the OPs were found in more or less similar concentrations. and then comparing the schools versus the homes, it shows that the schools have like more or less homogeneous profiles compared to the homes where the concentrations varied a lot. Yeah. And then I also wanted to show like geographically how the concentrations were distributed, but like for the total plasticizers. And so like in total concentrations, also more plasticizers were detected in homes than in the schools. Yeah. And then to conclude, we used the SPE cartridges to collect air samples. 28 compounds were detected. For the different settings, all the 3 groups were significantly lower present in indoor concentrations compared to outdoor concentrations. Then the phthalate esters and the alternative plasticizers were present significantly higher in the summer. And then the phthalate esters were present in significantly lower concentrations in the schools. And for total plasticizers, it goes the same, like in schools, the concentrations were significantly lower than in the houses. So thank you for your attention. I would like to thank the group in Portugal for their efforts of sampling and the funding by Europe.
Thanks, Judith, for this interesting presentation. There is any question for her?
Hello, thank you for your presentation. I was wondering if you had any hypothesis for the reason of finding more plasticizers in homes, for example, regarding than schools, and also I didn't see a clear pattern in the geographical pattern. Was there any reason for which you found in some homes higher plasticizers than in others, and same in schools?
So for the geographical pattern, I think it's mainly because it's about the concentrations indoor. And the main sources of the plasticizers are also indoor. So geographically, an airport is not going to affect that much, like how much plasticizers you find indoor. And then the other question, can you remind me?
Why you finding more plasticizers in homes and schools? I guess because of the type of products that we use, but if you have any others.
And also the, a school in general, they are more equal. Like you will find similar products and like furniture in each school, like compared to a home. Might differ a lot, on when your building was built, or what your parents put in your home. Like if you have siblings, if you have really small children, or or if you're sharing with with the older siblings or not.
Okay, so depending on the construction itself, the building, but also the products you use, of course.
Yes.
Okay.
Yes.
Thank you.
Thank you. Is there any way that you can weight those results by the volume of the place you sample? Because I don't know if I follow you, if you collect, I don't know, in a house that it's 40 square meters, and the school has I don't know 60 meters.
Yeah, I understand what you mean, but then it's also it's quite difficult to do it that way, because also somebody can open a window and then you should consider the outdoor environment as well. So, the way that we were normalizing the data, let's say, was by the total volumed amount.
Okay.
Yeah.
Then yeah. Okay.
Yes.
Thank you.
Yeah. Regarding this, I have also a question. Because I saw that, for example, during the weekends at home, you put that you were sampling during 30 hours, 15 one day and 15 the other one. It means that this sample is just one cartridge is containing these 30 hours, or it is changed?
So each cartridge was during the whole sampling period. So for the schools there was the full 5 days, and then also for the homes it was like this 30 hours for the weekend plus the full 5 days.
Okay, and you correct the final results, normalize it by these hours and all the volume.
Yes, exactly.
Okay, thanks. There is any other question? No? If not, thanks, Judith. And now we will move to our last speaker, who is David Alcaide from IDAEA-CSIC also. He's going to present us the study of micro and nanoplastics in stool samples by the analytical development.
Hello, and thanks for your kind presentation. Today I'm going to present one of our latest work titled Study of Micro and Nanoplastics in Stool Samples. As an outline of my presentation, first I will introduce a brief introduction between human health concerns and microplastics. Then I will state the objectives of this work. Third, I will explain the analytical approach we did in our laboratory for the analysis of stool samples. Following that, I will explain the results of the analysis of real samples, and finally I will conclude with the key points of this study. So, as we all know, microplastics can enter the body through 3 different pathways: inhalation, digestion, and dermal exposure, and this can lead to some kind of toxicities. First, physical damage by the size of the particles, and this can induce in oxidative stress, inflammation, translocation, and even the development of cancer. And also, we all know that these plastics contain plastic additives that can lead to chemical effects, and it can be endocrine disruption, hepatotoxicity, and cancer. So there is an increasing concern about human exposure to micro nanoplastics and their implication for health, particularly on sensitive populations such as children. Therefore, the objectives of this work are to develop and optimize the extraction procedure of micro nanoplastics to assess the polymer contents in stool samples, and to apply this approach to the analysis of 98 samples of stool collected under the frame of the EXMINA project. Considering the low levels of micro nanoplastics expected in a stool and the difficulties in their analysis, particularly of nanoplastics, an optimal extraction and cleanup procedure is essential for accurate analysis. So what we did first was the sample collection, and this protocol was developed to avoid cross-contamination. Then we lyophilized the sample to homogenize it and also to eliminate the water content. As a first trial, we tried to do a water solution of the stool and to filter and do the analysis, but we saw that we have a lot of matrix interferences, so a digestion step was needed for the further analysis. In our research group, we have some experience in the type of digestions, and we consider for the oxidative, the alkaline, the acid, and the enzymatic one. We first eliminated the acid one because, being the most effective one, it also damage the plastic particles on the surface. Also, we eliminate the enzymatic one because even it's high efficient, it's also highly expensive. So we are left with the oxidative and the alkaline one that are high efficient, and it doesn't damage the plastic particles. And as for these reasons and the ones I'm going to explain later, we choose the oxidative one. So for the oxidative digestion, we're going to use the Fenton reagent, that is a mix of hydrogen peroxide and the Fenton reagent, and an iron catalyst, and can break down a wide variety of organic compounds. So in general, for this type of digestion, 100 milliliters of hydrogen peroxide, 40 milliliters of Fenton reagent, and 50 milliliters of nitric acid are employed. But we did this, and the recoveries we got were really low, between 30 and 35%. So we thought that we needed to do a small change of the procedure. So we reduced the amount of reagent used, and we did the digestion overnight. And with this, the recoveries increased from 40 to 65%. So for this type of digestion, we have some pros and some cons. On the pro side, we have that it has a high efficiency in the degradation of organic compounds. The reactant we are using are cheap and accessible. There's no need of working at high temperatures, and it's a non-selective process. On the other hand, we have that we need the pH to be acid between 2 and 4. We use high volumes of reactive for a single sample, and it's a non-controlled reactivity. So the new dilution approach is the following one. To 2 grams of sample, we're going to add the Fenton reagent and the hydrogen peroxide, and we're going to do the digestion overnight. Then, the day after, we are going to centrifuge the sample, and we're going to add water. Then we will centrifuge again, and the supernatant is going to be filtered. And to this filter, we are going to do a 10-minute acid digestion to eliminate the organic compounds that could be left. When it's finished, we are going to add water to clean the acid that's left, and we are going to add ethanol for fast drying. Once we have our filter dried, we're going to do 3-type extractions. With half of the filter, we're going to do a toluene extraction, and we're going to analyze by size exclusion chromatography coupled to high-resolution mass spectrometry with an ionization source of APPI. With this, we're going to detect polyethylene, polypropylene, polystyrene, and other polymers. With the quarter of the filter, we are going to do the same kind of extraction, but we are going to add acid. So we are going to be able to detect polyethylene terephthalate. And with the other filter with the other quart of filter that's left, we are going to do a methanol extraction, and we are going to do analysis by liquid chromatography coupled to high-resolution mass spectrometry with an ionization source of electrospray. And with this, we will be able to detect polyamide. The reason we are doing a toluene extraction is because it has a high efficiency on the extraction of micro nanoplastics, and also because it acts as a dopant in the further analysis because it enhances the signal of these compounds. So when we have all our samples ready, we're going to inject it by liquid chromatography, and the polymers are going to be separated by a size exclusion column, and it will be ionized by a PPI source. So in this slide, I'm showing you the typical mass spectra of polymers, and in this slide, we can see the mass spectra of polymer, and we can see the monomers losses between all the peaks in this case. So for the data treatment, we're going to use Excalibur 2.1 software. And as we all know, real plastics are composed by a dispersion of polymeric chains on different lengths. And for this reason, we are going to have different retention times because our column is not going to separate the type of polymer, if not the polymer size. And thanks to high-resolution mass spectrometry and the Kendrick mass defect, we can provide the information about the identification and quantification. So here we have an example. In the chromatograph peak above, we can see that there's only one corresponding to polyethylene, but in the chromatogram below, we can see that we have 2 different types of chromatograph peaks. And the thing is how we can zoom these 2 peaks if they have different retention times, even being the same polymer. So we're going to do this with the Kendrick mass defect graph. So we're going to plot in the x-axis, we are going to plot the exact mass corrected by the repeating unit, in this case the polyethylene one, and in the y-axis we are going to plot the difference between the exact mass and the Kendrick mass. If all the data, when it's plotted, it's parallel between one and another, we can conclude that this is the same polymer, so we can sum the 2 areas we obtain of the 2 different chromatogram peaks, and we can quantify the total amount of polyethylene in this case. So here I'm showing you the analytical parameters that we obtained. We obtained a good limit of quantifications and also a good precision for the type of sample we are analyzing that are really dirty. Some precautions we need to have when we are working. First of all, we have to wear cotton coats. Then we have to work always under laminar flow cabinets because of the reagents we are using, and also we have to maintain a clean lab environment. For the procedure blanks, we did the same. We did one for every set of samples we were extracting. We also, the same extraction procedure was done for the blank, and the blank consisted in an empty bottle where we were putting the sample. Now I'm going to pass to the results section. In a total of 98 stool samples, in 68% of the samples, microplastics were detected. In 47% of the samples, micronanoplastic could be quantified, and in 40% could only be detected because they were below the limit of quantification. The polymers we found were polyethylene, polyoxymethylene, polypropylene, and polyamide, and we quantified and detected among all the samples. Here I'm showing you a graph of the ranges of concentrations that we found in this kind of samples, and polypropylene and polyamide were the ones found in larger ranges of concentration, and polyethylene and polyoxymethylene in shorter range of concentration. As you might think, this could be a higher concentrations for this kind of samples, but if we compare to other studies, they are really low. So here I'm showing you a comparison between two different studies, and we have about 200 micrograms per kilogram, and other studies have higher ranges of concentrations, and this could be because they are using different analytical approaches. So the conclusion of this work is the optimization of the digestion protocol for the assessment of micronanoplastics in stool samples was performed with an improvement of the recovery rates. 98 stool samples were analyzed with concentrations ranging from 0.45 to 105 microgram per kilogram. Polyethylene, polypropylene, polyamide, and polyoxymethylene were the compounds found in the 68% of the samples, and comparison with other studies is difficult because of differences in analytical approaches. Most of the available results are based on particle counting, so fibers and fragments are assumed to be spheres of medium size. Unorganic compounds sometimes is considered as a plastic particle, leading to overestimation when the results are expressed in mass units. Last but not least, I want to say thank you to the two projects that allowed me to be here, the ANSYS project and the TWIN, and I want to say thank you for your attention.
Thank you very much, David, for your presentation. Is there any question in the audience?
Thank you for the talk. It was a very good one. There is no way to calibrate, having like standards of microplastics to intercalibrate the different protocols, because the last slide was amazing. Like, you found so little and other people found so much.
Yes, what we do is so we have standards of the different kind of most abundant microplastics. So what we do is calibration curves. So with this, we can know that if that's there or not.
Yeah, but for the recovery, like for the recovery, when you apply your methodology, you recover 100% of what you had?
Yeah, because we first do a study, an analysis of the samples, so we can know if there's some of them that are with no contamination of micronanoplastics, and we expect them to know the recovery rates when we do the extraction procedure.
Thank you. Other questions? I was wondering, where did you get the samples? Maybe you explained it, or maybe I missed it.
Well, we don't really know where the samples come from, but we know they are adults. That's the only information we have.
Specific population.
Yeah, I mean, it's in Catalonia, I think, but we only know that.
Yeah, okay. Thank you very much. Thank you. So we are finished, but now maybe Ethel wants to say some words to close the event.
Bueno, pues aquí llegamos ya al final de estas terceras jornadas de contaminación por plásticos. Antes de despedirnos, quería volver a agradecer a Luis Cabedo por la presentación de esta mañana, que nos ha dejado un poquito más claro la situación actual de los bioplásticos y hacia dónde hay que seguir trabajando e investigando. Luego también me gustaría agradecer a los chairmans de las sesiones de ayer por la tarde y de hoy, de las 3 sesiones, que han ido llevando estos 3 grupos de sesión que hemos planteado. Por supuesto, agradecer a todos los ponentes, tanto a los que habéis hecho las presentaciones orales como los que habéis presentado vuestros trabajos en formato póster. Bueno, ya sabéis que estas jornadas las planteamos de manera bianual, o sea, en principio os esperamos a todos dentro de 2 años, en el 2026, así que os animo a todos a seguir investigando en estas temáticas que, como veis, todavía hay mucho trabajo por hacer. Así que bueno, pues animaros a seguir investigando sobre el problema de la contaminación por plásticos. Y antes de dar ya por concluida las jornadas, sí que quería también agradecer a los miembros de mi grupo de investigación que, aparte del aporte científico en las jornadas, pues bueno, habéis tenido también que veros involucrados un poco en ayudar en temas de organización. Y por supuesto agradecer al Departamento de Comunicación del IDAEA, a Alex, a Ana y a Iria, pues por todo el trabajo y apoyo en la organización de estas jornadas. Así que bueno, un saludo a todos y nos vemos en un par de años.